Welcome back. So far, we've used several Unreal Engine classes from the class hierarchy, but we have not yet used the character class. Now, we've seen that the pawn class is derived from the actor class. Well, the character class is derived from the pawn class. So while the actor has its own capabilities, for instance, being able to be placed or spawned in a level, the pawn inherits those qualities from the actor class, as a pawn is an actor, but it also has its own characteristics that the actor does not have, such as the ability to be possessed. And the character inheriting from pawn also inherits the ability to be placed or spawned in a level, and also inherits the ability to be possessed, but it also has other more specialized characteristics specific to game characters. We'll talk about those now. The character class has a character movement component. As we saw with the pawn class, pawns do not automatically get a movement component. We had to add one. We added a floating pawn movement component to our bot pawn, for example. Well, the character class already has a movement component, and this character movement component is specific to characters. It moves characters in ways that characters should be moved. Characters also have a mesh component. So with our bot pawn, we had to add our static mesh component to it, but characters already have a mesh. Now, a character does not have a static mesh. It has a skeletal mesh component, which is different, and we'll discuss those differences soon. Characters also have an arrow component, which is something that you don't see in the game, but it's visible in the editor to show you which direction is forward for the character. Now, it's very common for the character class to have a camera component attached to a spring arm component, just like we did with our pawn. Now, this is not built into the character class, but I'll mention it here because it's one of those very commonly added things that just about all characters will have, at least those that will be controlled by a human player. Now, aside from these components, a character will also have a set of character-specific functions that the pawn class does not have. Now, we mentioned that characters have a skeletal mesh component, and that this is different than the static mesh component, which is what we've been using thus far. A skeletal mesh component differs from a static mesh component because it has a skeleton. A skeleton is a hierarchy of what we call bones. Each bone is skinned to the mesh, which means that when a bone moves, some of the polygons of the mesh move with the bone, and these are arranged in a hierarchy of attachment. So one bone will be attached to another bone in a sort of parent-child hierarchy. And these bones can get quite intricate, even down to the smallest appendages such as fingers. Now, skeletal mesh components do not have collision hulls. That's not to say that they don't have simple collision. Their simple collision comes in the form of a special type of asset called a physics asset. A physics asset can have multiple collision shapes, and these are attached to various bones, so when a bone moves, those collision shapes can move with it. We call these shapes physics bodies, and they can come in the form of simple shapes, such as capsules and boxes, etc. This allows for the mesh to move around in the world and animate, and those physics bodies will move along with that skeleton, allowing for a more dynamically moving set of collision shapes. So now that we've seen some of the differences in the character class, we're now ready to start creating our own, but we're going to need some assets for this next game project. So you're going to download the Jetpack sample project in the resources for this video, unzip it, and open it up. So I'm here in my Jetpack project, and as we can see, we just opened up to a default level called Jetpack level. which is pretty empty, but we have some assets in our content folder. And what I'd like to look at right now in the assets is the Kix folder, K-I-X. Kix is the name of this particular character, and we have some assets pertaining to Kix. The first one I'd like to take a look at is SKM Kix. Let's double click that. Now, SKM Kix is a skeletal mesh asset. As we can see, the naming convention is SKM Kix. SKM is short for skeletal mesh. And Kix is a nice stylized humanoid asset. Humanoid meaning it's roughly in the shape of a human. It has arms and legs and a head and a torso. And being a skeletal mesh asset, the asset has a skeleton. Now, we have a panel called the skeleton tree, which shows us the hierarchy of bones. These bones are each connected to one another in a hierarchical fashion. Every indentation indicates attachment. One bone is attached to its parent bone, and if its parent bone moves, all child bones move along with it. So each bone has its own individual transform. And these bones are skinned to the mesh. When one bone moves, it moves the polygons of the mesh itself according to how the mesh is weighted to those specific bones. Now, we can see the skeleton if we go up to Character, and under Bones, we can select All Hierarchy. If we choose that, we can now see all the bones, and we can click on them and select them. And we can see the names of those bones. And in the skeleton tree, we'll see them on the hierarchy as well. I just selected a Kix neck base joint bone, which is connected to another bone, which, as we can see, following the attachment chain, is attached to way up here the Kix spine joint, and multiple bones can be attached to a single bone. Now, we can rotate this bone here in the skeletal mesh editor, and notice that the mesh moves along with these bones. And we can see how moving one bone moves the child bones as well. And this is how animation is handled in a game engine. A skeletal mesh has a skeleton, which is weighted to the bones. Now, we can see the weighting of each bone if we go to Character, Mesh, and under Mesh, we can go all the way down to Selected Bone Weight. And if we select that, now I can see not only the polygons of the mesh, but the weighting of a given bone. I have this bone on the arm selected here, and where it's red is where those polygons are weighted to the bone the most. So it's color-coded in a sort of heat map. And that just means that if I move this bone, those red polygons move along with the bone, and the other polygons have less intense weighting to that bone. And we can even see that the fingers themselves have weighting, even down to the tiniest little appendage at the end of the hand there. So this can get quite intricate. So animation is handled by moving these bones, and the mesh moves along with the bones. And as we saw, the collision for a skeletal mesh component comes in the form of a physics asset. And we do have a physics asset called PhysKix. If we open that, we'll see those physics bodies. There doesn't have to be a shape for every single bone, but the ones that we do have are connected to the bones. And depending on the game, we may have more detailed physics assets or less detailed ones. So this is the simple collision for our skeletal mesh component. We'll go ahead and close that. Now, I did select the bones and moved them, but don't worry, as soon as I close this, those changes in the transforms of those bones will not be saved. So I'm going to go to Character under Mesh, and I'm going to select None under Mesh Overlay Drawing. Now we don't see those polygons and their weights. And I'm going to go to Character and choose Selected Only, And that way we don't see all the bones, we only see the bones that we've selected, and we can select them here in the skeleton tree. And as I said, if I close this and I open it back up, SKM Kicks, it's back in its base pose, so we haven't changed anything. Now, a skeletal mesh asset is associated with the skeleton, as we can see to the right, but we're in the skeletal mesh editor. There's also a skeleton asset editor, and if we double click on SkelKix, we'll see that this is the skeleton asset editor, and it looks a lot like the skeletal mesh asset editor, but we're just looking at the skeleton itself. And of course, we will see the mesh too, but this particular editor is just the skeleton editor. And at the top right, we have a set of icons, and we can switch between different asset editors because the engine knows that this skeleton is associated with SKM Kicks. So the first icon says SkelKix, and it has an icon of a skeleton. The next one says SKM Kicks, and it's an icon of a mesh. If I select that, now I've opened the skeletal mesh editor. The next icon over is for animations, and if I click on that, it's going to open the animation editor. And now we can see this animation asset that it just chose for me, and it's called AKix Idle, and it's showing me kicks in an idle animation. And in the asset browser to the right, we can double click on any of these animation assets, and we're playing those animations so we can see kicks, in this case, playing a grab animation. And we can also see the skeleton tree over here to the left and select bones and see those bones moving along with the animation. So animation assets, skeletal mesh assets, and skeleton assets are closely connected to each other, and that's why we can open those assets really quickly using the icons at the top right of these editors. So now that we know we have a skeletal mesh asset that we can use for a character, we can now begin creating the character class for this game project. And we'll do that in the next video. I'll see you soon. Welcome back. We're now ready to create our very first character class. I'm going to go ahead and close all the asset editors that are open and create a new folder in my content folder. So this one will be called Blueprints. We'll keep all of our blueprints in this folder. And in Blueprints, I'm going to make a new folder called Kix, K-I-X. Here in Kix, we'll create our character class. So I'm going to right-click, select New Blueprint Class, and for the first time, we're going to choose Character. I'm going to call this BP_Kix, nice and short, and I can open up BP Kix, and right away, I'm noticing that this asset editor has opened in a new window. I'd like it to open automatically docked up at the top, so I'm going to go to Edit, Editor Preferences, and change my asset editor open location to main window, so that won't happen again. All my asset editors will open docked at the top. Okay, so with BP Kix open, we can see what the blueprint looks like. We have a viewport tab, a construction script tab, and an event graph, much like actor blueprints. We even have those 3 grayed out events: begin play, actor begin overlap, and event tick. Now, let's go back to the viewport. Notice we already have a couple of things. We have what looks like a capsule and what looks like an arrow, and that's what those are. We have the capsule component and an arrow component as well. The capsule component for a character is the root component. Notice the pop-up says it cannot be renamed or deleted. Character classes have to have a capsule as their root component. This cannot be changed, so this is a limitation of the character class. Attached to the capsule, we have the arrow component and the skeletal mesh component. This component is called mesh, and it's inherited from the character class. And notice that beneath these components, there's a line under which we have character movement. This is the character movement component. It's separated by this line because character movement component does not have the ability to be attached to another component. It's based on the actor component class, but it does not have collision or the ability to be attached to other components. So components that don't need attachment do not exist in the attachment hierarchy that we see in the components panel. They exist by themselves beneath this horizontal line. Now, if we select the mesh component, we'll see in the details panel under mesh that it has a skeletal mesh asset variable. We've already seen that a static mesh component has a static mesh asset. So skeletal mesh components are similar, except their mesh asset is a skeletal mesh. So the character cannot have a static mesh assigned as the mesh asset for its mesh property. If we wanted a static mesh, we'd have to click Add and add a static mesh component and use that. But that's okay because we do have a skeletal mesh component that we can use. If we open the dropdown, this startup project already has SKM Kicks, as we've seen. So by selecting the skeletal mesh asset, we have Kicks, and notice that something looks off, right? Kicks is a little bit too high, and Kicks is also facing the wrong direction. And this is a very common situation you'll face in Unreal Engine when you create a character blueprint and assign a mesh to that skeletal mesh property. You see, the reason that it's facing the Y direction and not the X direction is because that's just how this mesh was created. Its pivot point faces the Y direction, and this is going to be very common. If you go to the Unreal Marketplace and you download a skeletal mesh asset, it will most likely be facing the Y direction. But that's okay because our mesh is not the root component. We can rotate it relative to the root component. So I can select rotation, and I can take the gizmo and rotate it by 90 degrees, and now Kicks is facing the character's forward direction, the X direction as indicated by the gizmo at the bottom left. Now we can also move Kicks down. I'll just hit W and move Kicks down slightly, but we're going to want Kicks to have their feet at the bottom of the capsule, and I'll show you why. Let's just go into our level here and drag our BP Kicks into the level and release, and just take a look at what happens here. The capsule is on the ground, the feet are above the ground, and that's because the character class uses this capsule component for lots of things. It uses the capsule component when placing the character on the ground. It's placed based on that root component. So the bottommost part of the capsule is what touches the ground. So we want our mesh to be on the ground based on the lowest point of that capsule. Characters also use the capsule component for lots of collisions. Yes, we have the physics asset if we want more accurate collision detection, but for most collisions, characters use this capsule component to detect collisions with walls, for example, with the floor, with the ceiling. It's the capsule that bumps into these objects and prevents the character from moving through them. So we also want that capsule's height to be appropriate for the Kicks mesh. So in the character blueprint, we're going to resize that capsule just a bit. By selecting the capsule component, we're going to change some dimensions on it. Now, we don't want to change the scale. What we want to change are the properties on the skeletal mesh component for the height and the radius. For the height, capsule components have a property called capsule half height. Now, we're going to click and drag it to the left until we have a bit shorter of a capsule. I'm just going to keep going until I see it just about at the right size. It doesn't have to be perfect. I'm going to enter in 75, and we can move Kicks down just a bit so that the feet are just about at the bottom of the capsule. So with a little bit of tweaking, we can zero in on some dimensions that look right. Looks like I set the capsule half height down to 70. And because my capsule half height is 70, I can also take my skeletal mesh component and go to its location here and see that -70 is its Z component. So that's going to put those feet just about at the bottom of the capsule. And we can go back to our level and move our character down to the floor, and we'll see that that looks just about right. Now, we don't want that radius to be too thin. If we wanted to, we could bring that capsule radius in so that it's about as thin as the head, for example. But if we did that, then we could bump into walls and we could see those arms passing through walls, which is not something we want. So I'm going to leave that capsule radius at about 34 to give us a bit of leeway, a little bit of space between walls and the character mesh. And now we have our very first character. Now, our project still needs a few things. If I press play, I'm not going to automatically possess Kix. I'm possessing the default pawn because we don't have anything telling our project to use this particular character blueprint as the default pawn. So we're going to need to do that. And we're also going to need to set up movement inputs so that we can move this character around. But for now, this is a good start. We have our character and we're ready to continue, and we'll do so in the next video. Great job, and I'll see you soon. Welcome back. Now, we need a few more things before our project is going to start feeling like an actual game. For one, we've seen that when we press play and start a Pi session, we just start possessing the default pawn. We want to possess our character class, this BP Kix character class. So to do that, we're going to create a game mode specific to our Jetpack game. And we can designate Kix to be our default pawn. So first, I'm going to go to my blueprints folder and make a new folder for game-related classes, such as the game mode. So I'll call this folder game, and in the game folder, I'll create a new blueprint class based on game mode base. I'll select that, and we'll call this BP Jetpack Game Mode. So this will be specific to the Jetpack game project. Let's open it up. And the first thing I'll do is go to the default pawn class, change this from default pawn to BP Kix, and compile and save. So now we have a game mode where Kix is the default pawn. We just need to make sure that the game mode is used by our project. If we go and press play, we're still just going to possess the default pawn because we're not using that game mode class. I'm going to set that game mode for our project. So I'm going to go to Edit and Project Settings, go to Maps and Modes, and change the default game mode from Game Mode Base to our game mode BP Jetpack Game Mode. Now I'm done with project settings, and if I press play, I'm now going to be possessing Kix. It's hard to tell, but if I go ahead and detach and move around, I can see that I was inside of Kix's head because we are now possessing Kix. And I can reattach, and I'm now on Kix, but of course we can't move. If I click to engage in the level, there's no WASD movement, there's no mouse movement, there's no way to move Kix at all because we have to set those things up as we learned in our previous project. We had to set up enhanced input, right? Now, another thing to keep in mind is if I press play and I go ahead and detach and turn and look around, I'll see that there's still that Kix character over there. We're actually possessing this new Kix that was dynamically spawned in thanks to the game mode. That one back there is just sitting there in the level. So that could be a source of confusion if your game mode is spawning in your default pawn class. You don't really need to have your character sitting in as an instance in the level, just there already. So I can take this instance of Kix, I can delete it, and now if I press play, I can detach and turn around and look and see that there's only one Kix, and that's the one that we are possessing by default. So now that we have a game mode for our game and we've set the default pawn class, we're now ready to continue developing our Kix character. I'll see you in the next video. Welcome back. In this video, we're going to add a camera and spring arm component, and you may have actually seen the title of this video and gone and done it yourself. Feel free to do that. You can go ahead and just pause the video and do it, or do it along with me if you like, but we're going to add a spring arm component and a camera component for our character. Now, these can be attached to our capsule component. So with the capsule component selected, I'm going to add a spring arm first, and we can just let it be called spring arm. And with spring arm selected, I'm going to search for camera and add a camera component. And now we have our camera. Now, I'm going to just leave it as is. I'm not going to rotate it by selecting the spring arm and changing its rotation. I don't need to do that. Once we configure input, we're going to make our camera move along with our mouse so we can look around and see Kix from different angles. Now, the spring arm target arm length is something we could adjust if we like. I might set it to 250 to bring it in closer, or I can bring it farther out. It depends on your preferences. But now if we press play, we can see Kix from behind, and we're no longer looking out from the inside of Kix's head, which is great. So now that we have a camera and spring arm, it's now time to set up input for our project so that we can actually move that camera and look around, and of course move our character as well. You may have noticed that our character has a jetpack on their back, and that is something that we plan on making fully functional so that Kix can not only run around, but fly around as well. So we've got some really exciting things in store for this game project coming up. Great job, and I'll see you in the next video. Welcome back. It's time to start implementing input for our character. And I'd like to start by being able to look around by moving my mouse. Now, we've seen in our previous game project that we could implement movement by creating enhanced input assets, such as input actions and an input mapping context. We're going to do that same thing in this video, except we're going to do things a little differently than we did for our bot pawn. In our bot pawn, we went to our event graph and we associated our input mapping context directly with the pawn, and we implemented functionality in the pawn event graph. Now, that's one way to do things. Another way is to implement movement on the player controller class. Implementing movement on the player controller allows us to keep our character class uncluttered so that we don't have too much functionality on the character class, and we're letting the controller handle the movement as a way to keep a separation of concerns so that we don't have too many things handled by any one given class. In programming, when one class gets larger and larger and handles more and more things, we call that a God class. And that's typically a pattern that we try to avoid. So first, we need input actions and an input mapping context. Now, if you feel so inclined and you'd like to get some practice trying this on your own, create an input action and an input mapping context for our Kix character. If you'd like, pause the video and do that now, and come back and watch the rest of the video, or you can just do it along with me by continuing with the video here. Okay, so what we're going to do is go into our blueprints folder, make a new folder for our input, associated classes. We'll go into Input, right-click, and make a new folder here called Input Actions. And we need a new input action. Now, this is going to be for looking around. That's a two-dimensional input. We have a mouse x-axis and a mouse y-axis. So let's make our new input action. We'll go down to Input and select Input Action. We'll call this IA Look. And IA Look can have its value type changed from digital bool to axis 2D vector 2D. And now we just need to associate this input action with our mouse XY movement. And we can do that with an input mapping context. So we'll go to Input, and we'll put our input mapping context right here. Right-click, Input, Input Mapping Context. We'll call this IMC Kicks Movement. The name isn't too important. And we'll open this up and add a new mapping here. Opening the dropdown, we can select our IA Look input action, and we just need to associate it with a given type of input. So I can open the dropdown, go to Mouse, and select Mouse XY 2D axis. So now we have an input mapping context, and we just need to associate it with our character. Now, I mentioned we're not going to put that association in our character blueprint, but rather in our player controller class. So that means we're going to need to create a new class for Kix's player controller. And that's where we're going to add our input mapping context and add the functionality to tie in our IA Look input action to moving our camera. So we'll create that new player controller class in the next video. Great job, and I'll see you soon. Welcome back. So we have Kix and things are looking great. We also have an IA Look input action that we've added to an input mapping context, associating this input action with the mouse XY 2D axis. And we mentioned that rather than adding the input mapping context to the BP Kix character itself here in the event graph, we're going to do this on the player controller class instead. And for that, we need our own player controller class. So let's go ahead and make one. We'll go to Blueprints. We'll make a new folder called Player. And here in Player, we can make our custom player controller class. We'll make a new blueprint class. We'll choose player controller. And I'm going to call this BP Kix player controller. Now we have a new player controller class, but that does not mean necessarily that we're going to be using it when we go and press play. In fact, we won't be if I press play and start a Pi session. What we have to do to use our new player controller class is we have to designate this player controller class as the default player controller class for this game project. And we know that we're using our BP Jetpack game mode. This is where we can specify the player controller class right here under classes. By default, it's set to the base player controller class, but we want our specific child of player controller called BP Kix player controller. So now that we've specified that class to be our player controller class, now we'll be using that. And we can prove that by opening our new BP Kix player controller. Here's the blueprint for it. We can go to the event graph, and look, our player controller class has a begin play. Why don't we prove that this is running by using a print string node? We'll print BP Kix player controller in the print string, and we can go and start a Pi session. And there we go. We see BP Kix player controller at the top left, which proves that our new player controller class is actually being used. And this is the player controller that's possessing our BP Kix character here. And in this player controller class is where I'd like to add our input mapping context and implement our look behavior. Now, before we go and do that, I'd just like to remind you how we did it before in our previous game project. We did it in the pawn class. We did it in bot pawn on begin play. And I'm going to run through that process just as a refresher so that you can remember what we did, and also so that we can see how that process is slightly different in the player controller class. So I'm going to delete these two nodes and leave begin play there, and remind you how we added an input mapping context to our pawn in begin play. We first called get controller and used this controller in a cast node. We used cast to player controller. And once we cast to player controller, we then had the ability to get what's called the enhanced input local player subsystem, this big fat node here. And from that local player subsystem, we were then able to call add mapping context. So we called this add mapping context function, specifying the mapping context. We could choose IMC kicks movement, for example. Once we did that, then we could go and search for the IA look enhanced action event, and we could implement movement functionality from here. That's how we did this on the pawn class in our previous bad bot game. Now we're going to delete these nodes because we're going to implement this on the player controller instead, but I want to point something out to you. Part of this process involved getting the controller that's possessing this particular pawn, casting it to the player controller class, just so that we could get the enhanced input local player subsystem from it. That's because this enhanced input local player subsystem is accessible from the player controller class. Well, our class BP Kicks player controller is derived from the player controller class. In other words, it is a player controller. So it just already has access to that enhanced input local player subsystem. So we can access it here in Kicks player controller just in the event graph. Let's do that. First, I'm going to delete my print string. I'm going to delete my event tick. I don't need that. And I'm going to search for enhanced input local player subsystem. I don't even have to type the whole thing. Now, there's a couple of options. One is get enhanced input local player subsystem, and this exists under something called local player subsystems. But there's also a get enhanced input local player subsystem under the player controller. Let's choose that one. Notice that this one has an input. If we hover over it, it says player controller object reference. So it requires an input because we need to get that enhanced input local player subsystem from a player controller. Now we can always right click and type self and get a reference to self, and we can plug that in to satisfy that input, and we can get the enhanced input local player subsystem that way. But let's right click again and search for enhanced input local player subsystem, and let's choose the other one, the one that's under local player subsystems, not under player controller. This one does not have an input. This just allows us to access the enhanced input local player subsystem from this player controller that we're in. So we don't have to pass in self, and for that reason, I like this one better for use within Kicks player controller. So we don't need to use the one with self, we can just use this one. Now back in BP Kicks, once we access that enhanced input local player subsystem, we were then able to call add mapping context. We can do that here in our player controller as well. We can drag off, type add mapping context, and get that function and call it on begin play. So as you can see, the process is actually a little bit easier on the player controller. We use less nodes because we don't have to access the controller and cast it to a player controller here. We're already inside of a player controller. So we already have access to that local player subsystem. Now we can just choose the mapping context, and we can simply select Kicks movement here, and now we've added that mapping context to this player controller. Now we can go back to BP Kicks. We don't need these nodes anymore. We were just looking at them for informational purposes. Now we can delete those, and we have our input mapping context added to Kicks player controller. And we can actually get those input actions. IA look is our only one. but we can get that here and we can test to see if it's working. We can print a string on triggered. And I can take the action value and just plug it straight in. And we'll get a conversion node from vector2d to string. And we can see if we press play and click and move our mouse, we can move left and right and see that we get a value for the x, the y stays at 0, but if we move up and down, then the y has a non-zero value, and we can move all around in the circles and change those values. So we can see that this is actually working, but we can actually remove that print string and go back to bpkicks and search for IA look here, and we also have access to the input action here. We can even print a string here, printing the value of action value. I'm going to change it to red or orange and play test and move my mouse. And notice that we also have access to that input action on the pawn itself. Here in the character blueprint, we can implement functionality here as well. So that's good to know. But we're going to implement our movement functionality here on the player controller class. And for looking behavior, this is actually kind of convenient because a player controller has its own rotation. And as we learned in our previous game project, we can just designate certain components on our pawn to follow the player controller. For instance, our spring arm component, this can be set to follow our player controller's rotation. Under camera settings, if we scroll slightly down, there's a checkbox that says use pawn control rotation. So if we rotate our controller, our spring arm will follow it if we check this checkbox. Before we check it, let's implement rotating our controller as a response to our IA look input action. How do we do that? Well, our player controller has functions for adding input to change its rotation. We have add pitch input. Let's get that function. And we have add yaw input. Let's get that function. We don't really care about the roll. We don't want to twist our player controller. We just want to rotate it up and down like it's nodding yes, and rotate it side to side like it's shaking its head no. If we call both of these on triggered, then we can pass in a value to rotate in the pitch and yaw directions. And remember, our action value can be broken. We can use a break vector2d to access the x and y. And the x is what I'd like to use for the yaw, and the y is what I'd like to use for the pitch. Now my wires are crossing, so what I'll actually do is swap them around like this. And now we're adding pitch and yaw input in response to IA look. Let's just go back and start our Pi session and engage and go ahead and rotate. Now I can rotate left and right, but I cannot rotate up and down. And another thing that I'm noticing is my actual character mesh is rotating along with my mouse as well. And I don't want that. I want my spring arm to rotate only and not my mesh. So let's go back and take a look at bpkicks. Now our character mesh itself is actually rotating along with the capsule component, which is following that controller. And this is because the character itself has a property called use controller rotation yaw. And that's set to true by default. If we uncheck that and go back and try to rotate, we'll see that nothing rotates at all. And that's what I want. I don't want my character itself to follow my controller rotation. What I do want is my spring arm to follow my controller rotation. So with my spring arm selected, now I have a use pawn control rotation checkbox. I'm going to check that and go back and play test. And now I can rotate both in the X and the Y directions. Now, when I move my mouse up, I look down. And when I move my mouse down, I look up. That's actually inverted from the way that I prefer, and you may not prefer it that way either. When I move my mouse up, I want to look up. In other words, I need to negate the Y value for my input action, IA look. So I'm going to go to my IA look input action itself, and I'm going to add a modifier choosing the negate modifier. And I only need to negate the Y axis, so I can uncheck the checkboxes for X and Z and go back and play test, and I can see that moving my mouse down looks down, moving it up looks up, and I can rotate as I wish. All right, this is looking and feeling a lot better, but I still can't move my character around. Pressing the WASD keys does nothing, so we still have some work to do, but we're getting there one step at a time. Excellent job, and I'll see you in the next video. Welcome back. Now our Kix character is starting to come along. We can rotate the camera around Kix, but we can't move our character. So we need an input action for moving the character around. And I'd like to use WASD movement, at least at first, to move the character. So we need an input action. Let's go ahead and create one. We'll go to Blueprints, Input, Input Actions, right-click and go to Input and select Input Action. And this will be IA Move. And much like IA Look, IA Move can be a 2D input action. So we'll make this Axis 2D, Vector 2D. And we need to add this to our input mapping context, of course. So we'll click plus to add a new mapping and select our new input action, IA Move. And we're going to want WASD movement here. So I can click on the keyboard and press W. That gives us the W key. We'll need to click plus to add more inputs. For the second one, I'll set this to A. We'll click plus, and for the third, we'll set this to S. And plus one more time and set the fourth one to D. Now, as we know, our input action has two axes, X and Y. And I would like left and right movement to be fed in to the X axis. And that's going to be A and D, A being left and D being right. And when moving left, I want that X axis value to be negated. So we're going to add a modifier to A and choose negate for that modifier and expand the dropdown and keep X selected and uncheck Y and Z. So even though all of our inputs feed into the X axis so far, A and D are the inputs we actually want fed into the X axis, and A will have its input value negated. W and S, however, should go into the Y axis, so we need to swizzle them. So for W, we're going to add a modifier and choose swizzle input axis values. We can expand it and make sure that Y is the first letter in the order. The others don't matter because we only want this input fed into one axis, the Y axis. And single keyboard keys and buttons only have one axis worth of data. So W now has its data passed into the Y. Now we need to do that with S as well. So we'll add a modifier to S, choosing swizzle input axis values. We see that Y is the first letter, which is perfect. But we also want to negate this value. So we're going to add a second modifier, and this one will be negate. And for the negate on this one, we want to negate the Y-axis so that when we press S, our input is scaled by -1. So we'll leave Y checked and uncheck X and Z. So S is the only input that has two modifiers. It needs to be swizzled because we're using the Y-axis, and it needs to be negated because we're moving backward. So now that we have WASD inputs set up in the input mapping context, we can now implement IA Move on our player controller. So let's go back to our player controller and implement IA Move. We can do so by right-clicking, searching for IA Move, and getting that Enhance Input Action event. And here we have the action value. And just to see that those values are what we expect, we can use a print string node, and we can take that action value 2D vector and pass it straight in to convert to a string. And let's just play test and see what happens when we press those keys. So I'm going to press W first, and we get 0 in the X and 1 in the Y as expected. I'm going to press A. We get -1 in the X and 0 in the Y. I'm going to press S. We get -1 in the Y and 0 in the X. And I'm going to press D, and we'll have +1 in the X and 0 for the Y. And that's exactly what I expected. So now that we've verified that our input action is set up correctly, we can now move the character. Now we have a character blueprint based on the character class, right? And the character class automatically has a character movement component. And the character movement component is designed to handle movement for the character. We don't have to set the character's location directly or add forces or anything like that. We add movement input to the character movement component. And the character movement component handles moving the character for us. And it has a number of parameters that allow us to customize that type of movement. It'll slowly ramp up the character's movement from a speed of 0 to a max speed. It takes care of applying gravity to our character, and it has a number of other parameters on it. All we need to do is pass an input vector to the character movement component to tell it that we're moving and to tell it what direction we're moving in. And since we're handling movement on the player controller, we need to access the character movement component on the character. Now, whenever we're in the player controller class, we can always access the pawn that our controller has possessed. We can do that by right-clicking and searching for the function getControlledPawn. This returns us a pawn object reference. Now, our pawn is actually a character, but we don't need to cast to the character class to access the movement component because the pawn class has a function getMovementComponent. If we call that, now we have a pawn movement component object reference. And the class pawn movement component is the parent class to character movement component. So the pawn class has a way to get its movement component if it has one, and our character is a pawn that has one. So this returns the movement component in the form of a pawn movement component. And the pawn movement component class has functions for adding movement input, and those functions are inherited by child classes that derive from pawn movement component. So we can add input to our movement component without casting it to a character movement component. So if we access the movement component, we can get functions like add input vector. This is how we add input to our movement component. It requires a world vector input parameter that'll tell us the direction and an optional Boolean. We don't need to worry about that for now. So let's see what happens when we add an input vector. I can remove my print string, and we can connect this add input vector function call. Now, we'll figure out what to do with this input action value in just a moment, but for now, I'm just going to add an input vector in the world X direction. I'm going to hard code the vector 1, 0, 0. This is a unit vector pointing in the X direction, right? Let's see what happens if we go and press play, and we press any of the WASD keys. I'm going to press W, and I'm moving forward. But this is a problem. If I press S, I also move forward. If I press D or A, all of these move me forward. So we're just hard coding that X world direction in to add movement input. But as you can see, we smoothly start moving forward according to that input vector that we pass in to add input vector. So this is a way that we can move our character We just need to figure out what direction we actually want to move in. And the direction that I want to move in is a direction determined by my controller. Because as I move my mouse, I'm moving my controller. I'm rotating it. And I want to get that control rotation, the rotation of my controller, and move forward in that direction. So if I'm looking at my character from this angle and I press W, I want my character to turn and start walking back that way. And if I'm looking at it from this side, I want my character to turn to the right and start walking that way. I always want to move in the direction that my camera is looking in. So I need to get the controller's rotation to do that. So back to Kik's player controller, I'm going to figure out that direction from my controller's rotation. Now, the controller itself has a function to get its own rotation, and it's called getControlRotation. If we call that, we get a rotator. And we want a vector corresponding to this rotation. And we know that we can get a vector from a rotator with the function getForwardVector. GetForwardVector requires a rotation and returns a vector pointing in the forward direction of that control rotation. That's the direction we're looking in when we're moving our mouse around and rotating that controller. So getForwardVector gives me that direction that I want. And this is perfect when I want to move forward. In other words, when I'm pressing the W key. So I'm going to get my action value, but rather than getting it here and using breakVector2D and getting the X value from that, instead I'm going to get my action value as a standalone node by searching for IAMove and getting the enhanced action values IAMove Blueprint Pure node. So I don't need to break this one and drag my wires across. I'm going to break this one. Now, rather than dragging off and using breakVector2D, I can simply split my struct pin by right-clicking on it and choosing Split Struct Pin, and that gives me one less node. And I can get my Y value. Remember, W and S are being fed into the Y-axis of my action value. And Y is going to be 0 if we're not pressing the key. It'll be 1 if we're pressing W, and it'll be -1 if we're pressing S. So if I simply take this forward vector and multiply this by the Y value, then it'll be pointing in the opposite direction when pressing S. So if I'm looking forward and I press S, this vector will be pointing backward. So I can right-click, convert this to a float, and pass in Y for it. And this can be the vector we pass into addInputVector. I'm going to go ahead and pass that right in. And now we can go and play, and I can engage and press W and move forward. I can press S and move backward. And the cool thing is I can rotate my controller to some other angle and press W, and we're moving that way. So I can move around with W and S, and I'm going in the direction I'm looking in. And that's the type of movement that I want for this character. But we can only move forward and backward. We can't move left and right. So we need to handle that as well. And what we can do is the same thing that we're doing here, except we can get the right vector of our control rotation. So we're going to get the control rotation. I'm going to duplicate that node. And instead of the forward vector, I'm going to get right vector this time and multiply this. But I'm not going to multiply by Y. I'm going to multiply by X on our input action. So I'm going to duplicate these nodes and simply change the float that I'm multiplying by to the X value on IAMove. And we're going to call addInputVector a second time, passing in this vector. So calling addInputVector twice is going to tell the movement component, I want to move in this direction, but I also want to move in this direction, and the movement component is capable of combining those two input vectors, but still managing the speed of the character according to the parameters on the movement component that determine how fast the character should move. Now, add input vector does require a pawn movement component object reference. So I do need to get controlled pawn and get movement component from it. So I'm going to duplicate those nodes over here and pass those into the target. And now we should be able to move left and right. And playtesting, we'll use A to move left, D to move right, and now we have WASD movement. And we can move our mouse to look around and control which direction we're going in with both mouse and keyboard. Now, yes, I know the character is just standing idle. It's completely frozen, and we need to change the animation poses based on movement. We'll do that soon enough. For now, it's enough to just program movement, and we have that. Now, I'd like to use the console command, show collision. So pressing the tilde key and typing in show collision and hitting enter, now we can see those collision volumes associated with our mesh. We have the capsule, we can see that, and we have a bunch of smaller capsules. Those are those physics bodies on the physics asset. Now notice as I'm orienting my controller and rotating it around, not only is my character's mesh staying still, but so is that capsule, which is the root component. But there are parameters that allow us to follow the control rotation if we want to. We've seen one of those. If we go back to BP Kicks, select BP Kicks self in the components panel, so we're looking at the actor as a whole, we can search for control, and under pawn, we have variables for inheriting the controller's pitch, yaw, and roll. And then we have the character movement component variable, use controller desired rotation. So before we wrap up, we're just going to briefly look at what these do. First, let's look at the pawn variables, use controller rotation, pitch, yaw, and roll. First, I'm going to check use controller rotation yaw, compile, and press play, and engage, and we'll see immediately that our character's mesh rotates. But if we enter show collision, we'll see that the capsule rotates as well. So it's actually the capsule that's rotating along with the controller, because our pawn's use controller rotation yaw is selected, and this just designates our root component to follow the control rotation. And we have rotation pitch and roll as well. Now we're not really changing the roll, but we are changing the pitch of our controller. So if we check that checkbox, let's see what happens when we change our controller's pitch. Take a look at that. It kind of looks like we're flying, right? It's not a good look. It doesn't look right. So use controller rotation pitch in our case is not something that we would want. In fact, I really don't want to use controller rotation yaw either. So I'm going to go ahead and uncheck both of those. Now, the character movement component has a separate Boolean variable called use controller desired rotation. And the pop-up says, if true, smoothly rotate the character toward the controller's desired rotation using rotation rate as the rate of rotation change. Well, we don't see rotation rate here because we filtered the details panel with control. But if I search for rotation instead, we can see that rotation rate down here along with use controller desired rotation. So I can check use controller desired rotation, and I see the rotation rate, and it has 0, 0, and 360 in that final value there. Let's see what happens if we go ahead and start moving. If I rotate my controller very quickly, we'll see that our character is rotating to use that controller rotation, but it's not doing so very quickly. It's taking a second to rotate in that direction, and that's according to that rotation rate. We're basically smoothly interpolating towards that control rotation using the rotation rate. That's what use controller desired rotation does. There's another option orient rotation to movement. If we disable use controller desired rotation and instead check the checkbox for orient rotation to movement, now we're going to orient according to how we're moving. So for instance, if I move to the right, my mesh turns to the right. If I move to the left, my mesh turns to the left. So we're always going to rotate in the direction that we're moving. And that rotation happens according to that rotation rate, which we can change. If 360 is too slow, we can change it. Let's change it to 720 and go back and move around. And we'll see that that rotation rate is higher and we're rotating faster. So these are properties on the character movement component, as we can see by the category here, character movement. And we can prove that by selecting the character movement component, and we'll still see those properties, rotation rate and orient rotation to movement. So now we know what those two Booleans do. And it's important to understand what these do because we may have conflicting settings. We may have orient rotation to movement set to true, but if we go back onto the pawn and check use controller rotation yaw, well, now we have two conflicting settings. One setting on the character movement component says we should orient rotation to movement, and another setting says we should use our controller's rotation yaw. Now, if we go back and press play, we're going to use the controller's rotation yaw because that's something that sets the pawn's rotation every frame. And if we try to move, now we're fighting ourselves. We're trying to orient rotation to movement, but we're also trying to orient rotation to the controller's yaw as well. And so we get this jitter because the two settings are conflicting. And that's not what we want. We never want incompatible settings. So it's important to understand the settings so that we don't have two settings set that are fighting against each other. So if we want to use the controller's rotation yaw, we can't orient rotation to movement. I want to orient rotation to movement, so I'm going to uncheck use controller rotation yaw. And now I have movement that is closer to what I want. I can run in a particular direction, and my character is going to orient in that direction. I just need my character to actually play a running animation when my character is actually running. And we'll get to that soon. For now, we're doing a great job. Now, the feet are not quite planted on the floor, and I can fix that by going to BP Kicks, selecting my character mesh, and moving it down ever so slightly. I may want to disable snapping for this, and just move it down a little bit and play test and see what that looks like. It's not quite low enough, so we'll move it down a little more. And now it looks like it's actually on the floor. So sometimes this can be an iterative process to get it just right. I see that -73 is about right, and that plants my character right there on the ground. Excellent. Great job, and I'll see you in the next video. Welcome back. Before we move on, it's important to keep our blueprints clean and tidy, and this is something we should do at every stage of development. So I'd like to clean up our player controller nodes so that everything looks nice and clean, and the more complex our project gets, the easier it will be to maintain this way. So we'll start with begin play. We'll add our mapping context in a function designated to handle that. So I'm going to right-click, collapse to function, and we'll call this add mapping context. And we can keep these in categories. Add mapping context is related to input. So with add mapping context selected under functions, I can go to my details panel and enter a new category. I'm going to call this kicks input and compile that. And the next function we make will also be related to input. I'd like these nodes to be encapsulated in their own function. And this is for adding the yaw and pitch input for IA look. I'm going to collapse this to a function and call this add look input. And this can take that in action value. It's a vector 2D. Instead of invec, we're going to call it action value. And add look input can also go into that category kicks input. So it'll be right there in that category. And already our blueprint is looking better. Next, we have IA move. Now, we're doing a couple things here in IA move. First, we're getting the forward vector from our control rotation and scaling it by our action value's Y axis. So really, this is getting our forward input action. So I'd like to collapse these to a pure node. So let's collapse to function, and I'm going to call this get forward input. And I'd like this to be a pure function, so I'm going to check pure, and now we have get forward input. Now, the names here should be descriptive of what we're doing. Get forward input is pretty good. It doesn't quite tell us that we're getting the forward vector of our control rotation, but as long as we understand that, that's fine. And we can set this to have the same category kicks input as well. Now, we're getting the controlled pawn and getting the movement component, and you might be wondering, is this more expensive than, let's say, caching off this value, storing it in a variable on the player controller? And it's slightly more performant to do that because calling get controlled pawn is a function call. There's an indirection associated with that in the flow of execution. And once the pawn is accessed, another function is called to get the movement component. That's another indirection in the flow of execution. So technically speaking, it's slightly more performant if we were to store this movement component as a variable. And we can do that in begin play if we'd like. Here's what we would do. We would copy these nodes, come up here into begin play, paste them here, and take that movement component and promote it to a variable. We can call this movement component, and we can store that. And instead of calling these two function nodes whenever we need the movement component, we can now access it via the member variable movement component. And I can collapse this to a function. I'm going to call this store essential variables. And this doesn't have to come after add mapping context. We can have it before or after. So I'm going to put it right there before add mapping context. And now we have a movement component variable, and we don't have to make these two function calls. We can simply get the movement component variable and pass that in instead. And it's a good idea to make sure that that variable is valid before we use it. So I'm going to duplicate it, and for this duplicate, I'm going to convert to a validated get. And we'll only perform these actions if is valid is the case. If it's not valid, we won't continue. So now we have add input vector for the forward input. I'd like to do the same for the right input. So I'm going to collapse these nodes to a function and call this get right input. And this can be converted to pure and also given the category kicks input. And like we did over here, we don't need to call two functions. We can simply access one variable, our movement component variable. So now these nodes look a lot better. And all of this is doing one thing. We're adding movement input. So we can collapse these all to a function, and we'll call this add movement input. And we could pass that action value in as an input, but as you could see, we didn't need to because our pure functions just access those via the get IA move node. And if we really wanted to, we could come back to add look input and eliminate that action value as an input altogether if we just wanted to get the IA look input action value right here. So there's always more than one way to do things. It doesn't really matter in this case. We don't have to eliminate the action value and get IA look here and replace this. But if you wanted to, you could. And just to show you that process, I would just replace X and Y here, eliminate the break node, and then select Add Look Input and eliminate the input by pressing the X. Now it's gone, but if we go to our event graph, our Add Look Input has a wire going in where there's no longer an input. And to fix that, we right-click on it and we refresh the nodes, refresh nodes, and now we don't have an input. So I didn't have to make that change. You could just pass it in as an input. Either way is completely fine. There's no significant performance difference between the two ways. So now our player controller is looking much better, and it makes sense when we look at it. Input action IA_Look calls a function called add_look_input. We don't have to worry about what it does, and if we do need to know what it does, we can just double-click to go inside of it, and we see that we're calling two functions using the input action values. And these are functions on the player controller class. And if you really wanted to see what these functions did, well, then you'd be going into C++ code because these are C++ functions. So now our player controller is looking better. We can see the nodes required for movement. Things are looking great. We're ready to continue, and I'll see you in the next video. Welcome back. Now, we have movement, which is great, and I know you're dying to get some animations on Kix, and we will very soon, but before we do that, we're going to implement jumping. Jumping is essential, and it's a relatively simple thing to implement. So we're going to do that really quickly in this video. For jumping, we just need a simple input action. So we're going to go to our input actions folder, right-click, go to input, select input action, and this will be called IA_Jump. An IA_Jump can be a digital bool. We just need to know on or off. Are we jumping or are we not jumping? So now that we have the input action, we can go to the IMC Kix movement input mapping context and add a new mapping and scroll all the way down to the bottom and select IA_Jump and find it, open it up. And this is going to be tied to the spacebar. So I'm going to click on the keyboard, press the spacebar, and now we have the spacebar. And we're going to implement this. And we could implement it right here in the player controller by right-clicking, choosing IA_Jump. And I'd like to jump when we press the spacebar, not every frame while it's being held down. So I'm going to use started. Now our pawn is a character, and the character class actually has a function for jumping. If we go back to BP Kix and search for jump, we'll see that there's a function called jump. And it says target is character, meaning that this is a function on the character class. And this handles jumping for us. Now we have two options here. We can simply implement IA_Jump on the character class right here. And we can hook up started to a function call to jump. This is a very simple and straightforward way to do it. BP Kix implements its own jump. We can go ahead and test this even by pressing play, pressing the spacebar, and we can jump. And that's great. But we wanted to handle all movement on the player controller. So rather than doing this in BP Kix, I'd like to keep that movement code out of Kix and in the player controller. And to do that, I need to get my controlled pawn with get controlled pawn. But jump is on the character class, not the pawn class. We've seen this issue before where we needed to access something on a child class, but we only have that data in the form of the parent class. This is what casting is for. So if I cast to character, now I can access that function, jump, because the cast gives us our controlled pawn cast to the character data type. Now, casting is the type of operation that can affect performance in various ways, and we'll talk about those a little bit later in this section. In general, if we cast, we want to try to keep casting to a minimum, and if we hook this up to started, we'll be casting every time we trigger this input action, which will work, and that's fine, but if we can avoid casting multiple times in a row unnecessarily, that would be ideal. But just as is, we can go back and play test, and we'll see that pressing the space key does work. We can jump, but we're casting every time unnecessarily. So in order to avoid multiple casts to the same data type, we can simply cache the variable. We can perform the cast once and begin play, and then we can access the character every time we need it. So I can go back up to begin play, and we have a function for storing our essential variables. We can do the cast in here. We can get our controlled pawn, and we can cast it. So I'm going to get controlled pawn, cast to character, and once we've cast to the character class, I'm going to take that character and I'm going to promote it to a variable, not local, and this variable can simply be called controlled character. It's the controlled pawn cast to the character class. We'll go ahead and hook this up, and now we have a controlled character variable stored on begin play. Yes, we're performing a cast once, but we're not performing it every time we try to jump. Now, as I mentioned, we'll talk more in future videos about what casting is doing from a performance standpoint, especially when it comes to memory. But for now, we've made this optimization where we don't have to cast multiple times. So back to our event graph, we can go back down, and instead of casting our controlled pawn every time, we can simply get our controlled character and call jump on our controlled character. And it's a good idea to make sure our controlled character is valid. So I'm going to convert this to a validated get and hook that up to started so that we only call jump if our controlled character is valid. And I can collapse IA jump, and now we have our jump functionality. And I'm going to take my controlled character variable and just give it its own category. I'm going to call it essential variables. And I can even take my movement component and change its category to essential variables, and now they're both there together. And it's always a good idea to play test. Let's just make sure jumping still works. It does, and we don't have to cast every time. Okay, so now we have looking input, movement input, and jumping input. We're almost ready to dive into animations, but before we do that, I'd just like to do one more thing, and that's implementing our input using a console controller, like an Xbox controller or a PlayStation controller. I'd like to briefly show just how easy it is to do that, and we'll do that next. I'll see you soon. Welcome back. Now, we have movement with mouse and keyboard, but it's actually pretty easy to add movement for console controllers. Now, for this video, you're going to need a console controller that you can hook up to your computer in order to playtest this. I have an Xbox controller that I can hook up via a USB cable. And if you have an Xbox controller or a PlayStation controller, or just some generic controller that has a USB cable, you can plug that into your computer. So I'm going to go ahead and plug in the USB cable for this controller now. And you'll see that as soon as I do that, we get an input device has been connected message. We can check the checkbox to not show it again. I'm just going to leave it there. But now we know that Unreal Engine has detected an input device. So now that we have an input device connected, we can playtest controller input. Now, the first thing I'm going to do is go to my input mapping context and add controller input to my input actions. We'll start with IA look. Now, IA look uses mouse XY 2D axis as the input. And IA look is indeed a 2D input action. We can verify that by opening IA look and seeing that its value type is axis 2D. Well, I'm going to add another input to IA look by clicking the plus right next to the IA look dropdown. And now I have another input. And for this one, I want to use my controller's right thumbstick. So I can take my drop down and expand gamepad. And we have the thumbsticks for gamepads here. I want the right thumbstick. And notice that we have X and Y axes as well as a 2D axis option for both the left and the right thumbsticks. I'm going to choose gamepad right thumbstick 2D axis. And now this input is connected to IA look, which is already implemented. Now we can play test this. As soon as I press play and click to engage, well, I notice a drift. But as long as I'm actually moving my thumbstick, it looks fine. I can move left and right, up and down, and I'm moving my camera. But as soon as I stop, we have a drift. And that's because there's a tiny amount of input that is being fed in, and we don't want that tiny amount of input. This is due to the inaccuracy of floating point values. So if I go back to IMC Kicks Movement, I can add a modifier that will prevent any input if that input value is close to 0, according to a certain threshold. For input, we call this a dead zone. There's a zone on our controller where if we're not pressing enough, it's considered to be an input of 0. Let's add that dead zone. Now we can add it here on the IMC, or we can add it for the input action itself. I'm going to add it right here. So I'm going to add a new modifier, and from the dropdown, I'm going to select dead zone. Now there are parameters for the dead zone, such as the threshold for lower and upper, as well as the type. We want to leave that at radial because we're using a 2D axis. Radial is for the thumbstick's 2D axis as a whole, whereas axial would be for one dimension if we were only using the X or just the Y, for instance. Now I'm going to leave the dead zone's parameters at their defaults and just go back and play test again. And as we can see, we have no drift. I can take my controller, move to the left, move to the right, up and down, and everything is working. Now, when I move my controller up, I'm looking down. And when I move it down, I'm looking up. That's not what I want. I want that Y-axis inverted. So just like we did with our IA look input action, we applied a modifier to IA look itself. We're going to want to negate our thumbstick input. So essentially, the IA look is already negated. That results in the behavior we get with our thumbstick and our mouse. But for the thumbstick, it's not what we want. So we need to go back to our input mapping context and negate it here for our thumbstick specifically. So I can add another modifier and choose from the dropdown negate, and we can negate the Y. We don't want to negate the X or Z. And now if we go back and play test, when I move my thumbstick up, I look up. When I move it down, I look down. So our right thumbstick controls our camera, which is great, but we can't move around with our left thumbstick, which is the behavior that I want. So let's add the left thumbstick to our movement as well. So we're going to go back to IMC Kicks Movement. I'm done with IA look. I'm going to collapse that. And now for IA move, I want to add the gamepad left thumbstick. So I'm going to click plus. That automatically expands IA look again, which is a little annoying, but I'm going to collapse it back and collapse WASD. And we have our next input. I'm going to choose gamepad. And this time we're going to use the left thumbstick 2D axis. So with just that change, let's go back and press play. And let's move our left thumbstick. And as we can see, it's moving our character. But again, if I release, we still have that drift. So just like with our right thumbstick, we need a dead zone. So on the gamepad left thumbstick 2D axis, we're going to add a modifier and choose dead zone. And I'm going to leave the dead zone parameters as is and play test. And once again, we can move our left thumbstick, but when we stop moving, our character stops moving because we have a dead zone. So dead zones are very important when it comes to controller input. Now, something I'd like you to notice, thumbsticks are pressure sensitive, unlike WASD keys. So both of our thumbsticks, left and right, are pressure sensitive. If I barely push my thumbstick just past that threshold for the dead zone, we get a small value for the input, less than 1. And we can rotate our camera very slowly if we want to. Or we can rotate fast by pressing the thumbstick all the way. And the same goes for movement. We can barely press that thumbstick and we can move in our input vector direction a very small amount, or we can press the thumbstick all the way and get full-on movement. Pressing it all the way is the movement we get when we press the WASD keys. But we cannot get that input value that's smaller, less than 1, with a keyboard key. A thumbstick, being pressure sensitive, allows us to get those smooth values, and that can be very desirable in a game where you might want to move slowly for any reason. And we'll see how to take advantage of this pressure sensitivity when we implement movement animations, allowing us to blend between walking and running. And we'll get to that soon. So we now have movement input for looking and for moving, but not yet for jumping. So the last thing we need to do is add gamepad input for our IA jump input action. So I'm going to click plus next to IA jump, and from the dropdown, we'll go to gamepad, and what we want is our gamepad face buttons. On a gamepad, these are the face buttons. For Xbox, they're X, Y, A, and B. Of course, they're different for PlayStation, and they may be different depending on the generic controller that you have, but I would like to use the bottom gamepad face button. So that's going to be gamepad face button bottom. And if I were to click on this button and simply press one of these buttons, we can assign that button that way as well. So the shortcut works when doing that as well. So now that I have gamepad face button bottom tied to my jump, I should be able to jump with my controller. So pressing my A button, in the case of my controller, I see that I get jumping. So now I have movement, looking around, and jumping, and I can use all three of them together to get a nice, natural feeling character locomotion system. And it feels and looks great. It's a lot easier for me personally to control a character with a console controller. And even if you're developing a game that's designed for PC, you may want to implement controller input anyway, and just have that as an option for players who want to play your game if you'd like to add that extra level of control. And then later, let's say you get a deal and your game is released to one of the consoles, well, you've already implemented console controller input, and that's one important step that you've already taken care of, and you don't have to do it just for releasing to a new platform. So that's console controller input, and as you can see, because we've already done the hard work with keyboard and mouse input, adding those controller inputs to our input mapping context was relatively simple. We didn't have to go into our player controller and change how we use that input, which is nice. Excellent job, and I'll see you in the next video. Welcome back. Now we have movement, which is great, but Kix is just standing in this T pose. It's actually more like an A pose because the arms are not quite straight out, but regardless, Kix is not moving. Now, we do have animation assets in this project. That's partially why we started out with this game project, and in the assets folder, if we go to Kix, we can open the animations folder and see all the assets that we have. Now, rather than standing in an A pose, I'd rather have Kix stand in an idle pose. Notice that my animation assets are all prefixed with A, and their asset type is animation sequence. If I double-click A Kix idle, I can see what A Kix idle looks like, and it's basically Kix standing there and breathing, and this animation is just looping over and over again. And if we go to asset details, we'll see that this property called loop is set to true, which designates this animation to simply loop when it's played. Now we can see what this looks like on our Kix character. If we go to BP Kix into viewport, we can see that there's Kix with the A pose, but if I select the mesh and search for the animation section here, animation mode is a property with a dropdown, and by default it's set to use animation blueprint. We can change it to use animation asset, and now we have an anim to play property. This is an animation sequence, and we can choose an animation to play. I'm going to choose A Kix idle. And we have looping and playing variables. We can uncheck looping, and we'll only see it play once. Even though our animation asset has looping on it, this particular anim to play property depends on looping being checked if we want it to loop. We can also uncheck playing, so we won't even see it there. And if we check playing, we'll see that animation playing. And this does play in the game. If we play the game, we'll see that there's Kix, and Kix looks a lot cooler with an animation playing like this, so this is great. Now, the problem with this is that Kix is just in the idle pose, and it doesn't matter if we're moving, Kix is just in that idle pose. If we jump, if we look around, it doesn't change that idle pose because it's playing a single animation asset. What we want to do is change that pose. We want to change the animation that we're playing. And this often involves blending between animations. If I start running or walking, I want Kix to smoothly blend into a running or walking animation. And for that, we have a new type of asset that we're going to create called an animation blueprint. So let's get that created. I'm going to first close all my tabs at the top. I'm done with everything that we had open there. I'm going to save all my progress, and we're going to create an animation blueprint. Now, I'd like to go to my blueprints folder and find Kix and put my animation blueprint here next to my BP Kix character blueprint. In some projects, you'll see the animation blueprint in the assets folder right there with the other animations. You could put it there as well. I personally like to keep my animation blueprint next to the character blueprint, at least for a simple project where I have one animation blueprint used by one character. So we're going to create it here. And to do so, we right-click, go to Animation, and select Animation Blueprint. As soon as I choose that, I'm prompted with two choices: use a specific skeleton or create a template animation blueprint that is not specific to a skeleton. That's a little bit more advanced. We're going to choose specific skeleton, and we only have one skeleton asset in our project to choose from. That's SkelKix. We're going to choose that and click on Create. And we typically prefix our animation blueprints with ABP, short for Animation Blueprint. I'm going to call this ABP Kix. And we'll go ahead and double-click it to open it up. And here is the Kix Animation Blueprint. Now, notice to the top left, we have a viewport. I can hold Alt and left-click and drag to rotate around the character, and right-click and drag to zoom in and out. I can resize the windows if I want to see it bigger. And this viewport shows us an example of what Kix will look like based on the poses that we've configured. An animation blueprint also has an event graph and an anim graph. The event graph is a lot like event graphs in actor blueprints, where we can script out logic, and this is typically where we update variables that we're going to use to drive our animations, to select poses. And those poses are selected in the anim graph, where we have an output pose node. Now, it has an input called result. And if we hover over it, it says animation pose. And here we can choose animations to play for our character. And to the bottom right, we have an asset browser with animations. This is open by default. If you accidentally close it with the X, you can go back up to Window and find Asset Browser and get it back. And by default, we see a bunch of animation assets that use the skeleton that we chose for this animation blueprint. If we had animation assets that use a different skeleton, we would not see them here. It's filtered out. And we can bring in an asset. I'm going to choose A-Kicks Grab and drag it in and release. And we get a node that says Sequence Player. This will play an animation sequence, specifically the animation sequence that I dragged in. And in the Details panel at the top right, we can see that that sequence is a property here. We can change what that sequence is from the dropdown by selecting a different animation sequence here. So this node has an animation sequence, and notice its output pin has a little human icon. It says animation pose, and we can connect that to our output pose. Now look at our viewport. Kicks is still in the A pose, right? But if we compile our animation blueprint, now Kicks is in that grab pose. We played the grab animation, and we only played it once. Now, we could loop this animation by selecting the Sequence Player node, going to the Details panel, and checking Loop Animation. And if we compile that, we'll see in the viewport that we're looping the animation. So this animation blueprint so far is quite simple. It just plays a single animation on looping, but we can apply this animation blueprint to our Kicks character by opening its character blueprint, BP Kicks, selecting our mesh, and going to our animation section and changing animation mode from Use Animation Asset to Use Animation Blueprint. And here we can select the anim class from the dropdown. Now, it shows a lot of classes built into the engine. We just want ours, ABP Kicks. Now, if I go to my viewport, notice that Kicks is playing that grab animation on repeat. And that's because it's actually using the animation blueprint now. So if we go and press play, we're playing that grab animation. Now, this is not ideal, right? We want to run when we're moving, not play a grab animation, but this is just an example of how our animation blueprint is driving the pose of the skeletal mesh component that has assigned it in its anim class property. And animation blueprints are great for changing the pose based on data. And in order to have data to use to decide which pose to play, we update that data in the event graph. We have an event here called Blueprint Update Animation. It even has a delta time, and this is much like tick in actor blueprints. It's called every frame. So we can see if this is working by adding a print string node to it. And notice there's a grayed out node try get pawn owner. This is a function on the animation blueprint that returns the pawn that owns this animation blueprint. That's the pawn that has it assigned to its skeletal mesh component by selecting anim class. So if we take this try get pawn owner and drag it straight into print string, we'll get a get display name node, and we should be seeing that every frame. And if we go and press play, we'll see that that is BP Kicks 0. So ABP Kicks has access to the pawn that's using it. And this is what we can use to determine what animations to play by getting that pawn owner and getting properties from it, such as seeing if it's moving or not. We can see if it's moving by getting its movement components. We can use get movement component. And from movement component, we can just see how fast we're going. a movement component has a velocity variable. And if we get that velocity, we can see if that velocity is 0. The vector type has a vector is 0 function that returns true. I'm going to plug that straight into my print string so that I can see if my velocity is 0. If I go back and press play, I'll see true printed to the screen. But if I move, now it says false. If I stop, it says true. And if I move, it says false. So we know every frame if our character is moving based on its velocity. This is a very rudimentary way to know. So for a simple example of how we can change our pose, I'm going to store this Boolean in a variable on the animation blueprint. We can have variables on our animation blueprint. So I don't need my display name anymore. I'm going to highlight all these nodes and press Q to straighten them out. And I'm going to promote this Boolean to a variable called isVelocity0. I'm going to hook that up, and every frame we're updating our Boolean isVelocity0. Now I can use this in my anim graph. I can blend between two animation poses based on a Boolean. I can do that by right-clicking and using a special node designed for the anim graph called Blend Poses by Bool. If I get that Blend Poses by Bool, notice it has some inputs. It has a true pose, a false pose, and an active value, as well as blend times that specify how quickly we should blend into the true or false pose. The smaller the value, the quicker we blend. This is an amount of time to blend. So I can use isVelocity0. I can drag that straight in from my variables onto the active value. And if this isVelocity0 Boolean is true, then Blend Poses by Bool is going to output whatever pose we have here for our true pose. So I can bring in my kicks idle pose, and I can play that as my true pose. I'm going to go ahead and delete my kicks grab sequence player, and instead plug in my Blend Poses by Bool to the output pose. And I need a false pose too. So when isVelocity0 is false, that means I'm moving. So I'm going to play my run animation. I have an A kicks run forward animation right here. And by the way, if you want to see what these animations look like, you can hover over the animation here in the asset browser to see it moving, or you can double click on it to open that animation asset, or you can double click on the node itself, the sequence player node, to open that animation asset. Notice we got those print strings here in the viewport in the animation asset editor as well. That's because we haven't compiled our changes yet. As soon as we compile, now our updated changes are applied. And notice that our animation blueprint is running even when we're not playing the game, as indicated by these wire animations. We're showing our output pose evaluated based on these values. So let's go back into the world, press play, and we see we're in the idle animation. And if I run, I'm in the running animation. Now it's not looping, so that's a problem, but we've seen how to loop that animation pose by going back to our animation blueprint and selecting the sequence player node and checking the checkbox or loop animation. So I have it checked for run forward now, and if I go back and press play, now I'm looping that running animation. And if I stop running, now I'm in the idle animation. So Blend Poses by Bool is an example of how we can use a variable, some piece of data, to drive our animation pose. We're choosing between one or the other based on a Boolean value. And before wrapping up, just to show how the animation is blending, we're going to up the blend time to 0.5 for true blend time and 0.5 for false blend time. And we're going to start running. And notice that it takes a second to blend into that pose. Specifically, it takes half a second because our blend time is 0.5, and it takes half a second to blend out of that pose. And it's painfully apparent when these values are too high. I'm going to set them to 2 each and start running, and it takes a full 2 seconds to blend in and a full 2 seconds to blend back out. And we can see the effects of blending animations at play here. So it's a good idea to tweak those values until they look good. I'm going to leave them at 0.1. We're actually going to get rid of this blend poses by bool node and see a better way to blend our animations in this manner very soon. But now we can see that it's quite easy to drive our animation poses from data using our animation blueprint by harvesting data in the event graph, storing that data in a variable, and then using that variable to drive animations in the anim graph. We'll continue with this in the next video. Great job. I'll see you soon. Welcome back. Now, what we've implemented so far looks good. We're in the idle animation when we're not moving, and if we start moving, we're in the running animation. Now, this looks pretty good, except when I grab my console controller and apply that pressure-sensitive input. If I barely touch that left thumbstick, I'm moving very slowly, but I'm still playing that running animation at full speed, but I'd rather play something else, like a walking animation. In fact, we can see what a walking animation looks like by going back to our ABP Kicks animation blueprint, opening our anim graph, and changing our Kicks run forward animation by opening that details panel, finding the sequence, and finding a Kicks walk forward. Now we're going to play a walking animation instead. So if we press play, and I barely touch that thumbstick, now I'm walking and it looks normal, depending on the speed. But as soon as I push that thumbstick all the way, well, now I'm at a running speed and I'm still playing the walking animation, and that doesn't look right either. So what we need is a way to blend between our animations based on our speed. And ideally, we should blend between that walking animation and the running animation, and even that idle animation, depending on how fast we're going. Now, to blend between animations, we can use an asset called a blend space. We can do so by right-clicking in our content drawer. I'm right here in my Kicks folder under Blueprints, and going to Animation, and there's an asset called Blend Space. But if we go to Legacy, there's also a Blend Space 1D. For what we're doing, we could just use a Blend Space 1D, but I'm going to show you the regular Blend Space first. So let's choose Blend Space. When we choose Blend Space, we have to pick a skeleton, and as soon as we do, we can rename our asset. I'm going to call it BS for Blend Space, and we're going to call this Idle Walk Run. And as soon as I open it up, we see our blend space asset. Now, a blend space allows us to put a bunch of animations on a grid and blend between those animations based on values. We can place a series of animations left to right, and we have a horizontal axis as shown on the bottom going from 0 to 100. And this blend space will turn into a node that we can add to our anim graph in the animation blueprint and pass data into it. So if I search my asset browser, I now have BS Idle Walk Run here, along with my other animation assets. If I bring in BS Idle Walk Run, notice I have 2 float inputs. Both are called none. And this blend space outputs an animation pose that we can hook up to our output pose. Now, what are these inputs, both called none? Well, if we go back to our blend space, these are the axes on our grid. We have a horizontal axis, that's the first none, and a vertical axis, that's the second none. Now, none is a horrible name for axes. So what we can do is go up to our axis settings in Asset Details and expand these dropdowns. Our horizontal axis, called none, needs to be renamed. And I'd like to blend between idle, walk, and run animations based on a speed variable. So I'm going to rename my horizontal axis to speed. Now, as soon as I do that, I can go back to ABP Kicks and see that my BS idle walk run blend space has speed for its first input. And the second input is still called none, and we don't really need that one. That's why I said we could use a blend space 1D. A blend space 1D is the same thing, except instead of a grid, we have one dimension, a single line going from left to right, and we don't have a horizontal axis. But we can still use this blend space and simply not use that second axis. And if we go back to our blend space node in the anim graph and select it, in the details panel, we can take that none axis and hide that input pin. We don't need to use it. We can open this dropdown and uncheck expose as pin. And now our blend space only has a single node for speed. Now back to our blend space, we need to decide what values our horizontal axis should take. And then we need to bring in some animations that we can play when our speed variable passed in is a certain value. Now, if we go to BP Kicks and select the character movement component, under walking, we'll see that we have a max walk speed. It's set to 600 centimeters per second. By the time we reach 600, I want my character Kicks to be in the running animation. In fact, I want it to be in the running animation well before that. So what I'm going to do in my blend space is set the maximum value for my speed horizontal axis to 600. And now we can see that reflected at the bottom right. So we're going to drag in some animations here, and we're going to drag them all onto the bottom line where this vertical none axis is 0, because we're never going to pass in a value for none into our blend space node. So when my speed is 0, I want to be in the idle animation. So I'm going to drag in a kicks idle right here, and I want it to snap to that bottom corner. So I'm going to hold the shift key to snap it. If you hold the shift key down, we can snap to increments on the grid. I'm going to leave that there. Now, when I'm walking, I want to be in the walk animation, and I want to see what my walk speed will be when I'm at the perfect speed for my walk animation. So what I'm going to do is go to my ABP Kicks event graph and find that speed. Now, I'm only interested in the X, Y components of my velocity to calculate my speed. I don't care about the Z component, how fast I'm moving up and down. I just want the lateral speed. So I can take my velocity and type vector length, and we have vector length XY, which will only take into account the X and Y components of this vector. And I'd like to print the value of this vector length XY. So I'm going to use a print string node and hook that in and just see what that value is as I'm walking. And I'm going to use my pressure sensitive console controller as I'm walking so that I can see exactly how fast I need to be for this walk animation to look good. If I go too fast, I'm sliding. If I go too slow, my feet are also sliding, so I need to find that happy medium. So it looks like about 168 is the right speed for my walking animation. So I'm going to try that value on my blend space, about 168. So I'm going to get my walk forward animation, and as I'm dragging it around, I can see my X and Y values. I want to go to about 168, perhaps 170 here, but I want it down here at 0. So I'm going to drag all the way down and get my speed value at about 170 or so. And now I can see my Kicks character blend between these on my grid by holding down the Control key. And I can drag left and right and see what my animations look like for various values of speed. And at about 168, 170, I'm in the walking animation. And beyond 170, I want to blend into my run forward animation. as long as I'm playing that animation before I reach 600, I'm good. So I'm going to drag it in and snap it to right about the middle, 300 and 0 for the none axis. And if I hold Control, I can show what that looks like blending from walking into the running animation. So now we have this asset called a blend space, and we can use values that we pass into that node in the anim graph for speed to drive that pose. And that's what we're going to do. We're going to cache off our speed in a variable. But I'd like to clean this up a little bit. So we're going to do things a little differently here. For one, I don't want to call two functions just to get a value from our movement component. We're going to cache off some values, and we're going to do that at the beginning rather than every frame. And there's a function kind of like begin play for animation blueprints. It's called blueprint initialize animation. Here is where we can get our pawn owner, our character movement component, and so on, and we can cache those off. Now, what I'd like to do is get my pawn owner and cast it to a character. That way we have access to everything on the character class. So I'm going to cast to character and promote this to a variable, and we'll call this character. And as soon as we've done that, I can now get the movement component, and if I'm getting it straight from the character class, I can actually get character movement. And if I scroll down, there's a variable called character movement, which is of type character movement component. We can promote that to a variable, and I'm going to call this character movement. So now we have not only the character that owns this animation blueprint, we also have its character movement component. And I'm going to collapse this to a function called store essential variables. So now we have those variables stored, and we can access properties from them here in update animation. Now, I'm not going to use isVelocity0 anymore, so I'm going to go back to my event graph and simply delete where we're using it there. We're going to use the blend space now instead. And that means in the event graph, I don't need isVelocity0. I'm going to delete those nodes and delete isVelocity0. Instead, we're going to get our ground speed. So I'm going to get my character movement component, get velocity from that. That's a variable of type vector. And we're going to get the vector length xy, and we're going to promote this to a variable, and I'm going to call this ground speed. Now, as soon as we have ground speed hooked up to event blueprint update animation, we'll have this variable updated every frame as long as our character movement component is valid. And we can make sure of that by converting this to a validated get so that we only get this value if that character movement component is valid. So if this gets called before store essential variables successfully gets that character movement component, well, we won't try to access something that isn't valid yet. So now that we have our ground speed, we can go back to our anim graph and pass ground speed into our blend space and hook that up to our output pose. So now that we have a blend space being used instead of a sequence player, we're going to blend between our idle, walk, and run animations depending on what value is passed in to the speed input to this node. Let's see how that looks by pressing play. And I'm going to grab my console controller, and I'm first going to just run. I'm going to go full speed, and then I'm going to barely touch my left thumbstick. And as I'm barely pushing it, I can see that I'm in the walk animation, and as I push it harder, I'm going into the run animation, and we're blending. Now, if you don't like how it looks, you can always tweak your blend space, move those animations around, and get it looking just right, but this is looking pretty good. The only thing is I'm in the run animation while I'm going a little bit too slow, so I can move that run animation forward just a little bit and play test. And really, this is an iterative process. You might find yourself experimenting with it until you get it right. the most important thing is that that animation matches your speed at full speed. So as I'm running at full speed, 600 units, it's important that we don't get much sliding. And if there is sliding, you can do one of two things. You can speed up the animation, or you can slow down your character's movement speed by changing max walk speed. I'd like to speed up my run animation to accommodate for my running speed. So I'm going to take my kicks run forward animation. I'm going to double click on it, and I'm going to change its play rate here. Notice its rate scale is 1.5. So it's actually going faster than this original asset looked like. We can put it at 1 to see the original run animation speed. That's a little slow, so I'm going to set it to 1.65, and we're going to play test and run at full speed and just see how that looks. And I think that's looking better. All right, so we now have a blend space, and we're able to blend between walking and running animations, and things are looking great. And now that I'm walking, I'm seeing the feet go a little bit into the floor. So I would like to go to BP Kicks and raise that mesh just a little bit. We don't need to be quite so low. So I'm going to raise it a little. And we're going to check out how it looks. It's okay if we're a little bit above the ground, as long as we're not going too far into the ground. And I think that's looking great. So now that we have a blend space and we're walking and running and blending between the two, it's now time to implement jumping, and we're going to do that next. I'll see you soon. Welcome back. Now that we have a blend space to blend between walking and running animations, it's time to implement jumping. Now back in our animation blueprint, we see that in our event graph, we're updating our ground speed variable. And this can drive our blend space to blend between idle, walking, and running animations. But for jumping, we're going to need to do something a little bit different. Let's take a look at the animations we have for jumping. We actually have 3 main jump animations, not counting jump double, that's different. For regular jumping, we have jump start, jump mid, and jump end. I'm going to double click on jump start, and this is what it looks like. It's a beginning jumping animation. We also have a jump mid, which is more a falling animation. It's the middle of the jump animation, and it's a loop. And then we have a jump end, which is a landing animation. Now, the reason these 3 animations are separate and not one big jumping animation is because in our games, we may be in the air at varying times. If we're just on a flat surface and we jump and land, we can be sure that jumping will take the same amount of time, roughly every time we jump. But if we're up on a high ledge and we jump down, then we'll be in the air for longer, and we need to be playing that falling loop animation, jump mid, while we're falling. And we can't play that jump end animation until we actually hit the ground. So this is why we typically break jumping into 3 animations like this. So we need to know whether or not we're in the air. And that's going to require another variable. We can use a Boolean for whether or not our character is in the air. We can get that from our character movement component. If we take our character movement component and drag off of it, there's a function called isFalling. And this function, if we call it, returns a Boolean value. And we can get that value and store that in a variable here on the animation blueprint so that we can use it in our anim graph. Now, just to make sure things are tidy, we're going to move this variable updating business into a function. So I'm going to collapse it to a function and call this update animation variables. And that way, our event graph is going to look nice and clean, and we can do our business here in update animation variables. And here, the first thing I want to do is make sure the character movement component is valid, but I'm going to break this pin and move these nodes up and just use the character movement component from a get node here. And that way this can be separate and we can access the character movement component again after. So it's just a way to keep things tidy. I'm also going to add a reroute node here so that we can move this entire section around as a whole. And I'm going to comment this and say store ground speed. And just to make this nice and pretty, I'm going to give it a bluish color. I'm going to store that color here at the top. Click OK and check Show Bubble when zoomed. Now, I'm going to do several things, and I'd like to use a sequence node to keep them organized. So I'm going to use a sequence node here. The first thing we do will be to store the ground speed, and then next we're going to call is falling. So I'm going to use a duplicate of the character movement, get node, and call is falling. I'm going to highlight them, press Q to straighten them out, and I'm going to promote this return value to a variable, not a local variable, but a variable on the animation blueprint, and this will be called is falling, or we could call it is in air. That way it's a little more descriptive for what we're using it for. So we'll connect this to the sequence node. I'm going to double click the wire to give it a reroute node, highlight the reroute and is in air and press Q so they're exactly aligned. And I'm going to comment this part and say store is in air. We'll give it a color. I'm going to choose that same blue and check Show Bubble. So we now have two things we're doing in update animation variables. And we now have a Boolean for when we're in the air. This is all necessary so that when we go back to our anim graph, we now have a Boolean we can use in our anim graph. So how are we going to use it? Well, this is where a new concept comes into play, the concept of state machines. You see here in the anim graph, we can only plug in a single pose to our output pose, unless we're blending poses with some other node. You may have thought, well, maybe we can blend poses by bool, like this, and hook in is in air, and for false, we can plug in the BS idle walk run, but what do we pass in for true? The thing is, we need to blend between animations based on where we are in that jump cycle. As soon as we press the spacebar or the A button, we want to jump, but we want to play the beginning jump animation, that jump start, this one here, and then as soon as that animation has played, we want to move right into jump mid and play this falling animation, and then as soon as we hit the ground, we want to play jump end. And so things are going to get a little bit complicated if we blend poses using bools. What we can do instead is make a state machine. Here's how we do it. We right-click here in the anim graph, we search for state machine, and choose state machine. Now, this state machine is going to be called locomotion, and it's going to handle the locomotion for our character. Notice it has an output animation pose. We can plug it straight into our output pose here. But what is this pose? Well, that depends on what's going on inside of our state machine. If we double click it, we'll open it up, and we're here inside the locomotion state machine. And it's tabbed here at the top, and we can always go back to the anim graph by clicking here on anim graph. And now notice we have an anim graph and a locomotion tab, and we can go back and forth between the two. So locomotion is a state machine, and in state machines, we have states. A state can be added by right-clicking and selecting Add State. And we need a name for the state. This state is going to be called Idle Walk Run. And whatever we put in Idle Walk Run is what our locomotion state machine will return as the output pose if we're in this state. And by default, we can go straight to this state by dragging our entry node over to Idle Walk Run and connecting it with an arrow. So what pose is in Idle Walk Run? Well, we can double click it and go into it and determine what pose we get here. We can drag in individual animations and get sequence players and use that. Or we can use a blend space. And in our case, we're going to use a blend space. I'm going to drag it straight onto the result node so it connects right away. And I don't need that none axis. So like we did with my other blend space node, I'm going to find none and uncheck expose as pin. And we need to hook in a speed variable. That's going to be ground speed. And so this is our idle walk run state in our locomotion state machine. And if I click up here on locomotion and go back to my state machine, I see that it's just a state machine with one state. We go to it by default, and in our anim graph, this locomotion is going to output the pose dictated by where we are in our state machine, which is our idle walk run state. So back in our anim graph, we don't need this blend space node. We can delete it. And now our anim graph looks like this. We're driving our animation based on a state machine. If I compile, I'll see those wires animated. And if I press play, well, I now have my state machine dictating my pose, which is simply my idle walk run state, which contains my blend space. But now that we have a state machine, we can go into locomotion and we can have more than one state. We don't have to just have idle walk run. We can have multiple states, and we can have them connected with arrows. If I drag off of the edge of my state, I can add a new state. And I'm going to call this state jump start. And jump start can have my jump start animation inside of it. If I double click, I can come in here and bring in my jump start animation, make sure it's connected, and now my jump start state has an animation pose. So when do we transition from idle walk run to jump start? Well, that's where the transition rule comes in. You see, this arrow is a transition from idle walk run to jump start. And in order to make that transition, we have to set a rule for when that should happen. And we can do that by double clicking on the transition rule icon here. And this has a result node, which is a Boolean, can enter transition. I want this to succeed when is in air is true. So if I bring in is in air and hook that up, now my transition rule is dictated by the is in air Boolean variable. So if we go back to our locomotion state machine and hover over the transition rule, we'll see it says is in air. So we start off in idle walk run, but as soon as is in air becomes true, we transition to jump start, and we stay there. We never come back to idle walk run because there's no transition going back the other way. Let's just see how this works by pressing play, engaging in the game, and jumping. So we played the animation once, but we stayed in that state machine because we never transitioned back out of it. And we're not even looping the animation. So we're at the end of that jump start animation, and we're stuck there. Now, once we're finished with this animation, I want to transition into a new state, a state with the jump mid animation. That's this one here, the one where Kix is falling. So we need a new state in our state machine for the middle of our jump. Now, I could right-click and add a state. I'm going to delete that. I could drag off of a state and add a state. I'm going to delete that too, because there's a third way to add a state that automatically has an animation in it. That's just by clicking on our animation, dragging it in, and it's highlighted so we can rename it. I'm just going to call it jump mid. And if I double-click it, you'll see that that animation is already here. Except this is a looping animation, so let's select it and make sure that loop animation is checked. So now it'll loop. And we want to transition from jump start to jump mid as soon as jump start is done. In other words, we want an automatic transition from jump start to jump mid once jump start has finished playing. And we can achieve that by selecting our transition rule. We don't have to double click it to open it. we just select it, and there's a checkbox in the details panel called automatic rule based on sequence player in state. So the sequence player inside of the state for jumpstart is the Kicks jumpstart animation. This transition rule can transition automatically based on that sequence player that's inside of the state if we check the checkbox. And now as soon as jumpstart's sequence player, which is this node here, the jumpstart animation, as soon as that's done playing, we'll automatically transition to jump mid. Let's see what that looks like. By pressing play and jumping, we'll see that we're now stuck in that jump mid state, which is playing the looping jump mid animation. Now, you may have noticed that our jump start is a little slow. We might want to play this a little faster. So we can select that animation and we can scroll down in the details panel to the settings. We can increase that play rate. Let's try 1.65 and let's go back, play test and jump. Now that looks better, but we jumped a little earlier than our animation. In fact, I kind of don't want to play the beginning of that animation. I just want to play from about here, which is about 0.2 into the animation, 32%. But we see from a time perspective, it's about 0.2, 0.22 into the animation. That's in seconds. So with my sequence player selected, I'm going to start my sequence at 0.22 right here by setting my start position to 0.22. So we're playing it a little faster and we're playing a little bit into the animation. Let's go ahead and jump. And I think that looks a little bit better. Now we're stuck in that falling animation, so we need to get out of it. And we want to stay in that falling animation until we're no longer in the air. So we can drag a transition rule all the way back to idle, walk, run. And this transition rule can be based on is in air. So let's open that transition rule by double clicking it and drag in is in air. I'm going to hold Control to get a get node, but we don't want to plug in is in air because we don't want to transition when is in air is true. We want to transition when is in air is false. So we can get the opposite value of is in air with a node called not Boolean. If we get a not Boolean node, we're going to negate this value. If it's true, not will return false. And if it's false, not will return true. We're getting the opposite of is in air, which is what we want here. So I'm going to connect that, highlight my nodes and hit Q to straighten them out, and go back to locomotion. So now when is in air is false, we'll go back from jump mid to idle, walk, run. So we have this loop here. So let's see how that looks by play testing and jumping. So as soon as we hit the ground, we'll go back to our idle, walk, run. But we also have a landing animation, don't we? So we can use that as well. So holding Control and clicking on that arrow, I'm going to get rid of it. And I'm just going to get my jump end animation here and rename it to jump end. If I double click it, I see the jump end animation. And I want to transition from jump mid to jump end when is in air is false. So I'm going to go into this transition rule and get is in air, get a not Boolean, and hook it up. And we're done. And back in locomotion, from jump mid to jump end, we transition if is in air is false. And from jump end, I want to go straight to idle, walk, run automatically. So I'm going to drag a transition rule, select it, and check automatic rule based on sequence player and state. So when jump end is finished, then we'll go back to idle, walk, run. So let's see how this looks. Now we're playing that landing animation. Now I'd like to play a little bit into the landing animation. I don't want to play it from the exact start. I'd like to play it from about here, which is about 0.12. So I'm going to take that jump end, scroll down in the details panel and set the start position to 0.12. and I'd like to play it a little faster, about 1.5, but we can tweak that and we'll test it out, and that looks better. And I'll grab my controller and test with my console controller and just make sure that that feels good, and it does. So we now have a jumping animation. Now you might feel like Kix's movement is a little bit floaty, that once we jump, we're not going that high, but we're still staying in the air a little bit longer than you might think. And these are parameters that we can adjust for our character. So in the next video, we're going to do some tweaking of our parameters to get that character movement feeling exactly how we want it to feel. But for now, we have jumping, we have running, things are looking great, we have our basic locomotion for our character. This is a great milestone, so congratulations, and I'll see you in the next video. Welcome back. Now we have walking, running, idle, and jumping, right? And I mentioned in the last video, you might not be happy with your jumping. You might want a more stylized look. In other words, we might want to jump higher but fall quicker. And there are other various movement parameters we might want to tweak as well. So we're going to talk about some of those in this video. The first thing I'd like to do is jump higher and fall quicker. So I'm going to go to BP Kix and select my character movement component. And here is where we can change some aspects of our game. For instance, gravity scale. By default, we fall in a specific way, but we can scale that. If I set this to 2 or 3, I'm going to set it to 3, then when I jump, I'll be falling to the ground faster. It's like having a stronger gravity force. Now, I'm almost to the ground as soon as I've jumped, which is not good, so I need to jump higher as well. So back in BP Kix, I want to scroll down to my jumping/falling and change my jump Z velocity. For my stylized games, I like to increase this to a nice high value. I'm going to try 1200, and we'll see what this feels like in the game. So I'm going higher, and I'm falling to the ground faster. And if you want this to be even more stylized, more platformy, kind of like Mario, then we can make this jump Z velocity higher. I'm going to try 1600. Notice that it changes to 16 meters per second as soon as it's a larger value. It was centimeters before, so don't go changing it to 1600 meters per second. That's way too high. And we'll change our gravity scale to about 5, and we'll see how this feels. So we're falling faster and we're jumping faster. So this is a way to get a little bit bouncier movement, not so floaty, and ultimately these values are going to depend on your game. I'm going to up it to 1800, and I think that's feeling pretty good. So that's jumping, but what about movement? Notice that as soon as we start pressing WASD keys, we're actually not going full speed right away. There's a ramp up. There's also a ramp down, a slowdown that we can't really see that well, but we can if we adjust the walking parameters. If we scroll up in our character movement component, we'll see that we have a max acceleration, a braking friction factor, and under walking, we have ground friction. Now, if you don't want to slow to a stop at all, you can set ground friction to a higher value, such as 10. Then, as soon as we stop moving, we stop immediately. We can also do away with that ramp up by increasing our max acceleration. If I set this to a very high value, such as 100,000, then as soon as we start going, we go immediately. See how jerky it is? Now, with the console controller, we still have pressure sensitivity, but if I quickly press all the way, then we start moving right away. So there is no ramp up, and generally you want some ramp up. So I'm going to go ahead and set that back to its default value by hitting the curved arrow. But it's there in case you'd like that type of movement. Now, if you want to be able to control the character in the air, for instance, as soon as you jump and you're going one way, if you'd like to turn around and go back the other way while you're in the air, well, that's called air control. And if you go to your character movement component under jumping, falling, you can take your air control and increase that value. 0.6, for instance, will give us a lot more air control. If we jump and we turn around, we'll be able to influence where we're going, and a value of 1 is full air control. But this is full air control only at max speed of max walk speed, which means if we want to always go max speed without a ramp up, we'll set max acceleration to a high value. We'll go 100,000. And with a value of 1 for air control, notice I can turn around mid-air and go the other direction instantly. So this is not realistic, but for a stylized, more platform kind of game, this might be what you want. You might want to be able to run up to the edge of a cliff here and completely jump off, but turn around and come back. There might be a pickup that you can grab up there in the air, and then you can come back to safety. So that may be what you want, it may not be. With no air control, I would go flying off that cliff no matter what my inputs are after I've jumped. So because this is a stylized platforming type game, I'm going to keep a large max acceleration and air control of 1, just because I find that to be a little bit more fun and kind of fitting for the style of game. But choose the values that make sense to you. Now, the last properties I'm going to touch on in the character movement component involve stepping and walking on the ground. These are under the walking category. The first one I want to look at is max step height. Now, if I create a mesh, let's just say I go to modeling mode, choose box, and for the height, I choose 45. And I bring in a mesh. I can create this mesh. I'm going to go to Assets, make a new folder called Meshes, and I'll just put it here. We're going to create this. I'll click on Accept, Shift 1 to get out of modeling mode, and I now have a box. Let's see what happens when I try to step on this box. Remember, its height is 45, right? So I'm going to press play. And notice I can step up onto the box, no problem. We can see what the capsule is doing by showing collision. Here's my collision capsule, and it just goes right up onto the box, right? That's because my max step height on my character movement component is 45. If I bring it down below 45, now it's almost 42. If I run up to my box, I can't step on it anymore. Its height is 45, my max step height is less than that. Now, if I bring it up above the ground and I change my max step height to 100, well, we can try to step on it now, and sure enough we can, because the max step height is 100. So that's a property that allows you to dictate how easy it is to step up onto objects based on how high they are from the ground. 45 is the default value. I'm going to reset that. Now, related to step height, we have walkable floor angle, and that's set to 44.76, just below 45 degrees. So this determines how steep an angle can be before we can no longer walk on it. I'm going to scale this rectangle up and rotate it by 45 degrees. I'm going to set snapping increments to 15 and rotate it to 45. So we have a nice steep angle. Let's see if we can run up that wall, and no, we cannot. If I take this slope and bring it down, I'm going to set this to snapping by 5-degree increments. Now we have less than 45, and I can run up that slope. So that property on the character movement component, walkable floor angle, determines how steep an angle can be before we can run up that angle. If I increase it all the way to 90, then we can basically run up walls because our walkable floor angle is 90. If I bring this up to almost 90 degrees, let's make it something like this. Well, I can run all the way up that wall, which doesn't necessarily look that great. So you don't really want that high of a floor angle. I'm going to leave it at its default, which is just below 45. As soon as an angle is 45 degrees, it's barely too steep to walk up, and that's generally pretty good. So that's walkable floor angle and max step height. If you're having trouble running upstairs in an asset pack or a ramp or getting over obstacles and you're like, well, this isn't that high, why can't I walk on it? Go into your character movement component and adjust those values too. So those are some properties on the character movement component. Adjust those until you get things feeling and looking exactly how you want them to look in your game, and your games will feel a lot more responsive and less like the default mannequin that you get in an Unreal Engine template project. So many games just leave those default settings, but that's not appropriate for all game genres. If your game project requires a different feel, then you might want to go in and tweak those settings until they feel good. Excellent job, and I'll see you soon. Welcome back. We're going to cover a handy feature of animation blueprints in this video. Here I'm in my Locomotion state machine. I went ahead and closed one of the tabs because I had two Locomotion tabs up there. Now here's what my state machine looks like. And if I go and find my Kix player controller, here's what my logic looks like for implementing the jump input action. We're calling jump, and this logic is hooked up to started, which means that we'll only jump as soon as that jump button is pressed, and we'll only jump once. But if I hold that jump button down, we won't keep jumping. We'll hit the ground, and we'll only jump again if I release the button and press it again. But the jump function can be called continuously, and if it's continuously called, we'll continuously jump if we're not in the air. So really, if we wanted, we can go to Kix player controller, and instead of calling this on started, we can call it on triggered. If we do that, and we press play and hold that jump button down, we'll keep jumping, except notice that we play the full jump land animation and then the full jump start animation, so it doesn't quite look right. It would look better if we could go straight to that jump start animation as soon as we touch the ground and skip out of that jump end animation. We don't want to play the whole thing if we're still in the air, if we're still jumping. So what we can do is go back to our Locomotion state machine, and we can take our jump end animation and add another transition rule going back to jump start if our is in air boolean is true. So we can open this transition rule, use is in air for it, and now if we're in the jump end animation and we suddenly are in the air again, we'll go back to the jump start animation. So if we hold that space key down, well, now we're going straight back to that jump animation, and we can get this sort of bounciness, this bouncing behavior. So we can continue jumping. Now, the feature that we're going to cover is a feature designed to make our state machines a lot neater. See, we have a state here, jump start, with two transitions going to it. And both of them use that same is in air boolean as their transition rule. And state machines can get way out of hand, just like event graphs can in blueprints. And it's a good idea to use all tools that we have to keep them neat and tidy. Well, the tool that I'm going to use is called a state alias. If I right-click, I can choose Add State Alias, and I can give this a name. I'm going to call it toJumpStart. Now, toJumpStart can replace these two transitions because they're both going to jumpstart. if I select my to jumpstart state alias, I can select which of my states should have a transition going to where my jumpstart points to. For instance, I can have it going to jumpstart, hence the name to jumpstart. And I can take my transition rule and give it that is in air boolean and come back out. And I can remove these transition rules from jump in to jumpstart and from idle walk run to jumpstart. And instead, I can select my to jumpstart and I can select those states that I want to have transitions to jumpstart. One of them is idle walk run, so I check that checkbox. And the other is jump end, so I check that checkbox. So now these two nodes have transitions to jumpstart, but we can't see them. They're now here because of my state alias to jumpstart. So with this, I don't have to have so many transitions. And I can have a transition to jumpstart from literally any state. I just have to check the checkbox next to that state's name. And provided that my transition rule is appropriate for those states, this will work. If it's not, I can drag a second transition rule and I can have two of them. And I can double click the second one and put whatever condition I want here as well. But I don't want to, so I'm going to remove that one and just keep the single state. And by the way, states can have rules going both ways if you want. So these can get quite complicated. So it's a good idea to keep them nice and organized. So now we have the ability to hold down the jump button and continue jumping. And as soon as we're playing that jump end animation, if we're continuously pressing that button, we'll start that jump start animation. So that's a nice trick that you should use in your animation blueprint state machines. Excellent job, and I'll see you soon. Welcome back. Now, I'm sure you've noticed that Kix is wearing something on their back. It's actually a jetpack. It has two jet thingamajigs. I don't know what they're called, but they are supposed to blow fire out of the holes. So for that, we need some fire. Luckily, this game project has fire. If we go to our assets folder to effects and we check out thrusters, here is a Niagara system. Let's double click that. And here's what it looks like. I can right click and zoom in, middle mouse click and bring myself up. And I can look at this beautiful stylized jet thruster effect. What I'd like to do is see Kix blasting fire out of that jetpack, both holes. So in order to put one of these Niagara systems on the mesh, it has to go on the mesh in a specific location. And on top of that, it needs to follow along with the mesh. In other words, I want to attach it to one of the bones on the skeleton. Well, two to be exact, because we have two jetpack thrusters. And for that, sockets are a perfect solution. Now, we can add a socket and we can attach a Niagara system to that socket. So that is my goal for this video. So how do we add a socket to a skeletal mesh? Well, we can do so by finding that mesh. I can select the mesh on Kix and browse to it and open up the skeletal mesh editor, and I can actually add sockets to the skeleton from here. I can also add sockets to the skeleton from the skeletal mesh editor by either opening up the skeletal mesh here in the content browser or by clicking on the skeleton icon and going to the skeleton asset editor. I personally like to do things in the skeletal mesh editor, but that's personal preference. So we can add sockets to bones and we can attach things to those sockets. So I'd like to add two sockets to Kix's skeletal mesh. Now, which bones do we want these sockets on? Well, here's the spine bone. That might be good, but these jetpacks kind of move according to animations. So it might be a good idea to preview Kix in an animation while we're deciding which bone to put our socket on, because this spine 1 is right here. That's not exactly the best spot to shoot flames out of. It would be kind of funny. But we can preview an animation on this mesh by going to Preview Animation and selecting one. Now we have some flying animations. I'm going to select Kix Fly Idle. As soon as I select that, now we can see Kix in a flying animation. And look at those jetpack thrusters. They're animating. So we might not want to put those flames on Kix Spine 1. We might want to find a different bone. So I'm going to scroll down and, oh, take a look. We have Kix Jetpack Base. That's this bone here. And there are other bones attached to it. We have Kix L Jet 1. That's this bone. And Kix R Jet 1. So we actually have a bone for each of these jetpacks. So these are going to be the bones that I want to add sockets and attach them to. So I'm going to right click on Kix L Jet 1 int and select Add Socket. And right away, that's an awful name. So I'm going to rename this to thruster underscore L because we're on the left jetpack thruster. Now, we can change the transform of this socket relative to the bone it's attached to. It can have an offset, rotational and translational. But I don't know what that offset should be because I can't see the Niagara system that I want to attach to it. Well, Unreal Engine has a really nice feature to preview what it would look like if we attach some asset to a socket. We can do that by right-clicking on the socket and choosing Add Preview Asset. We can attach a preview asset such as a mesh or even a Niagara system. We want to attach a Niagara system, so I'm going to choose NS Jetpack Thruster, and there's that thruster. And as we can see, it doesn't quite look right. It's not oriented correctly, but we can change the socket's location and rotation relative to its parent bone. Now I have snapping on for rotation. I'm going to set its snapping increments to 10, and I'm going to rotate it by 90 degrees so it's facing down the thruster. And I'm also going to hit W to go to translation mode and move it on down like so. Now, I'm going to need to actually tweak this a bit. So I want to pause my animation for a second and move that thruster socket so that it's looking about right. I want it to be right here coming out of the jetpack, right? So something like that should do it. And now I can press play and I can see that it looks a lot better. Now that's just my left thruster. I need one on my right. So I'm going to pause the animations and add a socket to my right jet bone. I'm going to right click, add a socket. Right away, I'm going to rename it to thruster underscore R. Right click on that and add a preview asset and choose NS Jetpack Thruster. And just like the other one, it is not oriented correctly. It's 90 degrees off, so I'm going to rotate it by 90. And then I'm going to move it down. So we'll go ahead and bring it down like this and make sure that it looks good. We might have to tweak it a little bit, like so. And there we go. Make sure you adjust it until it looks just right. And now we have our thrusters. Make sure when you're adjusting these that you have the socket selected and not the bone. You do not want to move the bone. You want to move the socket relative to the bone. All right, and this is what it looks like with the jetpack. Now, this is only a preview asset. If we go back to Kix, we will not see those thrusters. All we did was add sockets to our skeleton. We can see them here in asset editors. I don't see it in that skeleton asset, but if I close it and open it back up, I do. So really, this is a preview asset we still need to actually add that Niagara system to our character, and we'll do that soon. For now, we have those sockets and they're positioned correctly. So if we do spawn in a Niagara system or add one to our character and attach it to this socket, it's going to be at the correct location, as the socket has the correct location relative to the bone. And that's what we care about for now. Awesome. And before we wrap up, I just want to bring your attention to the color of the flame. If we go back to our NS Jetpack Thruster, notice that our Niagara system has a sprite renderer. It's rendering this material, and notice it's a material instance. And if we browse to it, there are two different versions of this material. We have the material itself, and we have the material instance, which has a category thruster with some colors that you can override. Now you can change those colors, but I recommend not messing with these colors, but instead making your own material instance of the parent material by right-clicking, choosing Create Material Instance, and calling this MI Jetpack Thruster _ yellow, for instance. And now I have this MI Jetpack Thruster yellow, and I can change my jetpack to use that MI Jetpack Thruster yellow. And this is the original material. If I save that, I can go back into the skeletal mesh editor and see what it looks like with this material. And if you really want to, you can take your jetpack thruster and change the materials by overriding them in that material instance. So you can make a purple flame or a red flame, and you can play with some of these parameters to make it look different. So I just thought I'd throw that out there. You have options to make that effect look different. You can even duplicate the Niagara system and have multiple versions of it as well. But I'm going to leave it at blue because I like the blue and I think it looks good on Kix. All right, so we now have sockets on our skeletal mesh. Excellent job, and I'll see you soon. Welcome back. Now our Kix skeletal mesh has sockets, and we know that if we attach a Niagara system to those sockets, it will be oriented correctly and positioned correctly. Let's test that theory though by adding a Niagara system to our Kix skeletal mesh. Let's add two of them actually, one for left and one for right. Now I'd like these to be components, and that way we can activate or deactivate those components at will, and we'll learn how to do that. So let's go to BP Kix, and we'll add this to our mesh. So we want these attached to our mesh because if we attach a component to our mesh, we can select a attach point. We can select a bone, or in our case, we want to select a socket because it has an offset from the bone that we need. So with our mesh selected, I'm going to click Add and search for Niagara and choose Niagara Particle System. And this one will be Thruster Effect _L. This one will be for the left thruster. Now notice it's attached to my mesh, but it's right here at the base of the mesh at the bottom. But we can specify a socket to attach to by selecting the thruster effect, scrolling up, and under sockets, we can choose a parent socket. It says none and it's grayed out, but we can click on that browse icon and choose a socket. We want thruster L, and that's going to place it right there where that socket is. Now, what I want to do is take my thruster effect and set its Niagara system asset by choosing Jetpack Thruster. And there we go. It's attached at that socket and it's at the correct location. It looks great. I want to do this for the other socket. So I'm going to select the mesh. I'm going to add another Niagara Particle System component, and I'm going to call this Thruster Effect _R. I'm going to choose its parent socket to be Thruster R, and choose its Niagara system to be Jetpack Thruster, and now we have two of them. And these are actual Niagara system components on Kix. Perfect. So now I can go and press play, and I have those thrusters, and it looks great. Now, if I'm moving around, notice we have this blur that doesn't look too good. And for this type of effect, that's not something we want. This is actually motion blur. And I can turn motion blur off for my project in project settings. I can go to Edit, Project Settings, and search for motion blur. And that's a checkbox I can deactivate. So now we won't have motion blur. So for this particular project, I want that off. And now if I move my camera quickly, I don't have that motion blur and it looks a lot better. Now, my thrusters shouldn't be on all the time. We should activate them and deactivate them, which means we're going to want an input action and logic to activate or deactivate our Niagara system. And all components have an activate and deactivate function, and we can also start them off not active by selecting the component, and under activation, we can uncheck auto activate. We can do that for both of them. So they exist, they're there, but they're not active. We can activate them at will, and just to test that, in BP Kicks begin play, we can place a delay for, let's say, 2 seconds. And after 2 seconds, we can activate these thrusters. I'm going to grab both of them and drag off and call activate. And we can plug both of these thruster effects into activate. And after 2 seconds from begin play, we'll activate both thrusters. Let's see what that looks like. We'll wait 2 seconds, and there they are. They're now active. So we can activate and deactivate Niagara systems at will. We're not going to do so with a delay, so I'm going to delete those. We're going to do so with input when we activate our thrusters, and we'll do that next. So excellent job, and I'll see you soon. Welcome back. We now have 2 Niagara particle system components attached to our mesh, specifically attached to sockets on our mesh, and these are our thruster effects. Now we can check auto activate in the details panel for each one to see what they look like activated automatically. But we want to activate these on demand with input. So for that reason, we're going to keep auto activate unchecked for each component here. And we're going to create an input action for activating our jetpack. So let's create that input action. For now, I'm going to go ahead and close all my tabs except for BP Kicks and BP Kicks Player Controller. All the rest of these can be closed. And we're going to go into our Blueprints input folder, into Input Actions, and create a new input action called IA Jetpack. I'm going to go ahead and leave IA Jetpack's value type to digital bool. Now we just need to associate it with keys in our input mapping context. So we'll open IMC Kicks Movement, add this mapping, and select IA Jetpack, and choose which keys we want to activate our jetpack. Now, for the keyboard, I'd like to use my left shift key. So I just clicked on the keyboard and pressed my left shift key. But for my console controller, I'd like to be able to activate the jetpack with my right trigger. So if I click plus to add a new control binding to this action mapping, let's see what happens if I click on that keyboard icon and I press that trigger button on my console controller. Well, notice that my control mapping is now set to gamepad right trigger axis. This treats that trigger as a pressure-sensitive input, much like a thumbstick, and it will have values on a scale from 0 to 1, depending on how far in that trigger is pressed, and that's not exactly what I want. So I need to go back and change it by going to Gamepad and searching for Gamepad right trigger and choosing the one that does not say axis. Axis gives us an axis of values from 0 to 1, whereas Gamepad right trigger is simply on or off, which is more appropriate for an input action that has a digital bool value type. So we're going to make sure that it's set to gamepad right trigger. And now we have an IA Jetpack input action. Now I'd like to activate and deactivate my thrusters based on when this IA Jetpack has been started and completed. Now we've seen that we can go straight into our character BP Kicks, right-click in the event graph, and search for IA Jetpack. And we can implement IA Jetpack here on the character, even though the input mapping context has been added to Kicks player controller. So if we wanted to, we can simply activate and deactivate our thruster effects here. And just to show how that works, we're going to do that. As soon as we've started our input action, our trigger has been pressed, or our left shift key, we're going to take our thruster effect R, and from that get node, we're going to call activate, and we're going to hook that up to started. Now we can also take our thruster effect L and hook that up to the same node. This is the equivalent of calling activate twice. Now, in addition to that, I'd like to deactivate our jetpack thrusters when our input action has been completed. So I'm going to drag off of thruster effect R and type deactivate and call that function and hook that up to completed. And I'm also going to take thruster effect L and hook that up to deactivate as well. So now we have only 4 nodes achieving this effect, and I can go ahead and collapse my input action node and give myself a reroute node here. I'm going to highlight the reroute and the deactivate node and hit Q, so they're aligned horizontally, and now our nodes look nice and neat. And we can test this out by pressing the shift key and the right trigger. So let's go ahead and press play. I'm going to hold down the shift key and I get my thrusters. I'm going to release the shift key and my thrusters are gone. Likewise, I'm going to get my gamepad controller and press my right trigger. I see that I get my jetpack thrusters, and if I release, my thrusters are deactivated. So everything works as expected. And this is great. We can actually say that we've accomplished our goal here. But if I'd like to handle all of my input in my controller class, just to keep that responsibility contained within the player controller, I can do that. I could implement IA Jetpack here and get my controlled character and cast it to BP Kicks. You see, the controlled character is a character object reference, not a BP Kicks object reference, and the character class does not have these thruster effects. It's the BP Kicks class that does. But I don't want to cast to BP Kicks from my Kicks player controller. And the reason is that creates a dependency on BP Kicks here in player controller. I don't want my player controller to depend on the BP Kicks class. I want it to be more generic than that. You see, managing your dependencies is something you do in good coding practice. I would be okay with BP Kicks accessing my Kicks player controller class, but I don't want that dependency to be going the other way from the player controller to Kicks, because I see my player controller as a more generic class that I should be able to use with multiple types of characters. So if I want to activate and deactivate my thrusters from the player controller, a good way to do so in a generic way is through an interface. I can create a Jetpack interface with Jetpack-related functions that my BP Kicks character can implement, and my Kicks player controller can simply call those functions on its controlled character. So before we wrap up, we're quickly going to create that interface. So I'm going to create a new folder in my Blueprints folder. This is going to be for my interfaces in this project. So I'm going to create a new folder called Interfaces. And we'll make our new interface here. So I'm going to right-click, go to Blueprint, and choose Blueprint Interface. I'm going to call it BPI Jetpack. So we now have a BPI Jetpack interface. And this function can contain Jetpack-related functions, such as Start Jetpack. We'll go ahead and make that our first function. And we can have a stop jetpack function as well. So stop jetpack. And these are generic functions that my player controller can call without having to know what class has implemented it. So first we'll implement start and stop jetpack in BPKicks. We can go to our class settings, into interfaces, and add our interface to the dropdown. We can search for BPI jetpack. And now we have those functions in our interfaces section in the My Blueprint panel. And we can simply implement these functions. I'm going to double click on them both. That way we have them implemented here as events. And we can simply hook them up to the functionality that we already have. Start jetpack, which in my case was on the bottom, now it's on the top. That's going to plug into activate, and stop jetpack is going to plug into deactivate. And now I can remove this input action IA jetpack altogether. And I now have the implementation here using my interface functions. And now my BPKicks character doesn't have to implement that input action. We can still keep the responsibility of that on the player controller. Now the player controller simply has to implement that IA jetpack. So let's go ahead and implement that. And we'll get our controlled character with a validated get. That's a good idea. Except we don't want this connected to triggered, we want it connected to started. And we want to take the controlled character and call start jetpack our interface function. So we're going to do that here for started. And we're also going to use a validated get for completed. And we're going to call stop jetpack when completed. And I'll go ahead and collapse that input action. So now we're calling interface functions on the controlled character without having to cast that character to a more specific class. I don't mind having our controlled character be a character, as we did perform a cast in our store essential variables function. We cast a character, but this is a engine class. It's more generic, whereas BPKicks is specific to this project. And if we plan on using our BPKicks player controller in any other project or with any other character, we would then have to perform two casts. We'd have to first cast to BPKicks. If that's valid, we access the kicks specific thruster effects and activate them. Then if that cast failed, then we would cast to whatever other character classes we're using, and that gets messy. An interface call keeps things generic and expandable as a code base. So now that we're handling input on the player controller, and we're handling the jetpack functionality on the character, and our player controller doesn't have to know about the character, it just has to call interface functions, and Kicks implements those functions. Let's go back and test this out one more time, and we see that our jetpacks are working. Perfect. So we see that our jetpacks are working, but we're not actually flying around. So far, our jetpacks just have a visual effect, so we still have some work to do. So we're going to continue our work on the jetpacks in the next video. I'll see you soon. Welcome back. Now we have our visuals working for our jetpack thrusters, but everything is completely silent. So in this video, we're going to handle playing the sounds for our jetpack. Now, if we go into our content drawer, into assets, we can find our sounds folder, and we have some sound effects under thrusters. We have three main sound effects. We have thruster loop, thruster start, and thruster stop. And these are meta sounds. And we can play each one to see what they sound like. There's our thruster start. That's our thruster stop and our loop. And that sound is going to loop indefinitely. So we're going to start playing some sounds when we activate our thrusters. Now, I don't think I need any of my input-related assets open, and I'm going to close BPI Jetpack for now. We're going to come back into BP Kicks, where we're activating and deactivating our thruster effects. Now we have this compact form where we only have 2 get nodes and our wires are crossing over to the different function calls. And this looks great for the case where we simply need to activate and deactivate our effects. But I'd like to separate things now because starting the jetpack now is going to involve more than just activating our thruster effects. So the first thing I'm going to do is separate these. I'm going to duplicate my get nodes for my Niagara components, and I'm going to break the wire on deactivate and just hook up my new get nodes to those. Now we have separation, and we're going to start up here with activate. So with event start jetpack, I need to play a sound for my thrusters, and I want to play this MS thruster start. So I'm going to spawn a sound at location. We'll go ahead and hook that up. And for the location, we're going to use get actor location. We'll just use Kix's location for this. And for the sound, we're going to choose that MS thruster start. Now, this is quite an intense sound. Let's just go and check how this sounds and how it feels in the game. So it lasts for quite a long time. If we start our jetpack and release the button immediately, we still hear that sound for a while, like this. So it's a little much, and I'd like to fade that sound out as soon as we've played it. Now, this is going to involve more nodes, so this is a good time to start collapsing things to functions. I'm going to collapse these 2 nodes to a function, and I'm going to call this start thruster sounds. So I'm going to open start thruster sounds, and let's just expand the dropdown for spawn sound at location. For one, this sound is a little bit loud, so if we want, we can play this a little bit quieter. I'm going to set the volume multiplier at 0.6, and as soon as I play this sound, I want to fade it out so that it doesn't last so long. And we can do that using the return value, which is an audio component object reference. That's what gets spawned by this node. And we can call fade out. I'm going to use fade out and set a fade out duration of 1 second. So the sound will only last for a second. And expanding the dropdown here, I see fade volume level. This means we're going to fade down to 0. And the fade curve is the trend that our volume will follow over the course of that second. It can be a linear fall off. For us, that's going to be fine. So now that we have a fade out, let's see how that sounds when we start our jetpack. So we have a 1 second fade out, and that sounds a lot better. But while our jetpacks are active, we're going to want to play a looping sound. Okay, so I'm going to collapse spawn sound at location, and we're going to spawn another sound, and that's going to be a looping sound. Except this one is going to be attached to Kix. So we need to use a different node. We want to use spawn sound attached. This is going to allow us to attach the audio component that gets spawned to Kix. So we have an attached to component, and that's a scene component object reference. We're going to attach the sound to the root component of Kix, which is the capsule component. We'll drag that in, hook that into the attached to component, and hook this up, and we can choose a sound. We're going to choose thruster loop, MS thruster loop. And we can expand the dropdown, and we have different options for this. We can specify the location. I know we're attaching to the capsule component, but this specifies where that sound will be depending on the location type. If the location type is keep relative offset, then this location is a relative transform from that root component. So we can leave that at 0. I'm going to set the volume multiplier to 0.6. We're not going to set attenuation settings. We'll leave everything else as is. So let's see how this sounds. We're going to go ahead and start our Jetpack. Now, we don't get rid of the sound. It stays even when we stop our Jetpack. But while the Jetpack's active, this sounds pretty good. But I'd like to fade this in so that it doesn't just start abruptly. Because if we bypass our spawn sound at location node and just spawn our sound attached like this, we'll see that that sound starts very abruptly. So I'd like a bit of a fade in, and we can do that with a fade in node. And we can choose a fade in duration of something like 0.35 seconds. Now we can see how that feels. And it's a nice gentle fade in. It's a little faster than our fade out for the spawn sound. So I can connect this back. And we now have the ability to hear our Jetpack starting, except when we spawn this sound and attach it to our root component, it sticks around, and we need to deactivate this sound. We need to stop it. And we need to do that when our thrusters stop. So in order to be able to stop this sound, to destroy it or deactivate it, we have to store it as a variable. So we're going to take the return value, promote it to a variable, not a local variable, because we need to access it outside of this function. And we're going to call this looping thruster sound. And I'm going to go ahead and give this looping thruster sound a category thrusters. Now, I'm going to set this value here, and then I'm going to use the value of my variable for the fade in. So I'm going to break that target and hook these two up. That way our nodes are clean. And I now have a reference to looping thruster sound that I can access when we stop our Jetpack. So in Event Graph, if we go to Stop Jetpack, I can take that looping thruster sound and check to see if it's valid by converting it to a validated get. And if it is valid, we can then call stop on this sound. And this should stop the sound. So now that we're stopping this sound, let's go ahead and see what happens if we release that button. And we stop the sound. Now, you might be wondering if we're getting a whole lot of thruster sounds being spawned in our start thruster sounds function, because we're spawning a sound and attaching it to our capsule component. You see, spawn sound attached returns a audio component, and we're storing that in our looping thruster sound. So the next time we call this function, are we spawning a new sound, and is the old sound still around? Well, we can always check looping thruster sound with a validated get or an isValid node. So I'd like us to understand what happens to looping thruster sound after we stop it. Let's bring in looping thruster sound and call isValid on it. We'll get the one with the question mark. And we'll do two things. If looping thruster sound is valid, we're going to print a string that says looping thruster sound is valid. And if it's not valid, we're going to have another print string, and we'll have looping thruster sound is not valid, and we'll go ahead and make that one red. Now we can hook these up and see the status of our looping thruster sound every time we start our thrusters. So we need to hook both of these up to spawn sound attached. And the first time I expect this looping thruster sound to not be valid because we haven't set it to anything yet. So the first time it'll be not valid, we'll get the red message, and then we'll spawn a sound and set looping thruster sound and call fade in. Now, when we release that key, we'll call stop on that sound, and when we press it again, we'll start this process over and see if it's valid. So let's go ahead and press play and start and stop our thrusters. The first time it's not valid, we'll release, and let's start our thrusters again. And look at that, it's not valid. Why is that? Well, if we go back and take a look at spawn sound attached and expand the dropdown, all the way at the bottom we have auto destroy. And it says whether the returned audio component will be automatically cleaned up when the sound finishes by completing or stopping, or whether it can be reactivated. So our spawn sound attached has auto destroy set to true, which means as soon as the sound is stopped, this sound will be destroyed and the variable will not be valid anymore. That's what's happening. But if we uncheck auto destroy and we go back and press play, let's see what happens then. We'll start it, it's not valid. We'll stop it, but we're not cleaning up that resource. So if I start it again, it is valid. But the problem is we're spawning in a new audio component and then storing that in the variable. So the old one that did not get destroyed still exists in memory. So what we've done is created what we call a memory leak. And if we start and stop our thrusters enough times, then we'll spawn so many sounds that we're simply stopping and not destroying that eventually our game could run out of memory and crash. And this is not something that you want in your games. So what we have to do is either check auto destroy and know that our sound is destroyed every time we stop it, or we can check to see if it already exists and only spawn the sound if it doesn't already exist. And if it does already exist, we can simply activate it by playing the sound. The way we have it now with auto destroy set to true, we're just spawning and destroying the object over and over again. Now, technically, this is more expensive. The action of spawning and destroying a component does require resources, whereas starting and stopping a component that already exists is cheaper. So I'd like to show how we can spawn a single sound and keep it around and just start and stop it rather than spawning a new one and destroying it every time. So here's how we do that. I'm going to remove these print string nodes. And we'll check our looping thruster sound and only spawn a new one if it's not valid, if it doesn't exist yet. That's going to be using spawn sound attached. So we'll spawn the sound if is not valid is true. And we'll store the looping thruster sound and we'll call fade in. But if it already is valid, all we need to do is play the sound. So we'll get our looping thruster sound and call play. So now we can start that sound and we can call fade in on that sound. So we'll duplicate fade in and use the looping thruster sound for fade in. So I'm going to duplicate that node and put it there. So in this case, spawn sound attached can have auto destroy set to false. And now we'll only spawn the sound if looping thruster sound is not valid, which it'll be valid after we've spawned it for the first time. And then we can go back in our event stop jetpack, and all we need to do is stop it when we no longer want to hear the sound. And now we'll only ever spawn one audio component. Let's go ahead and check this out. And it works. So that's a little bit of an optimization. We'll only spawn the sound once and keep it around, and we'll be calling play and stop on that sound as we start and stop our thrusters. Now the only other thing left to do is to play the stop sound when we stop our thrusters. So we're going to go ahead and take these nodes where we're stopping the looping sound. We're going to collapse those to a function, and we're going to call this stop thruster sounds. And here in stop thruster sounds, we're just going to play the stopping sound as well. So in order to play our stopping sound, we're going to use spawn sound at location. We're going to pass in the actor location, so using get actor location. And the sound I'd like to play is the stopping sound, which is ms thruster stop. And expanding this, we see auto destroy is set to true. I'd like to leave that at true, so we get our sound destroyed once it's finished. I'm going to set the volume multiplier to a lower value, about 0.4, and I'd like to fade this sound out by taking the return value and calling fade out. And I'll give it a fade out time of about 0.55 seconds so we can see how this sounds. We'll go ahead and start the thrusters and stop them. And that sounds pretty good. We don't have to worry about the memory of an auto destroy sound that we spawned. It will be destroyed when it stops. And because it's not looping, it will stop once it plays once. So we now have stop thruster sounds and start thruster sounds. And our event graph is looking pretty good. Our activate and deactivate could be refactored into a function, but we'll clean these up as we continue in the next video. For now, we have our sounds. It sounds great. Awesome job, and I'll see you in the next video. Welcome back. Now we have some visual and sound effects working for our jetpacks. And it looks and sounds great, but it's not really functional. When we activate a jetpack, we expect to be able to fly. So this video is all about flying. Let's get started. If we go into BP Kicks and we select our character movement component in the details panel, if we scroll down, we'll see that there's a small section called flying. And we have a max fly speed and braking deceleration flying. The character movement component has movement modes, and by default, its movement mode is walking. But we can change its movement mode at runtime, and we're going to do that when we start and stop the jetpack. Now, before doing that, I'd like to collapse our activate and deactivate nodes. In fact, I'd like a function that can activate or deactivate it based on a Boolean input. So we're quickly going to create a new function. And we're going to call this activate thruster visuals. But we're going to have a Boolean input here called active. And we're going to get our thruster effects and activate or deactivate them based on this Boolean using a branch. So we'll set that branch right here. And back in our event graph, I'm going to just copy all of these nodes and come back to activate thruster visuals and paste them in. And for true, we'll hook up activate, and for false, we'll hook up deactivate. And now we have one function that can handle both scenarios. So back in our event graph, we can call activate thruster visuals here, passing in true, like so. And for stop jetpack, we'll delete that and call activate thruster visuals and pass in false. And we'll just quickly test to make sure we didn't break anything by activating and deactivating, and we see that it works. So now we have the sounds and the visuals. Let's take care of actually flying by setting our movement mode. And to do that, we need to get the movement component. And we can do that here when we start the jetpack, or we can do it on the player controller when we start the jetpack here, as we do have the movement component here on the player controller class. I'd like to handle that on the player controller class as it's related to movement. So I'm going to go to our essential variables section and drag in our movement component, convert it to a validated get, and from the movement component, I'm going to call set movement mode. Now, we don't see it here because our movement component is a pawn movement component object reference. But we can easily change this to a character movement component object reference if we go back to store essential variables and we instead cast to character movement component before storing our movement component variable. So after calling get movement component, I'm going to call cast to character movement component, and I'd like to change movement component to a character movement component. Now we can do this in one of two ways. I can change the type of this variable, or I can make a new variable of a new type and delete the old one. let's see what happens if we take this movement component variable and we change its type. We go to variable type and search for character movement component. If I choose object reference for character movement component, we get a warning that says this could break connections. Do you want to search all variable movement component instances, change its type, and recompile? That's what we want to do. So we're going to choose change variable type. And it's going to search for all instances, and this may create some errors that we have to fix. For instance, this set node here isn't going to work because now this is a character movement component object reference. So we can break that wire, and instead we can use the return from as character movement component. We're going to go ahead and hook that up and make sure that our cast is hooked up. And now we have a character movement component object reference. And if we click on compile and we don't get errors, then we don't have any other errors to fix. So now that movement component is a character movement component object reference, after our validated get here in our IA Jetpack, we can now call set movement mode, which is a function on character movement component. And we can change the movement mode on our character movement component to flying. Notice the dropdown shows us the movement modes. Walking is the default. We're going to choose flying. So we're going to set that to flying. And when we've completed our input action, when our jetpack is no longer active, we can now set this back to its default movement mode, which is walking. So we'll go ahead and set that back. And now we have a change in movement mode for our movement component, which belongs to BP Kicks. So let's just see what happens if we do that. But first, I'm going to run up to the top of this little hill, and I'm going to activate my jetpack here. And then I'm going to move off the hill. Notice that I'm actually floating. Now I'm going to continue floating until I get back to walking mode, and jumping works as expected, and gravity works as expected. But as soon as we go to flying mode, we're now not actually affected by gravity, and we can move around in the world. And notice there's a very small degree of friction, so it takes a while to slow to a stop. And as soon as I deactivate my thrusters, gravity kicks back in and we fall. So there's just a couple of things I'd like to tweak about this mechanic. For one, I'd like to slow to a stop a little bit faster. In other words, if I start my thrusters and I start moving, I'd like to just slow to a stop right away and only keep moving if I'm continuously pressing the input keys. So to do that, I'm going to go to BP Kicks, select character movement, and on this component, I'm going to go down to the flying section, and I'm going to increase my braking deceleration for flying. I'm going to set that to a value of 200. And now we should slow to a stop much faster. Let's see what happens if we do that. I'm going to start my thrusters, and we'll see that we slow to a stop pretty much after a couple seconds. And that's the kind of friction that I want here in the air when I have my thrusters active. So that's the first thing I wanted to tweak with this. But the next thing is, as soon as I'm flying, I want to orient my rotation to the controller. In other words, I don't want to be able to move my camera around and see the front of Kicks. When I move my camera, I want Kicks to follow that rotation, at least in the yaw direction. And the reason for that is we're going to implement some flying animations that will look good when our character actually follows the controller. So there are a couple of settings to set for that. So back in BP Kicks Player Controller, after setting the movement mode to flying, I'm going to take the movement component and set a setting on it. We're going to set orient rotation to movement, and we want orient rotation to movement to now be false. I want to orient my rotation to the controller instead, which means we now have to set a setting on the character called Use Controller Rotation Yaw. Remember, if we search for controller in BP Kicks with BP Kicks self-selected, we have Use Controller Rotation Yaw, Pitch, and Roll. I'm now going to want that to be true when I'm not orienting to movement. So I'm going to get my controlled character here, and we're already making sure it's valid before we get to this point. And we're going to set Use Controller Rotation Yaw. We're going to set that to true. And we want the opposite of these settings when we stop our jetpack. So I'm going to duplicate these nodes, paste them down here. Only when we stop the jetpack, we're going to set Orient Rotation to Movement back to true, as we'll now be walking, and Use Controller Rotation Yaw back to false. So we're no longer using the control rotation. So let's see how that looks if we go ahead and activate the thrusters and we move around. We're rotating our camera, we're actually rotating our controller, and we're orienting our rotation to the controller instead of movement. But as soon as I disable my thrusters, now my orientation is no longer following the controller. It's now based on movement. Now notice with this setting, we just snap to this location. So a smooth way to do it is by simply taking our character movement component and setting the property on that allows us to smoothly interpolate to our controller rotation. Do you remember what that Boolean is called? It's called Use Controller Desired Rotation. If we set that to true, we'll now interpolate smoothly to our controller's rotation. Now I'm going to uncheck that when we deactivate our thrusters. And now if we rotate our camera around facing the back and we activate our thrusters, now we smoothly orient towards our controller rotation. This is using Use Controller Desired Rotation instead of setting Use Controller Rotation Yaw. So Use Controller Rotation Yaw is good for just automatically using the controller's rotation yaw, setting our character's rotation to follow that rotation yaw, whereas the movement component has the ability to smoothly interpolate to the rotation yaw. And that's better when we're transitioning into and out of this state. And of course, we can go to our character movement component and search for rotation, and we can speed that rotation rate up if we want to orient towards that direction faster. We don't have to use 720. We can use 1440, for instance, and we can go ahead and move our camera around and activate our thrusters, and we have a faster rotation rate. Just remember that that rotation rate also affects how quickly we rotate our camera, but 1440 is pretty quick, so we're pretty responsive. So now we're switching our movement mode, and we're also switching the way that our character is oriented. When our thrusters are not active, we orient rotation to movement. When they are active, we orient to the controller's yaw. And this will look a lot better once we implement some flying animations, which we'll do pretty soon. But I'd also like our thrusters to make us go upward as we're holding those thruster keys down. I'd like the thrusters to actually have some kind of upward force or perceived upward force. And we'll handle that next. But before we wrap up, let's just clean up our nodes here in the player controller, as we're doing a lot of things here, and we don't want our event graph to get out of hand, right? So we're going to collapse these to functions. And it's important to make sure the functions only do a specific thing. We don't want one function to handle too many responsibilities. Now, setting the movement mode is closely related to setting these properties on the movement component. So I'm going to collapse these nodes to a function, and these will be for setting the movement component variables when flying, we can simply collapse this and call it start movement mode flying. And we can collapse these other nodes to a function, and we'll call this start movement mode walking. And now this looks a lot better. And we could even collapse these to functions, but for now, we'll leave them as is. Our code looks nice and clean. It looks great on Kix as well. Excellent job, and I'll see you in the next video. Welcome back. In this video, I'd like to add some input to move the character up when those thrusters are active. Once we're in flying mode, I want us to be continuously adding input going straight up, and this is going to be a challenge for you. So while these thrusters are active, add input. I want you to add an input vector to the movement component. And since we're handling movement in the player controller, see if you can figure out how to do this from the player controller and only add this input while the thrusters are active. In other words, when the jetpack is on, and when it's off, I want you to no longer add that input. Then watch how I do it and compare your solution to mine. That's okay if your solution is different from mine. This is just a practice exercise. So pause the video and try this challenge now. Okay, so we want to add movement input, and I'd like to do this in the Kix player controller. And I'd like to add input every frame while the jetpack is active. Now, I could do this in Tick. I could perhaps set a Boolean to true or false based on when the jetpack is active, and then in Tick, check that Boolean and only add that input while active. That's a perfectly valid solution if that's what you did. What I'm going to do instead, though, is I'm going to use the triggered event on IA Jetpack, because I know that this triggered event execution pin is executed every frame while the input is active. So I really only need to call a function on triggered. So I'm going to add a new function, and I'm going to call this apply thrust input. And I'm going to take my controlled character and use a validated get for it. And I'm going to get my movement component and use a validated get for this one. So I know both of these are valid here. And on the movement component, I'm going to call add input vector. We know that this is how we're moving our character, but while thrusters are active, we're going to add an input vector up. Now, instead of hard coding just one in the Z here and moving in the world up direction, I'm going to get my controlled character and use get actor up vector. So I get my up vector of the character itself, and I'm going to multiply this vector by a float value. And this float value is going to determine just how much we're going to add that input vector. This can be a thrust factor of sorts. So I don't have to add a unit vector with a magnitude of 1. I can multiply this by, say, 0.25, but I'd like this to actually be a variable, and I'll call this thruster input factor. So its default value will be 0.25, but we can change that if we want to tweak it. And I'm going to add the input vector in this direction with this magnitude. And this will only be called onTriggered as long as I call it here, onTriggered. So I'm going to go ahead and call apply thrust input onTriggered. And really quickly, I'm going to set its category to Kix input. So it goes into the Kix input category. So now I can play test this. I can activate my thrusters, and we're going up. And if I deactivate them, I go back down. So now I can actually fly. And notice if I'm already going up, because I've jumped, as soon as I start flying mode, we still get a little bit of a drift. But because we have air braking deceleration, it's only going to last for a couple of seconds. So if I'm moving forward and I activate it, I'm going forward. So that's how that works. All right. So we now have a thrust input being applied on triggered, but when we're not triggering that input, we're not applying it. So we didn't have to create a Boolean and use the tick function. We're only applying this when we actually need it. And that's okay if you did use the tick function, that's totally fine. You can keep that solution or you can change it to the way I did it. Either way is fine. Technically speaking, not using the tick function in this case is a little bit better because we're not checking a Boolean every single frame when we don't need to. Checking a Boolean is a cheap operation though, so it's not really going to affect performance either way. And before we end the video, the last thing I'd like to do is refactor these nodes into a function, just because I like to see one node rather than three. So I'm going to collapse this one to a function called startJetpack. And I'm going to collapse these nodes into a function called stopJetpack. That's okay that they have the same name as the functions in the interface because Kix player controller is not implementing that interface. So these functions belong to the Kix player controller class. And we can give these the category of Kix input as well. And now the IA Jetpack looks nice and clean. I'm tempted to collapse these two nodes to a function, but I don't need to. Everything here looks pretty nice. And we're ready to move on. Great job, and I'll see you in the next video. Welcome back. Now that we have actual flying going on, it's time to handle what happens animation-wise. Because as you can see, while we're moving, we're still running in the air, and it doesn't really look right. But we do have some animations for flying. Let's take a look at those right now. We can go to Assets, Kix, Animations, and let's take a look at Kix Fly Forward. This is what it looks like. Kix is flying straight forward, but we also have Fly Idle, which looks pretty awesome, and Fly Left, we have Fly Right, and Fly Backward. And I'd like to use a blend space to blend between these values depending on our input. So that's what we're going to do now. Let's go ahead and create a new blend space. We're going to go into our Blueprints folder, into Kix, and we'll create our blend space here. We'll right-click, go to Animation, and we're going to choose Blend Space and select Skell Kix as the skeleton and call this BS Flying. Now remember with our idle walk run blend space, if we go ahead and open that up, we only used one dimension. We used the horizontal axis, but we didn't use the vertical axis. And that's because we didn't really need to. Blending between these animations is one-dimensional. There's only idle, walk, and run. But our new blend space, if we open that up, BS Flying, this one is going to use two dimensions. We're going to use both the horizontal and the vertical axis. And these are going to be driven by our input. I want to know when we're moving what our input action values are for movement. In other words, if we go to Kix Player Controller and use our IA Move input action, let's just see what those values are for the action value as we're moving. Let's print a string here and bring action values straight into that print string node. And let's see what those values are. I'm going to press play and I'm going to move forward. We see that we have a 1 for our Y. I'm going to move right. We see that we have a 1 for our X. I'm going to move backward. We have a -1 for Y. And I'm going to move left. We have a -1 for X. And these values are actually not so discrete when we use our thumbstick. If I use my left thumbstick, I have a negative value for x, but it's only 1 if I press the thumbstick all the way just about. And same thing goes for the other directions. So our values are between -1 and +1 for both x and y, and I'd like to use those to blend between animations in our flying blend space. So we need to change the axis range of values for both horizontal and vertical, and we need to change their names as well. Horizontal is going to be input underscore x, and my vertical axis, if I expand that, I'm going to rename this to input underscore y. And I need to change their minimum and maximum values. Minimum will be -1, maximum will be +1, and that will be for both x and y. Minimum -1, maximum +1. And we can see on our grid here that input x goes from -1 to 1, and input y goes from -1 to 1. And I want to see what it looks like when we blend between our flying animations. When we have no input, when those values are 0, I want to be in the idle animation. I'm going to find my fly idle, A kicks fly idle. I'm going to bring it in and hold shift so I can snap it to the grid, and I'm going to put it right there in the middle. And we can see that this is what kicks looks like in the fly idle animation. But remember, if we go back and press play and we start going to the right, our x value is going to be +1. And if we go to the left, our x value is -1. So back in my blend space, when my x value is +1, I want to be flying to the right. So I'm going to use A kicks fly right and hold shift and snap it right there. And if I hold down Control and drag my mouse, I can see the blend from fly idle to fly right. And it looks like kicks is leaning to the left, but we're facing kicks head on. If we hold Control and left click and rotate around, we'll see that this is leaning to the right, which means when x is -1, we want to be leaning to the left. So I'm going to use kicks fly left and snap it to -1. And we can now see kicks blending between these animations. Now we also want to use the y-axis, input y. So when the y value is +1, we'll be flying forward. So I'm going to drag in A kicks fly forward, snap it up there to the top, and I'm going to get A kicks fly backward and snap it down here to the bottom. And now I can hold Control and blend between all of these animations based on both x and y values. So that allows us to have a two-dimensional blend between all 5 of these animations. So now we need to use this blend space in our animation blueprint. Now I mentioned that I like my animation blueprint to be next to my kicks character in my folder structure, but blend spaces can go into the animations folder in assets. So I'm going to expand assets, go to kicks, and there's my animations folder. I want to bring those blend spaces in here. So in the kicks folder, I'm going to select both of these, drag them into content, kicks, animations, and I'm going to select move here. And that way our animation assets are not cluttering our kicks folder and blueprints. I'm okay with ABP because it is a blueprint, but those blend spaces are not blueprints, they're assets. So they can go into the assets folder. Okay, so we have a blend space. Let's use it in our animation blueprint. Now I'm going to go out to my anim graph, and I'd like a state machine for my blend space to go in. So I'm going to right click, make a new state machine, and call this flying. And I'm just going to plug it straight into my output pose. So for now, we'll just see the flying state machine. And in the flying state machine, I'm going to drag in my blend space, BS flying. I'm going to rename this state to flying and hook it up to the entry node. And if I go into this state, I see that we have the BS flying blend space. All we need is our input X and input Y values. So we need a way to access that data, our input action value. In other words, if we go to Kix player controller and go to IA move here, this action value is data that our animation blueprint needs to have. So how is our animation blueprint going to get it? Well, let's see what our animation blueprint has already in our event graph. In our event graph, we have our store essential variables. And here we can see we're storing our character and our character movement component. Now, we specifically need input from our IA move input action. We need this action value. And this exists on the player controller class, but it's also accessible on the character as well. As we've seen, we can go to our character and implement IA move or the other input actions separately here, and we can access that action value here as well. So the question is, where are we going to store that data, and what's the easiest way to access it here in ABP Kix, particularly without having our animation blueprint depend on specific classes like BP Kix or BP player controller? Well, one way is to use an interface function. We know that BP Kix already implements the Jetpack interface, so we can create a function on the Jetpack interface for retrieving that movement input. I'll show you what I mean. Let's go into Blueprints, Interfaces, BPI Jetpack, and let's add a new function here called getMoveInput. And getMoveInput can have a return value, an output, and this output can be a vector 2D. So make sure to choose vector 2D with the blue icon, not vector 2D array. So if we choose vector 2D, let's call this output input action value. This is the input action value, and we're going to implement this function on BP Kix. By double-clicking on it in the interfaces, we have a function instead of an event because we have a return node. And what we can do is access IA move from here. We have the enhanced action values. And this Blueprint Pure node returns the current value of IA move. So now we have an interface function that returns this value implemented on BP Kix. So now in our animation blueprint, we can access our character and call that function that we just created called getMoveInput. So let's go back to the event graph and find our function where we're updating our animation variables. Let's go into that. And from here, we can access our character and call the interface function getMoveInput. And we'll hook this up to our sequence. And this getMoveInput gets that input action value. We're going to go ahead and promote this to a variable, and we'll call this IA move input action value. And now we have this value, and we can access it to drive our blend space. So let's go back into our flying state where we have input X and input Y. And if you can't find this, just go back out to the anim graph, double-click the flying state machine, and double-click the flying state. And we can now use IA move input action value. Let's get it. And all we need to do is right-click on the output, split the struct pin, and we have access to X. We can plug that into the blend space input X, and we have access to the Y, which can go into input Y. I can highlight my nodes, press Q to straighten them out, and we now have our blend space being driven directly by that input action value that we're accessing through an interface function call in our update animation variables function. And by the way, I can simply comment this part here. This can say get IA move input action value. I can give it a reroute node right there, as I like to do. That's my personal style. And I can give this a color. I'll let it be blue. And I'll check show bubble when zoomed. And we now have a nice commented section of code. So now that we're driving our pose with our flying state machine, as we can see here, we're no longer using locomotion, so this won't really make sense when we're just on the ground. But what we can do is we can activate our thrusters, and then we can move left, right, forward, and backward. And with our keyboard keys, it's kind of jumpy, so it doesn't look the best. But with our console controller, we blend quite nicely. So that does look nice. So for the console, this looks pretty good. But for the keyboard keys, we're just snapping our values to 1 and -1 and then back to 0 very rapidly. So if we want our animations to blend a little bit more smoothly, take a little bit more time to blend to the targets on the graph, we can take our BS Flying blend space and we can change the smoothing time. The larger the value of smoothing time, the longer it'll take to blend. So we can try a value of 0.2 for our horizontal axis, and we can try a value of 0.2 for the vertical axis. Let's see what that looks like by engaging in our thrusters. And we now have a nice blending of the animations. They're not snapping anymore. Okay, so the last thing to do is to use our flying state machine when we're actually flying, and use our other state machine, locomotion, when we're not flying. Now, we can do this in one of two ways. We can create another state machine and blend between two states and use state machines inside of it, or we can blend poses. Remember, we had blend poses by bool. That's one type of blend poses node, but there's other blend poses that blend by another data type called an enum. Enum is a data type that has a green color, and we can see that by going into Kix Player Controller and finding IA Jetpack, and in Start Jetpack, remember we have Start Movement Mode Flying. If we go into that, we'll see that the Set Movement Mode function takes in a green input for the movement mode, and notice its type is eMovement Mode Enum. Enum stands for enumeration, and enums have several possible values. We'll learn more about enums when we create our own later, but we can access the movement mode as an enum from the movement component. So in our animation blueprint, we can right-click, we can blend poses by, and we can find the eMovement mode, and there's a blend poses by eMovement mode. And what this does is it takes in a value for this enum and gives us the ability to blend between different poses based on the value of that enum. So I'm going to hold Alt and break this wire, and our output pose will now get this animation pose from the blend poses node, and we can add input pose pins for the different possible values of the eMovement Mode enum type by right-clicking and adding a pin. At the bottom, we have the different types. So I'm going to add the movement modes that we're interested in, namely walking, and now we have a walking pose. And I'll also right-click and add flying. We'll have the flying pose, but also notice that there's a falling movement mode. So that's a separate movement mode from walking. So we need the falling pose as well. And our falling pose is going to get our locomotion state machine just like our walking pose. So really, I want flying to be last. So I'm going to right-click on falling pose, remove that pose, right-click on flying pose, remove that pose, and right-click on the node and add falling right after walking, and then we'll have flying last. And the default pose is what will be returned by this node if our enum value passed in is something that's not covered here. So we have a couple things to do. One is we need to pass in an enum value to this node so it knows which pose to blend to. And next we need to hook up poses to the inputs. So first, let's get our movement mode enum. And we can do that by going back to our event graph, back to update animation variables, and we can get our character movement component here, So I'm going to get our character movement variable, and we can get the movement mode from this with get movement mode. This gets us the movement mode enum, which we can promote to a variable here, not local, and we can call this simply movement mode. And we need this hooked up to our sequence. So we'll hook this up. I'll go ahead and give it a reroute, comment it, and say store movement mode. I'm going to set the comment color to blue, show bubble when zoomed, and we now have the movement mode as an enum value. And we can use that back in our anim graph by plugging it into blend poses by E movement mode. Here's our movement mode. We'll hook it in, and the pose we get returned is one of these poses passed in depending on the movement mode. And if the movement mode is not one of these walking, falling, or flying, then we get the default pose. But we don't expect to get the default pose. We expect to get one of these because we'll always be in walking, falling, or flying. So we could take our flying state machine and plug it in to flying pose. And we could take our locomotion state machine and plug it in to walking pose. But there's a problem. We can't plug it into both. If I plug it into falling pose, then it breaks the pin to walking pose. So how do we use the same pose for two different nodes? Well, to do that, we can take our locomotion state machine. I'm going to break that wire. And we can cache it. This is like storing it in a variable, but this is for animation poses. What we do is we drag off, we type cache, C-A-C-H-E, and we select new save cached pose. And this caches the pose for this particular frame from this locomotion state machine. So I'm going to call this cached underscore locomotion. And we can use this in multiple inputs by right-clicking and searching for use cached pose cached locomotion. And we can hook that into walking, and we can duplicate the node with Control D and hook the duplicate into the falling pose. So now we're blending between these poses based on our movement mode enum. Now, if movement mode is not walking, falling, or flying, we'll get default pose, which doesn't have a pose hooked in. If we compile, we get a note that says default pose was visible but ignored, and that would just mean that Kix would be stuck in this A pose here. If you really wanted, you can hook up another copy of the cache locomotion into default, but we'll never get default. If we do, that's a problem that we should come in and fix. So anyway, we can now blend poses based on our movement mode. So let's go back and make sure that we can run around on the ground, which we can. And we can use our jetpack, which now makes us fly and use those flying animations, which is looking great. Now we can remove that pesky print string, which we added to Kix player controller in our event graph right here for IA move. I'm going to go ahead and delete that. And now we have some really great movement, especially when we're using a console controller. As you can see, things are nice and smooth. We can walk, we can run, we can jump, and we can use our jetpack. And as soon as we stop using the jetpack, we fall. And if I'm facing Kix with my camera looking behind Kix, and I start my jetpack, we get a smooth transition. Kix will rotate to face our controller rotation like this. So it doesn't just snap towards the control rotation, which is nice. And our blend space 2D is looking quite good. Everything is looking really, really good. This is great. Excellent job. And I'll see you in the next video. Welcome back. So we're blending between two state machines. We have locomotion. If we go back and take a look at our anim graph, we have our locomotion state machine, which is cached, and we're using that. But we also have flying, and we're using that when our movement mode is in flying. And I mentioned in the last video that this is one way to blend between animations, and another way is to use state machines, like we did in our locomotion state machine. We're blending between different states here, depending on transition rules. Now, blending poses by Boolean or by enums, such as the movement mode, that's a legitimate way to do it. But in general, I like to use state machines when we have states, right? We have a state when our thrusters are not active, and another state when our thrusters are active. Basically, our movement mode determines that. So I personally would just like to have an overall state machine that blends between these two based on that movement mode using transition rules. And that keeps my anim graph a little bit more under control. Just like blueprint event graphs, we don't want our anim graph to get too complex. So I'm going to make a new state machine. And this will be for overall movement. So I'm going to call this movement. And instead of blending poses with our movement mode, I'm just going to go ahead and delete that node, delete movement mode, and just bring movement up and hook that into my output pose. And in movement, I'm going to have two states. One will be for when our thrusters are active and one for when they're not active. So I'm going to add a state called thrusters not active. And I'll add another state, I'll bring it up this way, called thrusters active. Now, what will go into each state is another state machine. If I go back to my anim graph, I have two state machines. I have locomotion and I have flying. I'm going to go ahead and just delete these use cached pose nodes for now. Now, I can use these state machines inside of other state machines, such as movement. They just have to go inside of a state in the state machine. And they have to be cached in order to do that. Now, we cached our locomotion state machine. It's called cached locomotion. I can use cached locomotion inside of a state in another state machine. That's going to be for thrusters not active. I'm going to right-click, search for cached pose, and use cached locomotion here. But in my other state, thrusters active, I want to use my flying state machine. So for that reason, I'm going to cache this pose by using new save cached pose, and I'm going to call this cached flying. So now I've cached both of them. I'll go ahead and bring them here so everything looks neat. And in my movement state machine, I'll go into thrusters active and use my cached pose with use cached pose. And look, now I have cached flying. I'll hook that in there. And back in my movement state machine, I just need to decide when to go from thrusters not active to thrusters active. And that's going to be depending on my movement mode enum. When I'm going from thrusters not active to thrusters active, that's going to be when my movement mode is flying. So I'm going to implement my transition rule by double-clicking and going into it, and I'm going to get my movement mode enum, and I need to check to see if this value is equal to flying. And I can check an enum's value by dragging off and typing the double equal sign. Now, there's two options, and we want the one for enums specifically. So if I choose equal enum, I now have this comparison node that returns a Boolean that will be true if movement mode is equal to whatever I select here. And I want to select flying, so we're going to hook this up, and the Boolean will be true if movement mode is flying and false otherwise. So this allows us to transition when movement mode is flying. And that goes from thrusters not active to thrusters active. But we also need to transition back the other way. And we can drag a transition from thrusters active to thrusters not active and get another transition rule. So we need to implement this transition rule, and this will also depend on movement mode. If we get movement mode, we need to see if it's one of two states. We need to see if it's walking or flying. So let's drag off and get an equal enum node and first check to see if it's walking. But we'll duplicate these nodes and the second one will check to see if we're falling. If either one of these is true, we want to enter the transition back to thrusters not active. So what we need is to combine these into a node that will be true when either one of them is true, but will be false if both of them are false. And this is what the OR Boolean node is for. This is kind of like the AND Boolean node, except it's a little bit different. With AND, we only get true if both the first and the second inputs are true. With OR, we get true if either the first or the second is true. They don't have to both be true to get a true. Only one of them needs to be true. And that's what we want. If walking or falling, we want to transition, right? So now we have our transition rule going back to thrusters not active. And this may seem a little more complicated than blending poses by enum, but it results in a neater animation graph. Things are a lot easier to see. We have two states, locomotion and flying, and our movement blends between locomotion and flying. In fact, we don't have to make these names tied to the thrusters. We can just associate the names with those state machines. Thrusters not active, that's the locomotion state machine. And thrusters active, that's the flying state machine, right? So this might actually seem a little bit more intuitive because we know that we're using those cached state machines in there. And notice every time we go into a state and out of a state, we get a new tab for it up here. So this can get quite out of hand. I'm going to right click and close tabs to the right and just close all but my anim graph here and my event graph. So things are not so crazy. And as we always should, when we make these changes, we should go back and play test. I'm going to test running around, jumping, and flying. That was with keyboard and mouse. And I'll try with the controller. And everything works as expected. So you have nodes like blend poses by bool or blend poses by some enum type, and those are useful when you need them, but you also have the ability to create state machines which can blend between poses depending on transition rules, and sometimes that's what you need. By the way, I closed my anim graph. I can always get it back by going to Animation Graphs default shared group and double-clicking anim graph to get it back. And with that, we now have a nice organized anim graph, and we have walking, jumping, flying. Things are looking great. I'll see you in the next video. Welcome back. Now our jetpack works and it has sounds, but that's the only thing that has sounds. And usually when we run around or simply walk around and jump and land, we typically expect to hear some kind of footstep sound or impact sound. So in this video, we're going to handle implementing sounds for footsteps for our character. Now, when we want to play a sound and have that sound associated with a given animation, such as a walk cycle or a run cycle, we can make use of animation notifies. We do that by going to our animations. So in our case, we go to Assets, Kicks, Animations, and we find the animation that we would like to play a sound at a specific point. So in our case, we can start with Kicks Walk Forward. So here in Kicks Walk Forward, we want to play a sound when those feet hit the ground. So what we can do is we can wait until the foot is just about on the ground, in our case, right here towards the middle. And notice in our Kicks Walk Forward tab, if we expand this to show more room, we have a Notifies section with its own dropdown and one Notify underneath. It's called Footsteps, but you can click on this to rename it. By default, an animation will have one as the name for this first option, but this particular animation asset has Footsteps, as the label for it. This is called a track, specifically a notify track. A notify track allows us to have notifies for our animation, which are simply markers in the animation that determine that something should happen. And if we need a lot of notifies, more than one track can handle, we can click the drop down that says track and insert a notify track to get another one. And now we have 2 notify tracks, and I can remove that notify track by choosing track, remove notify track. Now we add a notify to a notify track by right-clicking on the track, and we have a number of options. We want to add a notify, and we can create custom notifies, or we can use notifies that are built into the engine, and playing a sound is a common enough notify to be built into the engine. So we can simply use the built-in notify, play sound. If we select that, we now have a marker, a little flag, and we can click and drag this around on the notify track, and we can even hold shift while we're dragging it around to bring that playhead with us, and we can see that the animation scrubs through to that point in time. So for this, I'm looking at my left foot, the one that's farthest away from me. I'm going to go to right where it's about touching the ground here, and that's where I want my play sound notify. And with my play sound notify selected, in the details panel, I can select what sound to play. Now we have sound assets for kicks. If we go to Assets, Sounds, there's a Footsteps folder, and we have this MS Footsteps Metasound. It's using all these sound waves and choosing one at random and randomizing the pitch a little bit. So I'd like to use this MS Footsteps. I'm going to select it, and then up here on the details panel, I'm going to click on this left arrow, and that will insert that MS Footsteps so that my sound is set to that. And we can hear this when we play the animation. Now I want another one where my other foot is touching the ground, so I'm going to scrub to that part, right-click, add notify, choose play sound, and I automatically get MS Footsteps because that's what I have selected in my content drawer now. And if I press play, I can listen to how this sounds. So I'm probably going to adjust the positions until things sound natural. All right. Now these sounds are attached to this animation asset. So when we play this animation, even in a blend space, we're going to hear those footstep sounds. We can go back into our level and we can play test and see how this sounds. I'm going to use my controller so I can walk. And I can hear the sounds. Now if I speed up, now I'm playing the running animation, and we don't have any sound notifies on that animation, so we don't get those sound notifies. But varying my speed, at some point I'll be playing a mixture of walking and running animations. So past a certain point, when we're playing more of the running animation than we're playing the walking animation, we stop hearing the sounds because we don't have those notifies on the running animation. So we need to add them to the running animation as well. And that's going to be our kicks run forward animation. We can double click it in the asset browser, and we can add notifies to the footsteps notify track here. So I'm going to add the notifies, and I'm going to tweak their locations by playing the animation and listening to how it feels, and I'm going to time lapse this process. Okay, so now that I have footstep notifies on my run forward animation, I can play test in the level by walking and running. Perfect. So now that we have run and walk footstep sounds, we need to play a sound when we jump and when we land. Now, the landing is going to be pretty easy. I'm just going to use a couple of footstep sounds. So I'm going to go to Kicks Animations and find my landing animation. That's going to be jump end. And I can remind myself by going to ABP Kicks, going to Locomotion, going to jump end, and there it is. And I could double click that to open it as well. So here, I want to play a couple of footstep sounds. I want to play one right here, and probably another one about right here. So I'm going to add a notify here. Notice my notifies tracks. There are 2 of them this time, and they're not named, but we can click on them to name them. I'm going to call this one Footsteps 1, and I'll call this one Footsteps 2. And on Footsteps 1, we're going to add a sound notify and select MS Footsteps for it. And for right about here, I'm going to add another one and select MS Footsteps for this. And now we can play it and we can adjust things. And we can, of course, test in the game. And I think that sounds great. Now we just need our jump start sound, so we'll go to jump start, and we'll add a sound at just about when we leave the ground. Remember, we're not playing this whole animation, we're cutting off the beginning of it, so I need to make sure that this notify is late enough. I'm going to put it right about here. I'm going to add a notify play sound, and this one can use a jump start sound. Let's see if we have one. We'll go to Assets, Sounds, Jump, and here's an MS jump sound. I'm going to select it and hit the left arrow up here so we have it on our jump animation. And we can go into the world and play test. And I think I can move it a little bit earlier in the animation. But we do need to make sure we get that animation sound notify playing, so let's play test. And that sounds pretty good. And we even get that sound playing when we start that falling animation. And I'm actually okay with that. I think it sounds great. All right, so now we have footstep sounds. Things are not so silent anymore. And we're ready to move on. Great job. I'll see you in the next video. Welcome back. Now that we have sounds, things are looking great, and we have a jetpack. But the problem I see with this jetpack is we can use it anytime we want. There is no restriction. We can always use it. There's nothing stopping us from just always flying all the time. Now, one way to restrict it in a game would be to use the concept of jet fuel. If we have fuel for our jetpacks, then we have to use it sparingly, and then perhaps seek out jet fuel to refill our fuel in order to use it, and that can be a valuable platformer mechanic when we have the concept of scarcity of our fuel resource. So I'd like to implement fuel in this video. Now, because our jetpack is closely tied to our character, it's literally attached to our character's back, I want to handle jet fuel here on our character, as we're handling our visual and sound effects on the character when we start and stop the jetpack. So I'd like to have a variable for fuel on our character. So we're going to click Add Variable, and we're going to add a jet fuel member variable, and this is going to be a float. I'm going to compile and set it to its default value, and I'll set it to about 50. This is an arbitrary value for now, but now we have fuel. Now, as we're setting the fuel, changing it, subtracting from it, adding to it, I want to have a maximum amount of fuel that we can have. So jet fuel is actually going to be our current value, but we can also have a max value that we can never put jet fuel above. So I'm going to add another variable called max jet fuel. And this is common when it comes to attributes and values that keep track of characteristics of particular game objects. We usually have a current value and a maximum value. And I'd like to drain that jet fuel at a specific rate. So I'm going to have yet another variable, and this will be jet fuel drain rate. So when we're using our jet fuel, we're going to drain it at a specific rate every frame, and the higher this value is, the faster we'll drain that jet fuel. So we can compile and give max jet fuel a default value. I'll go ahead and give it 50, and jet fuel drain rate can also have a default value. And for now, I'm just going to set it to about 5, but we'll see how it feels. Now we need a way to drain our jet fuel. In other words, we could use a function here on kicks that we can call every frame while the thrusters are active, and kicks will use that function to drain a little bit of the jet fuel. Now, our jetpack is closely tied to input, and here on the kicks player controller, while our IA jetpack is triggered, we're applying thrust input, but we can also apply fuel consumption on the character. We can add a BPI jetpack interface function for that. So I'm going to add another function to BPI jetpack, and I'm going to call this drain jet fuel. And this will be for a single frame. We'll call this repeatedly every frame while the jetpack is actively being used on Kicks player controller. Just like apply thrust input, we'll be calling this function every frame as well. So what we'll do is we'll get our controlled character, we'll get a validated get node for it, and we'll use the interface function, but we haven't implemented it on BP Kicks just yet. So we'll go to our interfaces in BP Kicks and implement drain jet fuel. And what we want to do is set our jet fuel variable to something. So we're going to get jet fuel and get a set node for it. And we need to set it equal to some value, right? Well, we need to perform a calculation so that we know what to set jet fuel to. I want to set it equal to its current value minus our drain rate. So I'm going to use a subtract node, but I don't want to use jet fuel drain rate here by itself. I want to scale this by delta time so we have frame rate independence. So I'm going to take jet fuel drain rate and multiply it by get world delta seconds. And now we have a frame rate independent system, and this will be what we subtract from jet fuel. So we're performing a calculation where we subtract our amount to drain this frame from jet fuel, and we're going to update jet fuel with that amount. Now, here's the thing though. What if this calculation results in a negative value? We never want jet fuel to be negative. We don't want it to go past 0. So what we can do is make sure that this value that we're setting will never be less than 0. We can do that with a clamp node. We can take our value, drag off of it, search for clamp, and we want a clamp float node. So if we select clamp float, it takes in the value that we want to clamp, and it has minimum and maximum limits here. We never want it to go below 0, so our minimum will be 0. And our maximum should be our max jet fuel value. So whenever we clamp our jet fuel, we can use max jet fuel for the maximum of our clamp. And this value we can simply use to set our jet fuel. So event drain jet fuel is going to update our jet fuel by subtracting the amount we need to subtract just for one frame. scaled by delta time. And this can be its own function. We can collapse it to a function and call it something like consume jet fuel for frame. That way it's clear that this is jet fuel consumed for one single frame. We can even put this function in its own category. I'm going to put it in the category of jet fuel. And I'm also going to put those variables in their own category as well. I'm going to select jet fuel, put it in the jet fuel category, max jet fuel as well, and jet fuel drain rate as well. So these are in their own jet fuel category, just like consume jet fuel for frame. And now we can call this in our Kix player controller when our jetpack is active. So we'll take our controlled character and call drain jet fuel like so. Now I'd like to simply put these two nodes in their own function, and we'll call this drain jet fuel. So now we're doing two things on triggered, applying thrust input and draining jet fuel. So the next thing we can do is test out our jet fuel system by watching the value of jet fuel as we're draining it. Now to do that, I have to take my jet fuel and open the eye icon to make it instance editable. And that way, if we go in and press play and we find BP Kix here in the outliner and select it, then we can look at its details panel and find that jet fuel value. If I scroll down to the jet fuel section, I can see it there. It's set to 50, and I can drain some fuel and see if that value changes. And there it goes. So we're draining our jet fuel, and it's updating. But there's a problem. What happens when our jet fuel reaches 0? Well, let's find out. Okay, there it goes. It's 0, but I can still use my jetpack. So we're not enforcing any restriction on the use of our jetpack. We can still use it when our jet fuel is 0. So we need to enforce the requirement that our jet fuel has to be greater than 0 in order to use our jetpacks. And we're going to enforce that in the next video. Excellent job, and I'll see you soon. Welcome back. So we now have jet fuel, and our jet fuel starts at 50, and if we're using our jetpack, it drains all the way down to 0, but we can still use our jetpack even if we have 0 jet fuel. And to make this easier to test, I'm going to go to BP Kix and set my jet fuel drain rate to a higher value, such as 10, and that way we can reach 0 much faster. I can press play, I can select BP Kix in my outliner, find jet fuel, and use my jet. And as we drain our jet fuel, we can see it, and when it goes down to 0, I should stop using my jetpack, right? So in this video, we're going to enforce that jet fuel requirement. Essentially, we want to enforce a couple things. For one, if we look at our Kix player controller, we have our input action IA jetpack, right? And what I want is when we try to start the jetpack, we check, do we have jet fuel? If we don't start the jetpack. And then another thing I want to make sure is while we're using the jetpack, if all of a sudden our jet fuel goes down to 0, we want to stop the jetpack, and we don't want to keep triggering functionality for the jetpack. We don't want to keep applying thrust input. We don't want to drain the jet fuel, and we want all the things that happen when we stop, such as sounds and effects, to trigger as well. And this is going to be a challenge for you. I want you to enforce jet fuel as a requirement for using the jetpack. Make it so that we cannot start the jetpack if jet fuel is 0. And also, I'd like you to stop the jetpack as soon as the jet fuel reaches 0. So pause the video and give this a try. Okay, so the way that I'd like to implement this is I'd like to easily check to see if our jet fuel is 0 right here on the player controller. And to make that easy, I'd like to have an interface function that can return a Boolean for whether or not we have jet fuel. So I'm going to make a function on BPI Jetpack, and this is going to be called has fuel. And it's going to have a return value, an output of Boolean type, and this is going to be called has fuel. And we're going to implement this on BP Kicks. So on BP Kicks, we're going to implement has fuel, and all we need to do is check our jet fuel and see if it's less than or equal to 0. It should never be less than, but I'll have less than or equal just as a safeguard. And this returns a Boolean. That's what has fuel is going to return. So now that BP Kicks has this has fuel bool returning function, we can call this from Kicks player controller. We can call it first when trying to start the jetpack. So we can have a branch here, and our Boolean condition can be the value of has fuel when we call that interface function. So we can get our controlled character, and we can call has fuel. And this function will return a Boolean that we can pass into the branch. And if has fuel is false, we'll never go into the true case. But if we do have fuel, then we can start the jetpack. So this prevents us from ever starting the jetpack if we don't have jet fuel. But we also need to check this as we're triggering this IA jetpack, because we don't want to continue applying thrust input or draining jet fuel if we don't have fuel. If the fuel runs out, we want to call stop jetpack. So we need to have this same branch right here for the triggered case. So I'm going to paste it there and hook it up. And if we do have fuel, we can do what we were doing before. But if we don't have fuel, we want to call stop jetpack. So I'm going to paste that there. And now our nodes are looking a little bit more complicated, right? So we'll need to clean this up just a little bit. So I'm going to go ahead and put a reroute node there. And I'll go ahead and put a reroute node on this one as well. And what can really help is some comments. So we'll put a comment around these nodes. And we'll say, if controlled character has fuel, apply thrust and drain fuel. Otherwise, stop jetpack. And here in the player controller, I'm going to give this a nice dark red color and save that color here. Now for started, we'll give this its own comment, and we'll just say, if controlled character has fuel, start jetpack. And I'd like this to have the same red color. We'll go ahead and show bubbles when zoomed. And stop jetpack is self-explanatory, but I'll still say stop jetpack when input complete. Like so. And this will also be a red comment showing the bubble. Okay. Now we can also take these nodes and move them up next to our other input nodes here. And what we can do is put all of the input functions in a single comment. So these ones are IA look, move, and jump. This one's IA jetpack, but all of these input functions can go in their own comment called, and this one can have its own comment color. We'll go ahead and give it something like yellow. If you think that's an awful color, by all means, use a different one. But now we have order. I actually really don't like the yellow. I'm going to make it more dark blue. And by the way, to get rid of colors here, just drag them to the trash can. Okay. So now we have input handled. And organize this how you wish. If you like, put them any which way you want them until you feel they're nice and organized. I actually may get rid of these bubbles because they're getting in my way here. Without them, I can have a much more compact graph, which I think I kind of like. Okay. And it's this big, large comment that I can show the bubble for, like so. And now things are looking great. Okay, so now that we've organized this, let's make sure that we're enforcing that jet fuel requirement properly. And to speed things up, I'm going to set my jet fuel drain rate to 20. So that way we'll drain our jet fuel really quickly. And I'll find BP Kicks, see its jet fuel in the details panel, and I'll use my jetpack. And it looks like I cannot use my jetpack. So we are failing to use the jetpack. So let's see why. As soon as we've started our input, we're getting our controlled character, seeing if it has fuel. And if we do have fuel, we're starting the jetpack. It looks like we're never actually starting it. So I'm going to go back to BP Kicks and has fuel. Oh, I see it. I made a mistake. Has fuel will return true only if jet fuel is less than or equal to 0. That's actually the opposite of what we want. We want it to be true when jet fuel is actually greater than 0, right? You probably saw that at the time and were really confused. You might even went over to the Q&A section and posted a question. Stephen, shouldn't this be greater than? And you'd be right. This should be greater than. I make mistakes from time to time as well. But now that that's fixed, we should be able to use our jet fuel. Let's see if we can look at our jet fuel and use our jets. And as soon as it hits 0, oh, we stopped it, but we spammed our stopping sound. That didn't sound good. So let's go ahead and diagnose that. Let's take a look at our nodes here. When triggered, we check to see if we have jet fuel, and if not, we call stop jetpack. But this gets triggered as long as we're holding that input down, doesn't it? So really, we don't want to stop the jetpack every single frame. We just want to do that once, don't we? Well, there's a blueprint node that allows us to do things once. It's called a do once node. This will let us only stop the jetpack once, even if we call this multiple times. So as is, we can go ahead and press play and drain our jet fuel and keep it held down. And we only get that ending sound once, except we get it one more time when we release that input, which would be on completed. And that's because right here on completed, we're calling stop jetpack again. So really, we need to know if our jetpack is actually being active before we go and stop it. But another thing is, we want to be able to stop that jetpack multiple times. So how do we actually allow this do once to let us call stop jetpack from here again? Well, we do that by executing the reset input pin. And we can do that when we start the jetpack. As soon as we start it, we can reset our do once node. Now, we could do that by bringing the start jetpack output pin and hooking it up here, or we could make a custom event here called reset jetpack do once, like this, custom event, reset jetpack do once. And we can use this to reset the do once and just call that here, reset jetpack do once. This is a little bit cleaner as I don't really like to cross my wires that much, especially from one comment block to another. So I find this to be a little bit cleaner. But we also need to make sure that our jetpack is currently on before we stop it, don't we? Well, that's easy. When we start our jetpack, if we have fuel, here in Start Jetpack, we can keep track of whether the jetpack is actually on. So here in Start Jetpack, we can set a Boolean value. We can add one. We can add a variable called jetpack active, set its variable type to Boolean, and we can set it here in Start Jetpack to true. and we only want to stop the jetpack if jetpack active is true. So back out in our event graph, before we stop the jetpack, we can use a branch and check jetpack active, and only if the jetpack is active will we stop it. So we're going to plug up completed to the branch and the true to stop jetpack here. There we go. But we're setting jetpack active when we start the jetpack on started here, when we call start jetpack. But if we stop the jetpack, we need to set jetpack active to false. So here in stop jetpack, we can set jetpack active to false. We'll do it first thing, set jetpack active to false. Okay, so now let's recap on what we're doing. When started, we check if our controlled character has fuel. If it does, we start the jetpack. In start jetpack, we set jetpack active to true. Then every frame as we're holding that input down, we're continuously checking if the controlled character still has fuel. And if it does, we apply thrust input and drain the jet fuel. And if it does not, we use the do once to call stop jetpack. And it'll only trigger once, even though we'll be reaching this flow of execution multiple times as long as we still have the button held down. And we won't be able to call this stop jetpack here until reset is executed. And that's not going to happen until started happens again. That's when we call reset jetpack do once. And finally, when completed, if the jetpack is still active, we'll call stop jetpack. That way we don't call stop jetpack if the jetpack is not currently active. So let's play test this. We'll use our jetpack until it's used up. And then it stops. And if I release the jetpack button, I do not hear that stopping sound. And the final thing we can do to test out whether everything works properly is we can reset our jet fuel back to its maximum once we've run out. So to do that, I'm just going to go to my event graph on stop jetpack. And as soon as we stop the jetpack, I'm going to add to my jet fuel. So I'm going to use a set node, and I'm just going to set it back to its maximum. We'll just set it to max jet fuel. This is for testing purposes. We're going to remove this as soon as we're done testing. So I'm going to put it in a testing comment here. And we can go ahead and play test. We'll select BP Kicks, take a look at its jet fuel amount, and we're going to drain it down to 0. As soon as that happened, our jet fuel was reset, and we can try using it again. And it seems to work. And just for testing purposes, I'd like to place a delay before we reset our jet fuel, just to make sure that we're not going to keep draining jet fuel after we've stopped it. So I'm going to add a 4-second delay after we've stopped our jetpack before we reset our jet fuel. Let's play test. We'll drain our jet fuel till it's empty. There we go. And 4 seconds later, we have jet fuel again. We can stop using it. But 4 seconds later, it gets refilled. And of course, if we use it all up, we stop and we can't use it again, not until we have jet fuel, at which point we can use it again. So jet fuel is working. We can remove these testing nodes, and we now have jet fuel implemented. But the problem is, when we're actually playing the game, we're not going to be able to see that jet fuel value. We can see it here in the editor because we can select BP Kicks, and we have a blueprint exposed jet fuel value. But when we're actually playing the game, we can't really see it. That's what HUD elements are for. HUD stands for Heads Up Display, and HUD is things like health bars, or in the case of jet fuel, a fuel bar. And that's something that we're going to want to be able to see in the game. So that's going to be one of the next things we implement. So excellent job, and I'll see you in the next video. Welcome back. Now we have fuel, right? It's a variable on Kix. It's called jet fuel, and we're enforcing the requirement to have fuel in order to use the jetpack. So we have this precious resource, and we can use it. It can run out, but once it's gone, and we can't refill it. Sure, we could set its value back to its max value like we did for testing, but what about in the game? For the game, we need a way to get more jet fuel. Now, sure, we can't see our level of fuel. We're going to need some HUD elements for that to show it as a fuel bar. We'll get to that. But first, I'd like to create a way to replenish our fuel. We need a pickup of sorts. Now, in order to have a pickup, we need assets. I'd like to have something a little more exciting than some basic piece of geometry that we make in modeling mode. Sure, we could go to modeling mode, select sphere and make a sphere and call that our pickup, but that's boring. I'd like to use something a little bit better and find some free assets that fit the style of Kix. And believe it or not, there exists a free sample project that contains a ton of stylized assets that just so happen to work with Kix. So let's find it. I'm going to open my Epic Games Launcher, go to the Samples tab, and we're going to find the sample called StackoBot. Here it is. It's in the Samples tab. If we click on it, we'll see that StackoBot is a full blueprint project. It contains a lot of examples of how to do things in Blueprint, and it also contains a lot of assets that we can migrate to our project. So if this looks like something you'd like to use, you can follow along with me. Otherwise, you can use any assets that you like, but StackoBot has some assets that I'd like to use. And in order to use it, I have to create a StackoBot project. So I'm going to click on Create Project and find a folder that I'd like to put this project on. So I'll go ahead and select the folder I want this in, and I'm going to let it be called StackoBot and click on Create. Now, once that's finished being created, I can close my Epic Games Launcher and find my StackoBot project and simply open it up. I'm going to double click that U project. Here it is. And if you like, play around with this project all you want. Maybe look at some of the blueprints. You know how to open those blueprint assets up by simply right-clicking on an object. If it's a blueprint, you can choose Edit for that blueprint. But what I'm interested in is looking at some of the assets that I'd like to migrate over to my project. So it has a content folder with StackoBot, and in StackoBot, there's an environment, and we have a couple of interesting folders. One is modular, that has a lot of environment assets, and we'll probably be using some of those soon. And then we have a props folder, and the one I'm interested in is this one. It's called SM Generic Player Pickup Core. I'm going to double click that to open it up, and here is what it looks like. I find it to be actually very beautiful and simple, and it just so happens to really mesh with my Kix style. So I'm going to migrate this static mesh and all associated assets that it uses, such as the materials, over to my project. And to do that, all I really need to do is right-click on the static mesh, go to Asset Actions, and choose Migrate. Now notice when I do that, I'm actually migrating all these files because the materials used by this asset also use textures. So we have materials and textures, and there's other folders with other files that all are being used by this one static mesh, either directly or indirectly. So I'm just going to allow it to migrate all these assets over. So I'm going to click on OK, and I'm going to find my project, and I have to select my content folder and click Select Folder. And once that's done, I can close StackoBot for now, I'll save it and come back to it later, but for now I'm going to close it, and I'm going to go into my Jetpack project, into content, and there's my StackObot folder. Now, you might be tempted to go in here and rearrange the folder structure and move things around, move this into the assets folder. I'm not going to do any of that because I plan on migrating other assets over to my project in the future, and I'll just keep all the StackObot assets here in the StackObot folder. That makes it a lot more convenient for me. So now that I have this folder, I can go to Environment, into Props, and there's my nice pickup mesh. It looks great, but I want this to be for jet fuel, so I want to alter it just a little bit. And in general, when I alter assets, I always duplicate them so that I don't mess up the original. So I'm going to right-click on the original static mesh, select Duplicate, and call the duplicate SM Jet Fuel. And I'm going to open up the duplicate. I'm first going to close the original, and I'm going to open SM Jet Fuel. So which of these materials is the one that I want to change? I want to change this white one, but I don't know which of these materials is the white part. So what I can do is I can isolate certain materials. If I isolate the first one, I see that material there. If I isolate the second one, it's that interior metal part. And if I isolate the third one, it's the green part, the plastic part. What I want is the MI-Glow material. So this is using an MI-Glow material instance. And if we open that up, we can see that we can adjust the color here by picking one from the color wheel, but I don't want to mess with MI-Glow. I want to make a duplicate of MI-Glow. So I'm going to duplicate it and call this MI Jet Fuel. And I'm going to mess with the jet fuel material instance instead. I'm going to make this a nice yellow color like this, and go back to my static mesh jet fuel and change its material to MI Jet Fuel so it's nice and yellow. And now I have a jet fuel mesh that I can use for a pickup. I'm going to bring that mesh in. I have to browse to it first, and then bring that mesh into my world to see what it looks like. There it is. I can play test and see what it looks like next to Kix. Beautiful. And now all I want to do is be able to pick it up and refuel my jetpack. So we've got some assets. We also have a StackObot project with lots of other assets inside of it, and that's going to come in handy when we want to do some level design. So excellent job. In the next video, we're going to make our jet fuel pickup so that we can pick these up in the world. Excellent job, and I'll see you soon. Welcome back. Now that we have a jet fuel static mesh and it looks good, it's time to make a jet fuel pickup. So I'm going to go ahead and delete that static mesh and close all my tabs for now. And I'm going to create a new actor. So we'll go into our blueprints folder, and I'll make a new folder called pickups. And in the pickups folder, we'll have a new actor class. So we're going to create a blueprint class. This will be based on actor, and we'll call this BP Jet Fuel. So let's open up BP Jet Fuel. Now, jet fuel can be quite simple. We'll need a static mesh component. So we'll add static mesh, and we'll call this fuel mesh. And I'm going to set its static mesh property to SM Jet Fuel. Now we have a jet fuel mesh. Now we can give this jet fuel mesh an overlap callback for when something overlaps with it. But first we need to check out its collision properties. So I'm going to browse to the static mesh jet fuel and see if it has a simple collision. We can go to show, and we'll show that simple collision. And sure enough, it does have a simple collision. It looks like some kind of auto-generated simple collision. But really, this is a lot of polygons for something as simple as pretty much a sphere. In fact, it looks like we have more than one collision hull we have a sphere collision hull there, and we have this other collision hull, which I'm not sure why it's there, but we don't need it. I'm going to hit Control Z to move that sphere back to where it belongs, but I'm going to select this collision hull with all the polygons on it, and I'm going to hit Delete to remove that collision. So now we only have a single collision hull, and it's this sphere shape. In fact, it might actually be a capsule. I believe it actually is. It's a capsule. And spheres and capsules are much simpler when it comes to collision calculations because they don't have polygons, but rather they have a radius. And in the case of a capsule, they have that height as well. And that just involves simpler calculations than with a polygon mesh. So we're just going to have this one simple collision shape, and we also want to take a look at the collision settings. Now, collision complexity is project default, so we know that's simple and complex, and collision presets is block all. Now, that's okay. It's set to block all, which would be what we want for most static meshes, but in the case of jet fuel, we'd like it to overlap with our player-controlled character, in other words, our pawn. And if we want to overlap with the pawn using our simple collision, we're going to want our collision presets for our fuel mesh to be a little bit different. So for one, we're going to need to change collision presets to custom, at least while we're experimenting and getting the proper settings that we need for this jet fuel static mesh. Now, we're going to be using the query system because things like overlap events use the query system and not the physics system. And we won't be applying forces or gravity, so we don't need physics at all. So we can set collision enabled to query only. Now, the object type can be world static. That's totally fine. But we want to ignore all the channels. We don't want any collision interaction with any channel, except, of course, for one channel, and that's the one that our player-controlled character is using, specifically our character's mesh or capsule. We have to make the choice. Do we want to register an overlap interaction when our character's capsule overlaps or when our character's mesh overlaps? And for the simplest and cheapest calculations, we typically use the capsule. If we select our capsule, we'll see that our capsule's collision presets is the pawn preset, which has the collision object type pawn, and we have generate overlap events set to true. Whereas if we select our mesh and take a look at its collision presets, it's set to character mesh, which does have object type pawn, but it has generate overlap events not set to true. So by default, the mesh does not generate overlap events, and that's a good optimization to have because generally our capsule is sufficient enough to generate overlap events. It has simpler geometry, simpler calculations, and better performance. So our SM jet fuel can overlap with the pawn object type, and overlap events will be generated by our capsule on BP kicks because the capsule has a block response to world static. And if the capsule's response to world static is block and the jet fuel mesh response to pawn is overlap, between block and overlap, the least blocking response is overlap, and that's the type of interaction that we'll get. We just need to go into our jet fuel actor, and with our fuel mesh selected, we have to make sure that it has generate overlap events set to true, which it does. And we also want its collision presets not set to block all dynamic. We got that by default when we added the static mesh. We want it set to default, which is going to default to SM jet fuel's collision presets, which ignores everything except the pawn and only uses queries. So now we can simply test out overlap events with jet fuel by going to our event graph. And we have event actor begin overlap for that. We can simply print the name of the other actor with a print string to prove that our overlap event is working. So let's go ahead and browse to this jet fuel asset. We'll drag one into the world and we'll run into it with our character. Let's see what happens. And there's BP Kicks printed to the screen. So we're getting our overlap events, which is perfect. And we're only overlapping with that simple collision shape, that capsule. And this static mesh is set to ignore all object types except for pawn. So we have a nice, optimized and performant system. Now the only problem is our collision presets is set to custom, which is in general not the best practice. We want a collision preset specifically for pickups that only overlap with the pawn. So let's make a pickup collision preset by going to Edit, Project Settings, Engine, Collision, and opening the preset. And we can create a new preset called Pickup. And its collision enabled will be query only. Object type can be world static. And we'll say pickups that only overlap with the pawn. And we'll ignore all collision channels except for pawn. And that response will be overlap. We'll go ahead and accept that. So now we have a new pickup collision preset, and I'd like to actually use that on the jet fuel static mesh component here on the jet fuel blueprint. So I'm going to change its collision presets to pickup here. You might have to compile first before you see it. And then my static mesh component itself can just go back to using the block all collision preset. And that way, the static mesh jet fuel isn't specific to pickups. We can just override those collision settings on the actor at the actor level. So my fuel mesh actor has collision presets set to pickup for its static mesh. And now we have an actor that has a mesh, and our collision presets are properly configured so that our character can overlap with it, and other things will not register overlaps with this particular actor. So now all that's left is to make this jet fuel functional and refill our fuel on kicks, and we'll do that in the next video. I'll see you soon. Welcome back. So we now have an actor for our jet fuel. And we know that our collision settings are configured so that we can overlap with our jet fuel actor's static mesh called fuel mesh, and its collision settings are configured to ignore everything but the pawn object channel. Now we'd like to implement this fuel pickup so that once we overlap with it, we can refill our fuel, or at least refill some of our fuel. So this is going to be a challenge for you. Make your jet fuel pickup functional. Give it a variable for the amount of fuel that it's supposed to refill, and on overlap, refill some of that fuel on the Kicks character and destroy the pickup so that it disappears. Now, I want you to keep in mind that our jet fuel blueprint should not be dependent on the BP Kicks class. I don't want you to use casting. I want you to be more conscious of your dependencies, so try to think of a better approach than simply casting on overlap. Here's a hint: think about interfaces. Pause the video and give this a try. Okay, so in jet fuel on begin overlap, we're going to want to refill some of Kix's fuel. So we're going to add a variable on jet fuel for the fuel amount. We're just going to call it fuel and set it to a float data type, compile, and I'm going to give Kix about 25 when picking up this jet fuel pickup. But the question is, how do we add to Kix's jet fuel without taking the other actor and casting to BP Kix and changing the jet fuel on Kix from here? Well, we can implement a refill interface function on our BPI Jetpack interface. That's what I'd like to do. So I'm going to go ahead and close project settings. I'm going to close the static mesh editor for SM Fuel, and I'm going to go into my blueprint folder, into interfaces, and open BPI Jetpack. and I'm going to add a function to refill fuel. We'll call this refill fuel, and it can have an input that we can pass through for the amount of fuel. I'm going to make it a float and call this fuel amount. And all I need to do is implement this function on bpkicks, and then we can call it from outside of bpkicks. So we're going to go to the My Blueprint panel into the interfaces, and here's refill fuel. If I click on that, or double click rather, I can implement refill fuel, and all I want to do is set jet fuel equal to its current value plus fuel amount. In other words, I'm going to take this fuel amount, use an add node, and add to my current jet fuel, and then simply set my jet fuel amount to this, except there's a problem. What if we go past our max jet fuel? Well, we know that clamping is great for that. So instead of setting this directly like this, we're going to use a clamp float node and clamp this value between a minimum of 0 and a maximum of max jet fuel. So we'll never set jet fuel to a number higher than its max. And we can, of course, collapse these to a neat little function, and we can call this refill fuel. And we can't call this refill fuel because that's the name of an interface function already implemented by Kicks. So we're going to actually call this handle refill fuel. We'll just put a handle on there, and I'll change the input from A to fuel amount. So now we have a function to refill the fuel, and we're going to call this from BP jet fuel, our jet fuel pickup. So in the event graph, we don't need the tick function, we don't need begin play. All we want to do for now is take the other actor and call refill fuel, and we want to pass in the amount of fuel stored on this blueprint called fuel, and we can always change fuel. In fact, we can take fuel and make it instance editable so that we can change it per instance in the world if that's what we want. But what I want is just to verify that our actor begin overlap event is actually refilling our fuel, so we can play test that by picking up some fuel. I'm going to press play. I'm going to select BP kicks. I see the jet fuel is 50. I'm going to spin up some of that fuel. Now my fuel is 14.55. And if I pick this up, now it's 39.55. We've just added some fuel. Now, of course, we need to delete or destroy this actor as soon as we've picked it up. So the last thing to do after we refill the fuel is we can simply call destroy actor. And this fuel actor is going to destroy itself. So let's see how that looks. We'll go ahead and, first of all, let's select BP kicks to see its jet fuel. I have 36 because I already hit the shift key. Now it's down to 28.49. And if I pick this up, I have full jet fuel because adding that 25 would have put me over the max amount, but we clamped it to 50. And now we have jet fuel. Excellent. So we now have a fuel pickup. And if you implemented the solution to this challenge in a similar way, congratulations. And if you did it differently, that's okay. Still congratulations for tackling the challenge on your own, which makes you stronger every time you do so. All right, so in the next video, we're going to add some bells and whistles to our jet fuel pickup, maybe make it float or rotate and give it a little bit more juiciness so that it looks and sounds more like a fun pickup that you would have in your world. Excellent job, and I'll see you soon. Welcome back. We now have a functional jet fuel pickup, but in this video, we're concerned with juicing it up. We want to add some effects to make this pickup feel more fun, more juicy, and this is actually a really important aspect of game development because this adds some polish to your games and makes them feel more fun to play. So the effects that I'm interested in are both visual and audio. Now, I'm just going to quickly show you in our assets folder that in sounds, there's a jet fuel folder, and in effects, there's a jet fuel folder. So we have some effects and some sounds that we can use for jet fuel. And we also have other techniques to juice things up as well. We know how to create timelines. We know how to make things scale according to a curve on our timeline. And we know how to spawn effects and sounds. So your challenge for this video is going to be to juice up our jet fuel pickup. I'd like you to play a sound and spawn a Niagara system when we pick up our jet fuel. But in addition to that, I want you to feel free to add any other features to this pickup that you want to make it look and feel more fun. So pause the video and juice up your jet fuel now. Okay, so the first thing I want to do is go into my Actor Begin overlap implementation and do a couple things. One, I'd like to play a sound and spawn some effects. So I'm going to just break off my Destroy Actor node and move it to the side. And we're going to go ahead and use a spawn sound at location. And we'll use our actor location. So we'll use get actor location for that. And I do want auto destroy set to true, so we'll leave that as is. And I'm going to use a sound from my assets. I'm going to go to sounds and go to jet fuel. And here's a cool sounding jet fuel sound. I'm going to go ahead and select that and just click the left arrow so that it's hard coded in like that. And I'd also like to spawn a system, a Niagara system. So I'm going to spawn a system at location. I'm going to use the same get actor location, and I'm going to look in my assets folder into effects and jet fuel. And here's a nice Niagara system that looks like fuel splashing out. It's yellow. It looks like what would probably be jet fuel in this game. And we're going to use that NS fuel pickup. Also with auto destroy. So we now have some effects, and then we can destroy the actor afterwards. So let's see what happens when we pick it up. All right, so that looks pretty good. But I'd still like to juice it up with a couple more features. For one, I'd like to rotate my mesh, and I'd kind of like it to be tilted a little so that it's not just vertical up and down like this. So I'm going to make a couple changes, but first I'm going to collapse these nodes to a function, and I'll just call this handle pickup effects. Like so. And I'm going to go into my viewport and select my fuel mesh. It's not my root component. It's attached to my default scene root, which means I can give it a little bit of a rotational offset. So if I give myself 15-degree increments, I can rotate by 40 degrees like this. And now I have a rotational offset. So that looks more exciting to me. And I'd also like to add a world rotation on tick. So I'm going to get my event tick, and I'm going to add a world rotation to my fuel mesh. So I'm going to get that fuel mesh, add world rotation, and we'll hook that up to tick. And I think I'm going to split the struct pin for delta rotation and use delta seconds multiplied by a rotation rate. So I'm going to take delta seconds, use a multiply node, and promote this second value to a variable called rotation rate, compile, and give this its own value like 45, and plug that into the yaw like that. And now I should be able to see that pickup rotating in the world, and it does. So that looks great. That's a little bit more juiciness. I'm going to pick it up. And finally, I'd like to really make this pop when I pick it up by adding a timeline to scale that mesh up and then back down. So we'll refuel, we'll handle the effects, but before destroying the actor, I'd like to play a timeline. So I'm going to create a timeline. I'm going to call this pickup scale timeline. I'm going to open it up and add a float track. And this will be quick. It's going to be about 0.2 seconds long. I'm going to rename this track to scale. And I'm going to add 2 keys to my timeline. The first one will be at time 0, and we'll start with a scale of 1. And the second one will be at time 0.2, and we'll have a scale of 0. And then I'm going to alter these keys by first converting them to an auto curve, and I'll take the second key and angle it up like this. And the first key will be angled up like this. And I'm going to go ahead and click zoom to fit horizontal and vertical so that I can see what it's doing. And this is what it looks like. We'll go ahead and scale up and then back down. And in fact, I may wish to go back down with this kind of trend so that we scale up and go down. Let's actually see what this looks like by implementing this timeline back in Event Graph. On update, we're going to take our fuel mesh and call set world scale 3D. And update will go to this, and our scale is going to be used to make a vector, and that will be passed in, and X, Y, and Z will all get the scale value like this. And to play this timeline, I'm going to make a custom event, and we'll call this wink out. And this will play the timeline. And when the timeline finishes, that's when I'd like to call destroy actor. So we'll put that right up there. And as soon as actor begin overlap is triggered, we can call wink out. But I'd also like to disable collision on my fuel mesh. So I'm going to take my fuel mesh, call set collision enabled, and set it to no collision. That way, for these last 0.2 seconds that this actor is alive, it will not trigger any further collisions. And really quickly, I can collapse these to a function by holding Control, bringing this out and adding a reroute node, hooking it back up to scale, and collapsing this to a function. I'm going to call this scale fuel mesh. And I'll rename its input to scale. And that way we have a simpler blueprint event graph. All right. So, moment of truth. Let's see how this looks. When we play the timeline and wink out, let's overlap. And that looks pretty nice. It looks a lot juicier. It's squirting out particles, playing a sound, and winking out with its little timeline. I like it. All right. So that's my implementation of Juice. And we could clean up this blueprint all we want, but I think it's relatively clean already. So I'm just going to save it and close it. And now that I have jet fuel, I can once again play test by selecting BP kicks, using some fuel, going to 0, and then picking up a pickup. Now I have 25, and I can use my jet fuel until it's gone. Excellent job, and I'll see you in the next video. Welcome back. Now we have jet fuel, and we know that we're using jet fuel to use our jet thrusters, and that we can refuel by picking up one of our jet fuel pickups. But we can't see on the screen how much jet fuel we have. The only way to see our jet fuel is by selecting BP kicks right here in the outliner and looking for the jet fuel variable and seeing its value as it changes in the editor. Now, that's great for development, but it's not a great experience for the player. The player should see at least some measure of the jet fuel on the screen so they know if they're close to being empty or if they are empty. Otherwise, they don't know why their jetpacks aren't working anymore. So to show things on the screen, we need to make use of widgets. Widgets are images that we show on the screen in games. These are typically health bars, labels, text, images, and anything else you can think of. And in Unreal Engine, we can make widgets. Specifically, we can make widget blueprints, and we can add them to the screen, to our viewport. Now, historically, Unreal Engine has a class called HUD. HUD is an actor class, and it's one of those default classes that are spawned automatically by the game mode. If we go into Blueprints, into our game folder, we have our custom BP Jetpack game mode. If we open that up, we can see all the classes that are spawned by default. These include our player state class, our default pawn class, and notice there's also a HUD class as well. And we can create a custom HUD class and set that class here. And then our HUD can handle things like user interface elements such as widgets. Now, this is a perfectly fine way to do it, but HUD is more of a legacy class, and it just hangs around because Unreal Engine knows that to remove this class from the engine would require a lot of Unreal Engine classes to just restructure their entire game projects to not use the HUD class. And it's really a convenient class to use if you just want an actor that handles all of your HUD stuff, but it's more of a legacy class, and we can handle our HUD in some other class, such as the player controller. So using the HUD class is a valid option, but we're going to use another class to handle our HUD. I'm going to choose to use the player controller class, as the player controller is specific to the player who's controlling their character. So we're going to handle our HUD with the player controller. So I'm going to close the game mode. I'm done with my Jetpack interface for now, and I'm done with BP Kicks, and we're going to create our very first widget. So if we go into Blueprints, we can create a new folder, and I'm just going to call this UI, short for user interface, and we'll keep our widgets in this folder. Now, to make UI in Unreal Engine, a great tool to use is UMG, Unreal Motion Graphics. UMG contains all sorts of tools we can use for widgets, and we're going to see how that works by creating our very first widget by right-clicking and going to User Interface. And the first thing we'll do is create a new blueprint, specifically a widget blueprint. So we'll select widget blueprint, and we get a pop-up menu asking us to pick a parent class for our new widget blueprint. Now, the base class for widget blueprint is called user widget. That's the parent class that our widget blueprints are going to be based on. If we wanted to, we could click all classes and choose a more specific class if we had a custom child of user widget that we would want to inherit from. But rather than do that, we're going to inherit straight from user widget. So select user widget, and we're going to rename our new widget blueprint prefixed with WBP, short for widget blueprint. And I'm going to call this overlay because we're going to have one big widget that overlays our whole viewport. And we can stick other widgets on top of that widget because widgets can be composed of other widgets. We're going to see how that works by opening WBP overlay. And this is what a widget blueprint looks like. Now, UMG, Unreal Motion Graphics, is what contains all of these features we see here. We have a widget blueprint with a designer panel showing us this graph here and a palette with a selection of different types of widgets that we can add to our widget blueprint. And there are a lot of different types of built-in widgets that can be added to a widget blueprint. And when they're added to a widget blueprint, they're added in a hierarchical manner. As we can see, we have a hierarchy tab, and all widgets that we add to our widget blueprint show up in the hierarchy tab, and they're hierarchical. They can be attached to each other, and we're going to see how that works now. Now, for an overlay, we're going to want something that represents the entire screen, and the type of widget that we can use for that is called a canvas panel. So if we take a canvas panel and we drag it onto our hierarchy or onto the graph, either one is equivalent, we'll now have a widget on our hierarchy. And our graph is going to show us a rectangle that represents the entire screen. Now, a canvas panel allows us to have multiple widgets, and we can place them at arbitrary locations on the screen. So I'm going to clear my search filter and just drag in any widget from the palette onto my canvas panel. I'm just going to select a text widget. If I click and drag a text widget onto the screen, we now have a text widget, and in our hierarchy, it's attached as a child to the canvas panel. Now, I don't mean child in an inheritance sense. I mean a child in an attachment sense. Kind of like how components can be attached to each other, widgets can be attached to each other as well. Now, this text widget has its own properties, which we can see in the details panel, and we can change them. Under content, we have a text property, which shows us what that text content is for this text widget. It just says text block, but we can highlight that text and replace it. We can say test widget text. And notice that the text now goes past the bounds of this widget. That's because we typed more text than we have room for, but we can resize the widget itself by clicking and dragging on its corners. And now this text widget is larger than the text that it contains. And we can decide how the text inside of it behaves within the bounds. We can scroll down to justification. Right now it's set to align text left, but if we click align text center, it'll be centered, or we can align it to the right. We can also change properties of the text, such as its font. If we expand the font, we'll see that Roboto is the only font. We don't have any other options. We'll learn later in the course how we can import custom fonts and use those in our projects. The Roboto font also has typefaces. We can change from bold to italic to light and so on. And we can change the text size. Now, we can even change the size so that the text is larger than the widget itself. In that case, we could simply resize our text widget. Now, because this text widget is on a canvas panel, we can anchor this text widget. This medallion at the top left shows how our text widget is anchored. It's anchored to the top left, which means as our viewport size changes, perhaps on different devices, or just in a Pi session, we have our viewport resized differently, that text widget is going to be positioned relative to its anchor point. So if the viewport size gets smaller, it's always going to be the same distance in the horizontal and vertical directions from that anchor point. And we can anchor text either to corners or to the center or to edges of the screen. We do that by selecting the text, scrolling up, and changing its anchors property. If I want to anchor my text to the center of the screen, I would choose this option. Now we can see that anchor, and the text will always have its position relative to the center of the screen. And its position X and Y are now relative to the center. If I want this text perfectly centered, I can set its alignment. The alignment is a value from 0 to 1, and if we set it to 0.5 for both X and Y, that means a value of 0 for the position X and 0 for the position Y will perfectly center the widget in the middle, at least based on its anchor point. So now that we have a widget with a canvas panel and just some text, it's now time to see how we can add this to our screen. We need to create an instance of the overlay widget and add it to the viewport. I'll go ahead and compile and save this widget, and we'll go back and create this widget in our player controller class. So we're going to go to Blueprints, Player, and open BPKIX Player Controller. And I'd like to create this widget on Begin Play. Now we have Begin Play up here, so here is where we'll do it. Now, we create widgets dynamically with a special type of node called createWidget. So we'll get a createWidget node, and this is a lot like spawnActor from class, except it's specifically for widgets. So spawnActor from class allows us to specify the class to spawn, right? Well, createWidget allows us to specify the widget class to spawn. And if I open the dropdown, WBP overlay is an option. We're going to choose that. And when we create a widget, we can give that widget an owner. Notice the owning player input. This is a player controller object reference. So a widget can be owned by an actor, and we typically have player controllers own widgets. And we can get a reference to self and hook that in so that this widget is now owned by the player controller. It can always access its owner if that owner has been set, and it will be set as long as we pass in a player controller. Now, creating a widget is not enough. We're not going to see the widget just because we've created it. We also have to add the widget to the viewport. So we do that using the return value from this node. We grab that return value, which, by the way, is a WBP overlay object reference, specifically our class that we're constructing here. We can get that value and call add to viewport. And that's how we add this widget to our viewport. And since we're doing this on begin play, we should now see that widget on the screen. So I'm going to compile and save and press play. And now we can see that test widget text on the screen. It's right there in the center of the screen. So we've now successfully created a widget and added it to the viewport. And our player controller has access to this widget because we have the return value. And if we would like to access this widget to change properties on it later on after begin play, we can promote this to a variable and store it here on the player controller. So I'd like to do that. I'd like to take that return value, promote it to a variable, and we'll just call this overlay widget. And now we have access to it if we'd like to change things later on. So to clean up my nodes here, I'm just going to break the wire for target on add to viewport and just use the value on the set node for overlay widget, which is the overlay widget value. And I'll go ahead and connect these wires here. And now we have an overlay widget that we can refer to later. And we can collapse these to a function. I'll go ahead and do that. And we'll call this construct overlay widget. Actually, let's just call it create overlay widget. That sounds a little bit more like what we're doing, right? And we'll go ahead and leave that on begin play. So we have a create overlay widget function, and we now have our overlay widget, which can get its own category. We'll give it the category of UI for user interface. And there's our overlay widget. We can access it later. And just really quick before we wrap up, I want to show you an example of changing a property on our widget at runtime. I'd like to change the text on our text widget here. Now, if we want to change the text on our text widget, we have to make sure that this text widget is an actual variable, and we can always make a widget a variable by selecting it, and in the details panel here in our designer tab, we can check is variable. And now this variable can be accessed, but we need to make sure that it has a meaningful name. Text block 0 is not very meaningful, so I'm going to call it text block test. And we can access this variable and change it from within an event graph, such as in the player controller. So just for a test, we're going to add a delay node. We're going to delay for 3 seconds before we access our overlay widget. We'll get it here. And on the overlay widget, I want to access my text block test variable. So I'm going to drag off and type text block text and search for text block. And here's the getter for it. If I get that and hover over it, I see that its type is text object reference. And a text widget has the ability to set its text. If we call set text, there's a set text function with text in parentheses that takes in an input of type text. Now, the text data type is a lot like the string, except text is meant for user-facing text, such as the text we see in widgets. So we're going to connect this set text node, and we're going to hard code in some replacement text for that text widget. Initially, it's going to say test widget text, but now it's going to say something else 3 seconds after begin play. Let's just say changed text. So we can test this by playing the game and waiting for 3 seconds. Let's see what happens. And there we go, we changed the text at runtime by accessing that text widget on our overlay widget blueprint object. So that just proves that we can change our widget at runtime. So now we've successfully created our overlay widget. We don't need this test text. That was just to show that we can add a widget to our canvas panel. We'll soon remove that, but in the next video, we're going to add something a little bit more exciting than text. We're going to add a progress bar so that we can see how much fuel our Kix character has. Excellent job, and I'll see you in the next video. Welcome back. Now, we've seen that we can add our widget to the viewport, which we're doing in the player controller in Create Overlay Widget. And we're storing the overlay widget as a variable so that we can access it and change things on it later. And we proved that we could do that by changing the text on our test widget text block. Well, in this video, we're going to add a new type of widget to the top left of our canvas panel. I'd like to add a progress bar. Progress bars are great for things like health bars, or in our case, a fuel bar. So let's drag a progress bar straight onto our canvas panel. And notice that it pops up on the canvas panel in our hierarchy just under the text block, which I don't really need the text block anymore, so I'm going to select it and delete it with the delete key. But we have a progress bar, and our progress bar can be resized just like our text block widget. I'd like it to be long and somewhat thin. We're going to put it right about there. And a progress bar has a % variable. By default, it's set to 0. But if we click and drag it to the right and look at our progress bar up here, we'll see that we're filling up that progress bar from left to right. And when it's all the way full, it's blue. Now, a progress bar's color can be changed. It can even use a material instead of a flat color. These can be customized quite a bit. And we really have a lot of options in the details panel for progress bars. And we're only going to touch on a few for now. But this percentage here, this can be set at runtime. And that's typically what we do with progress bars. We usually set them based on the value of something that's going on in our game. And in our case, our Kix character has a fuel that we want to use to drive our progress bar. Now, fuel, at least in this game, is kind of a yellowish color, so I don't want my fill color to be blue. And if I scroll down in the details panel, we have a fill color and opacity, and I can click on that rectangle to get the color picker. And I'm going to change this to a more yellowish orange color. I'm going to go ahead and set that color like this. But we also have that gray background color, which is, in my opinion, quite ugly. So I'd like to change that background color as well. And we can also do that here in the details panel. If we scroll up, we have a style dropdown. We can open that. And here's where we can change things like the background image and the fill image. And if we expand background image, by default, there is no image, but it does have a tint, which is set to white by default, but we can change that tint to a darker value if we like. And I typically like to do that. I like to make it almost black, and I like to make its alpha less than 1, something like 0.5 or 0.6. So it's semi-transparent, and now we can kind of see what that looks like as we can sort of see the grid behind the transparent dark color. Now we can compile and go back into the level and playtest, and we can see that progress bar on the screen there. So that's what it will look like. But we have other properties we can change. One property that I'd like to change is the padding. I'd like my fill color to be padded a little bit. In other words, I want that rectangle to be slightly smaller than the background. So I can come down to the progress section and give it some border padding. I'm going to give it about 2 and 2 for X and Y. And now we can see that there's a little bit of padding around that fill color. And we can also change the way that our progress bar fills up with the bar fill type. By default, it's from left to right. So we start at 0 and we go all the way up to 100% from left to right. But you can change the bar fill type to any of these options. Right to left, for example, if you want to fill from the right to the left, or you can fill from the center horizontally or vertically, or fill from the center in both dimensions. Perhaps that would be for a dot that fills from the middle, but fill from the center horizontal would be something like this. If you want to fill from the middle, I'm going to leave it at left to right, as that's how I'd like this progress bar to behave. So we have a basic bar, and I'm going to leave it at 1 for the percent. Now it's actually a fraction between 0 and 1, so 1 really means 100%, but they just call it percent, and you'll see that a lot in game development, at least in Unreal Engine. So starting the game, we can see that this is what our fuel bar looks like when it's completely full. But if I use my fuel, I want to see that fuel bar get drained down, which means we need to know how much fuel we have when we're using our jetpack, right? So Kix Player Controller is where we're handling the input for that. And I have a number of tabs open. I want to go to my event graph, which I see here, but I'm going to go ahead and close some of these other tabs and go into my event graph and find my input where I'm handling the jetpack, which is right here, IA jetpack. And every frame while the jetpack is active, we have triggered being executed, and we're checking to see if we have fuel before we apply thrust input, and we call drain jet fuel. So drain jet fuel, if we open it, is simply getting our controlled character and calling drain jet fuel on it, where our character handles actually updating the fuel variable. Now, this is being called every frame while the jetpack is active, and this would be a perfect place to update our overlay by getting the overlay widget, accessing its fuel bar, and updating its fuel percent. So I'd like to do that. So we need to do a couple of things. We need to access the amount of fuel, particularly what percentage of our maximum fuel do we have, so that we can then access our overlay widget and update its percent. Now, let's think about this. What's an easy way that we can get the remaining fuel from our controlled character? We could make an interface function on our BPI Jetpack interface to retrieve the amount of fuel, but we're already calling an interface function related to jet fuel called drain jet fuel. And it's a function, and functions can return values. So after we update the jet fuel, why don't we just return the current value of the jet fuel here? Or at least the percentage that we need for our progress bar. We can do that. First, let's take a look at how we're implementing drain jet fuel in BP Kix. I'm going to go to the Kix folder, open BP Kix, and under interfaces, I'm going to find drain jet fuel. Here it is. We're calling consume jet fuel for frame. We're going to open that. And here we're updating our jet fuel values. Now, if we want to change drain jet fuel so that it returns a value, since we're calling it here in the player controller and we want it to return how much fuel we have, then we need to change it in the interface by adding an output to it. And as soon as we do that, it's going to change right here in BP Kix. It's no longer going to be an event, but it's going to be an actual function. So we need to be aware of that. Let's see how that happens by going into our interfaces folder, into BPI Jetpack, and let's go to drain jet fuel, and let's change it. We're going to change the function to have an output. I'm going to add that output and change its type to float, and I'm just going to call this current fuel %. So we can calculate the percentage here and return it from this drain jet fuel function. I'm going to compile and save. And if we go back to BP Kicks, we now get a warning, and this custom event has even been renamed because now drain jet fuel has an output, so it can't be a custom event anymore. We actually have to remove this. And now we have to implement the function as a function and not an event. So here it is under interfaces. We'll go to it by double-clicking it. And here is where we can call what we were calling before, which is call our consume jet fuel for frame function. So consume jet fuel for frame. Here it is. It's in our category jet fuel. That's why we can't see it under functions, but if we expand jet fuel, we'll see it there. This is our function where we're consuming the jet fuel. We're taking our jet fuel, subtracting the jet fuel drain rate, scaled by world delta seconds, and we're clamping the value between 0 and max jet fuel, and setting our jet fuel value. So now in our blueprint interface function implementation, we can simply call consume jet fuel for frame, but now this function returns the current fuel %. So I'd like to calculate that and return it here. And I can calculate the fuel percentage by finding my jet fuel and dividing it by max jet fuel. Now, the naive approach here would be to drag off and type slash and get a divide node and hook that up and pass that in. But the problem with this is if max jet fuel ever became 0 for some reason, we would be dividing by 0, and that would be an error. So rather than simply dividing this value, we can make use of a math utility called safedivide. And what safedivide will do is divide A by B and return the result of this division, except if max jet fuel, the B value, is ever 0, then safedivide will simply return 0 instead of trying to divide by 0, which is not mathematically something we can do. So now we have a way to get the fuel percentage by dividing jet fuel by max jet fuel. Be careful not to get this backwards. If you divide max jet fuel by jet fuel, this will be wrong. And if you're never getting the correct percentage, that would be something to check. So we have a way to get the percentage. This is a great candidate for a Blueprint Pure function. So I'm going to collapse it to a function called getFuel%. I'm going to select it and convert it to pure. So we now have an easy way to get the fuel % when we need it. And I'll stick it in the category jet fuel. So now our blueprint implementation of drain jet fuel on BP Kicks returns the fuel %. This is great. So I'm going to compile and save and go back to BP Kicks player controller and see that calling drain jet fuel here now allows us to access the current fuel %. So as we're draining the jet fuel, we can now use that fuel % to update the progress bar in our WBP overlay. Now we saw that with a text widget, we had to make that text widget a variable. Well, the same goes for a progress bar. We have to select it, and in the details panel, we have to check is variable to be able to access and change it from within an event graph. And we should also change its name as well. Now, we've seen how to rename widgets by clicking on them in the hierarchy. We have to actually click a second time. We can change their name here, or in the details panel, we can change their names here. And I'm going to call this progress bar underscore fuel. I typically like to leave the type of widget first with an underscore followed by a description for what it's supposed to be for. So now that we have a progress bar fuel, we can access it from the event graph in our player controller. And that's what I'd like to do now. I'd like to use my overlay widgets. I'm going to bring that in. I'm going to find progress bar fuel. We'll get that. And we can set the percentage for this progress bar by dragging off of it and calling set percent using the function and not the setter for the variable on this progress bar called percent. That's just built in. We want to use the function which takes in a float for the percent, and we can hook this up and take our current fuel percent that we get from drain jet fuel and hook that in. And now every frame that we're calling this drain jet fuel function, we're also accessing the widget and setting its fuel percent as well. If we compile, we get an error, and if we drag up our compiler results, we're going to see the property associated with progress bar fuel could not be found in overlay. Now, that's a problem, right? And the reason is because if we go to WBP overlay, we did make this a variable, but in order for our Kix player controller to see that change, we have to compile here in WBP overlay first, and then back in Kix player controller, if we compile again, we don't have an error. So compiling is the way for that change to be visible in other blueprints. So let's see how this works by draining some of our fuel. We're going to start playing, and I'm going to use my jetpack. And there it goes. It drains down to 0 as we're updating it, which is great. Now, there's a problem though. What about refilling our fuel? Well, if we go over and pick up our pickup here, we know that our fuel went up. In fact, we can use our jetpack. And as soon as we do, we're now updating that fuel bar again. But when we picked it up, we did not update the fuel bar. So we have to update the fuel bar when we refill our fuel as well. So how do we do that? Well, if we go back to BP Kix, we can see how we're refilling our fuel by going to our interface functions and check out refill fuel. If we double click that, we'll see that all we're doing is calling handle refill fuel. And if we look at that, all this does is updates our fuel. We take the fuel amount and add it to our jet fuel, we clamp it, and then we set jet fuel. And this function is an interface function called by the pickup in our world here, this BP jet fuel. If we edit that blueprint, we can see that in actor begin overlap, we're taking the other actor and calling the interface function refill fuel. So our player controller has no idea that we're refilling our fuel. We can't just come into Kix player controller and find somewhere where we can update the percentage because the player controller does not know that our fuel has been refilled. So that's something that we're going to need to think about how to handle, and we'll do that in the next video. In this video, before wrapping up, I would just like to clean this up a little bit. You see, here in the player controller, we have our overlay widget, which means we can access widgets on it, such as the progress bar, and change their percentage directly here. But it would be really nice if I didn't have to find the specific widget on my overlay widget variable. It'd be nice if I could just call a function on overlay widget for setting the fuel percent and let the widget handle finding its specific progress bar widget and updating its percentage and all that. So we're going to go back to WBP overlay, and we're going to take a look at another section of this blueprint, and that's up here where we see the graph tab. You see, we've been working in the designer tab where we put our widgets onto the designer graph, but if we click on the graph tab, we now have an event graph, much like the event graph for an actor. So widgets can have their own blueprint logic as well, and they can even have functions. So I'd like to have a function that can update our fuel percent to make it easy to do so, such as from the player controller. So back in WBP overlay in the graph tab, we're going to make a new function under the My Blueprint panel. So add, we're going to call this function update fuel percent, and this function can take a float input for the fuel percent. So we can select the purple update fuel percent node, and in the details panel, we can scroll down, and here we can add inputs. I'm going to add an input, and I'm going to call it fuel percent, and I'm going to change its type to float, And here is where we can update our progress bar. As you can see in the My Blueprint panel, there's a variable section and there's our progress bar fuel variable. And this would not be here if we hadn't gone into the designer, selected that widget, and checked is variable. So this is what makes it a variable, and we can update it from within our widget blueprint as well. So we're going to take our progress bar fuel, and we're going to call set% right here, passing in the value of fuel percent. So now WBP overlay has a function called update fuel percent, and this can be used to easily update the fuel percent without needing to reach into the WBP overlay class and find the progress bar fuel. We don't need to do any of that. All we have to do is call this function. And that's what we'll do in Kix Player Controller. We'll just take our overlay widget and call our new custom function update fuel percent. And then we don't have to access the progress bar fuel. We don't even have to know about it. And we don't have to call set% on it. All we have to do is call update fuel percent on our overlay widget, which is a lot cleaner. So cleaning up my nodes, there we go. So now our player controller will update the fuel percent every time it drains the jet fuel, which is great. This actually works really nicely while we're draining the jet fuel. The only problem is we're not updating it when we pick up a jet fuel pickup. So that's going to be next. Excellent job, and I'll see you soon. Let's take a moment to discuss the concept of class dependencies. This is a concept related to coding practices. And even though we're using Blueprint and not a programming language such as C++, we're still creating software, and we should still use good coding practices. In an object-oriented software program such as ours, we have objects, each of which have their own class data types. And inside each of these classes, we have dependencies on other class data types. Whenever we use a specific type inside of one of our classes, we say that our class now has a dependency on that type that we used. In our BPKix player controller class, we stored some of the essential variables on begin play using our function store essential variables. For instance, we accessed the controlled pawn class and cast to character and stored this value in a member variable called controlled character. This creates a dependency on the character class here in our BPKix player controller class. The character class is a base class in the Unreal Engine class hierarchy, and our BPKix character class is based on that. This is perfectly fine. One class can depend on another class like this. It happens all the time in software. But what we need to be careful of is that we don't want circular dependencies. The character class is an engine class, and we can't change it, at least not without downloading the engine source code and changing it, which is not something that we're going to do. So we can't just go into the character class and add a dependency to BPKix player controller, at least not without a lot of effort. So since the character class doesn't depend on BPKix player controller, we say that this dependency is one way and that these classes are loosely coupled. And from a coding practice standpoint, this is a good thing. But now let's say that rather than casting to character from within our BPKix player controller class, we cast to BPKix instead. Well, now our BPKix player controller class has a dependency on BPKix instead of the character class. Now, BPKix is our own custom blueprint class, and we can easily make any changes we want to it. In fact, there's nothing stopping us from accessing the player controller in BPKix and casting it to BPKix player controller and storing that as a variable so we can easily access functions and variables on the BPKix player controller class during the game. That sure would make things very convenient. This would now mean that Kix has a dependency on the BPKix player controller class. We now say that these two classes have a circular dependency and that they're tightly coupled. Now, this makes our software design a lot less flexible. We can't have a project with BPKix player controller in it that doesn't also have a BP Kicks, and vice versa. We can't have a project that has a BP Kicks in it without also having a BP Kicks player controller. These classes depend on each other, and they must exist together. In general, good coding practice is to keep classes loosely coupled with one-way dependencies. This makes the code more flexible. For example, if we had left our BP Kicks player controller as it was, and only cast to the character class and not BP Kicks, the BP Kicks player controller class would not have a dependency on BP Kicks, and the classes would no longer be tightly coupled. Now, inheritance requires dependency too, as BP Kicks is a character, as it's derived from the character class, so because of that, it too depends on the character class. It's important to realize that. But notice how these dependencies are one way. Character is completely independent of these two, and can be used in other Unreal Engine projects that don't even know about BP Kicks or BP Kicks player controller. It's really just BP Kicks that depends on BP Kicks player controller, and that's fine. We could create a completely new type of character called BP Talk, for example, and BP Talk could have a dependency on BP Kicks player controller, and this would work just fine, because BP Kicks player controller does not depend specifically on BP Kicks. Now, we still managed to affect BP Kicks from BP Kicks player controller because BP Kicks implements the BPI Jetpack interface. So BP Kicks player controller can call functions on BPI Jetpack and have a dependency on that interface without needing to depend on BP Kicks directly. If BP Talk needs a jetpack, it too can implement the BPI Jetpack interface, and BP Kicks player controller can still just call interface functions on that interface that BP Talk can implement its own logic for. So BP Kicks player controller is generic in a sense that it doesn't know or care about what specific character classes it happens to be possessing. It just knows that they're derived from the character class. This maintains a loosely coupled system, and this is considered good coding practice. So if we just take a look at our project, so far we have a BP Kicks player controller class and a BP Kicks class, which implements a blueprint interface, BPI Jetpack. If the BP Kicks player controller needs to affect the Jetpack-related variables on Kicks, it can do so by calling interface functions on the BPI Jetpack interface, and not need a dependency on BP Kicks. But now we have this BP Jet Fuel class, a pickup that has no idea what a BP Kicks or a BP Kicks player controller are, and nor should it. BP Jet Fuel has no business depending on these specific classes. It can simply depend on the interface instead. When the Jet Fuel pickup registers an overlap with the character, it can simply call a function on it for refilling jet fuel. We've already implemented this. Kicks implements refill jet fuel, updating its own jet fuel variable. But now BP Kicks player controller needs to know about this jet fuel update because it owns the overlay widget, which has the fuel progress bar. So we can simply let Kicks have a dependency on BP Kicks player controller to let it know that the jet fuel amount has now changed, and we need to update the WBP overlay widget. Now, you might be thinking that this is an awful lot of work just to keep this system loosely coupled. This whole thing would be easier if we just did away with BPI Jetpack and just let the BP Jet Fuel class directly depend on Kicks by simply casting the overlapped actor to BP Kicks in its overlap event and accessing variables directly on Kicks, or letting BP Kicks and BP player controller have references to each other, or even let BP Kicks reference the overlay class directly. You see this type of thing in beginner's code all the time, because it just seems like the natural thing to do, but it restricts our design and makes it rigid and brittle. If BP Jet Fuel has to cast to BP Kicks, what happens when we add a new character, such as BP Talk? Well, if Jet Fuel now overlaps with a Talk character, this cast to BP Kicks would fail. And if the cast fails, now we must do another cast to BP Talk. This means when we make a new character, we now have to go into our Jet Fuel class and change its code every time. But with interfaces, a new character requires no such change in our jet fuel code. We still just call the interface function, and it's up to the new character class to implement it how it sees fit. So the tendency to manage our dependencies is good practice from a coding standpoint. Later on, we'll talk about the consequences of casting to class types from a performance standpoint. But for now, it's enough to know about class dependencies and how we should try to keep them one way like this. So now we're ready to take care of the problem we mentioned in the previous video. When we overlap with a jet fuel pickup, we refill the jet fuel on BP Kicks. Now we must update our fuel progress bar, so BP Kicks needs a reference to the BP Kicks player controller to tell it to update the overlay widget. And we'll do that in the next video. Welcome back. So we need to let our player controller know once we've refilled our jet fuel. You see, when we drain the jet fuel, our fuel bar updates appropriately, but when we overlap with the jet fuel pickup and refill that fuel, we don't see that change reflected. So we're going to fix that in this video. Now, what happens when we pick up a jet fuel pickup? We can go to BP Jet Fuel and remind ourselves we have actor begin overlap, where we take the overlapped actor other actor and call the interface function refill fuel. Now, BP Kicks implements refill fuel. We can go to its refill fuel function and see how it handles it. It simply calls handle refill fuel, and if we go in there, we can see that we're adding the fuel amount to our jet fuel, and after a quick clamp, we update the jet fuel. So as soon as this fuel gets updated, we need to inform the player controller that the fuel has been updated. And this means our BP Kicks must now have a dependency on BP Kicks player controller. We need to have a reference to it. So what we can do is go back to our event graph and use event begin play. And on begin play, we can access our controller. We can do that with get controller. And our get controller node returns a controller object reference. And we need this in the form of a Kicks player controller, so we can cast to BP Kicks player controller. And this value we can store in a variable by promoting to variable, and we'll call this Kicks player controller. Now, I'd like to condense this into a function to store essential variables for Kicks. So I'm going to right-click and collapse the function and call this store essential variables. And this is where we store our BP Kicks player controller variable that we can access here in our handle refill fuel. All we have to do is bring it in. So we have Kicks player controller. I'd like to convert to a validated get. And here we can tell the Kicks player controller to update the fuel bar. Now, Kicks player controller does not have a function to update the fuel bar, but we can easily create one by adding a new function. And we can call this update fuel bar. And it can take in a float for the fuel bar percent. So we'll add a new float input called fuel percent. And all we need to do here is get our overlay widget. We can use a validated get. And on that overlay widget, we can simply call the function that the overlay widget has. If we go back, we can see that it's called update fuel percent. So Kicks player controller can simply call update fuel percent on the overlay, and we can pass fuel percent straight through like so. So now whenever our BP Kicks handle refill fuel is called, we can take our Kicks player controller and call update fuel bar. And all we need to pass in is our fuel percent, and we actually have a Blueprint Pure function to calculate it. It's called get fuel percent. We'll go ahead and pass that in. And just as a reminder, we can double click it to look at it. It's this safe divide, jet fuel divided by max jet fuel. That's all we do. So we're getting that and telling the player controller, hey, update the fuel bar, please. It has just changed. So we can check this out by draining some of our fuel. We'll go ahead and use that jetpack. And then we can go and pick up this pickup. And there's our fuel bar, nice and full. Now, it doesn't go all the way up because remember, our jet fuel pickup only refills the amount of fuel designated by our fuel variable, which is 25. And our BP Kicks jet fuel variable is 50. So one jet fuel pickup should fill up only half of our fuel bar, but we can duplicate this actor in the world and completely drain our jet fuel and see if these two will fill it back up. So we'll go ahead and drain that jet fuel. We'll pick up this one. That's about halfway. In fact, it's exactly halfway. We'll pick up this one, and our fuel bar is full. Excellent. So now that our fuel bar is functional, we can drain it. We can also refill it. We now have a visual way to know how much fuel we have. Excellent job, and I'll see you in the next video. Welcome back. Now we're updating our jet fuel progress bar, and that's great. Now, we did have to cast to our BP Kicks player controller from within BP Kicks. We did this in Begin Play. I'm going to go ahead and close some of my tabs to get things under control, and I closed my event graph, so I'm going to get that back right here by double-clicking, and I'm going to remind us in Begin Play that we called Store Essential Variables, in which we got our controller and cast to BP Kicks player controller. Now, this whole business of casting is subject of lots of hot debate. In fact, you might hear somewhere out there people saying that you should never cast, that it's always bad. Now, usually when someone says to never use an engine utility, that's generally an indicator that they don't quite understand that engine utility, and we should always seek to understand the things that we decide to use or not use. So if people say casting is bad and that you should avoid it, you should understand why casting is bad and in what circumstances. So what does cast do under the hood? Well, what it does is it checks the object we're casting to see what its data type is and compares it to the type we're casting to. For instance, we're passing in the controller, which is an object of type controller, and this cast checks to see the type of the object we passed in. And if it's not a BP Kicks player controller, then it goes to the controller's parent class, the parent that it's a direct descendant of, and checks that class to see if that is a Kicks player controller. And if it's not, then it checks that class's parent and climbs up that inheritance hierarchy until it reaches the very top, or it reaches a class that is this class we're trying to cast to. Now here's the Unreal Engine documentation for a player controller. And notice that we have the inheritance hierarchy here, and it's showing us that a player controller is derived from a controller. In C++, we have a in front of the names, but in Blueprint, those a's in front of the names are stripped away, and we just have player controller and controller. Now notice controller is based on the actor. Actor is the parent of controller. An actor is based on the object class, which in turn has its own parent class called object base utility, which is also based on another class called object base. So we have this class hierarchy here, and our player controller in our game, BP Kicks player controller, is based on the player controller class. So Kicks player controller has the parent player controller, which has the parent controller, which has the parent actor, which has the parent object. So this is why from a speed perspective, casting might be thought of as expensive because it climbs up the hierarchy checking each type until we get a match or we fail the cast. Now this controller is an object of type BP Kicks player controller. We know that because our game mode specifies that class to spawn for the player controller class, and that object is stored in the form of a controller. So when this cast is performed, it will check this object and see that it is indeed a Kicks player controller object, and we can move on from there. Now, this is generally a pretty quick process. It doesn't take very long in terms of computation time. It's even faster in C++, but we're not too concerned about doing a cast in Blueprint, especially if we only do it once, say on begin play or in a one-off function. It's not something we want to do in the tick event. So if you're casting in tick, you might want to think about figuring out a way to get around that. But we're not doing that. We're casting once in begin play, and that's fine. This is not going to affect the runtime performance of our game. But there's another consideration to be made about casting, and that's a memory consideration. You see, any dependency that we have in our blueprint increases the size of the object that our blueprint is the class for. For instance, bpkicks now depends on bpkicks player controller. And when we cast, we create what's called a hard reference. We now have a hard reference here to the kicks player controller class, and this increases the size of kicks because when kicks is loaded in memory, the player controller is also loaded in memory. Now, in the case of the player controller, it's already going to be loaded in memory anyway, but this is an example of a hard reference, and it does increase the size for kicks. And we can see that by going to our kicks blueprint, bpkicks, right-clicking on it, and selecting size map. Now, the size map shows us not only bpkicks and how big it is, but it shows us a map of the assets that bpkicks references, which are contributing to bpkicks being so large. Now, we see the size to display, but if we change this to memory size, this is the memory in the game. The pop-up says memory size is only available for editor data. But anyway, we can see that bpkicks, when we set this to memory size, takes up 15.9 megabytes. And we can see how much of that is taken up by the various assets. Most of them are the skeletal mesh, which has to be loaded if kicks is loaded, right? We need to see kicks. We also see that there's the Niagara system, the animation blueprint. By the way, I'm hovering over these and scrolling my mouse wheel up once to expand them. But we also see bpkicks player controller here, and it has a size of 96 kilobytes that we've increased bpkicks by. It's not a lot, which is why casting to it is not a huge deal in this case. But let's just say we did not follow good coding practice and our jet fuel class, rather than using an interface, let's say jet fuel, performed a cast to bpkicks in its actor begin overlap. So if it took other actor and instead did a cast to bpkicks, for example. Now, if I compile and save this, even if I'm not using this bpkicks node, this cast node here, just existing in BP Jet Fuel, has increased the size of BP Jet Fuel. If I go to my pickups folder and right-click on BP Jet Fuel and look at its size map, I see that it's 97 megabytes. And part of that is the bpkicks reference. We can see it in green here. It's 15.9 megabytes, as we know. We see that an even larger problem are the material instances referencing large textures, but that's another story. We got this from Stackobot, so we could take our gripes with the file sizes of these textures to the creators of Stackobot. But BP Jet Fuel doesn't need to be 97 megabytes. These almost 16 megabytes from bpkicks are unnecessary, but they're here because of the cast. If I delete that, compile and save, and look at my size map one more time, well, it's now only 81.4 megabytes because we're not casting to bpkicks. So using our interface in this case is good practice because Jet Fuel doesn't have a hard reference to kicks. It doesn't need one. So that's one reason why we would want to avoid casting. But if kicks needs the player controller, it needs the player controller. It needs to cast to it. So we're going to have a hard reference to it. But what if kicks player controller gets larger? What if we add a variable to it and we set its type to static mesh? We make that an object reference. We compile and we add the static mesh jet fuel to it. So now bpkicks player controller is larger. Well, now if we go to our Kix blueprint and check out its size map, it's now a great deal larger because it's referencing Kix player controller, which is also larger now thanks to static mesh jet fuel. This is an expensive asset, right? BP Kix doesn't have to be 96.9 megabytes. If we go back to our Kix player controller and we set this static mesh jet fuel to none by opening the dropdown and clearing it, compile and save that. Now we'll see that BP Kix, if we look at the size map, is back down to 15.9 megabytes. So Kix player controller, simply having a hard reference to static mesh jet fuel, not only made Kix player controller bigger, it made BP Kix larger as well. Now we're going to be removing that variable. This is just for demonstration purposes. We don't need a static mesh jet fuel on Kix player controller. But if we did have a big asset like this on Kix player controller, then what do we do for Kix? Kix doesn't need to be larger. It doesn't need a hard reference to the jet fuel static mesh. Well, we know one way to avoid this cast and this hard reference. We could create an interface, and Kix player controller could implement it, and we could simply use the interface rather than casting to the player controller. That's one option. Another option is to have Kix player controller be based on a parent class that has no assets on it, an empty parent class. Let's see how that works. Let's take our Kix player controller and browse to it, and right-click and make a new blueprint class based on player controller. And this is going to be called BP Kix player controller base. And this will be what we base Kix player controller on. This will be a parent class for it. So I'm going to save all and go to Kix player controller, open its class settings, and change its parent class from player controller to BP Kix player controller base. And now our BP Kix can cast to the player controller base instead of Kix player controller. Why? Because Kix player controller base does not have an expensive static mesh asset. It's much smaller. If we look at its size map, it's 3.5 kilobytes, which is tiny. So in BP Kix, instead of Kix player controller, we're going to now cast to BP Kix player controller base, and we're going to store this as a variable instead. We'll promote it to a variable called Kix player controller base. And we're not going to store Kix player controller. We're only going to store the parent class, which is cheaper. Now, if we compile, we're going to need to make a fix to our handle refill jet fuel function. If we go into that function, we'll see that we're calling a function on Kix player controller, but we're now no longer setting that. This will not be valid, so it'll never be called. We now only have the parent class, which does not have an update fuel bar function. But what we can do is add an update fuel bar function to the parent class. So I'm going to go to Kix player controller base, and we're going to add a new function here called, we'll just call this fuel update to give it a different name, and give it an input of type float called fuel%. And this function isn't going to do anything here in Kix player controller. It's kind of like an interface. There's no implementation here. We're going to override its implementation in its child class, Kix player controller. We're basically going to take update fuel bar and do what we're doing here in the function that we inherit called fuel update. So here's how we override a function. We go to the functions, click the drop down for override, and we find the function. Here it is, fuel update. We see that we've inherited it from BP Kix player controller base. We're going to implement it here. Now, this is a call to the parent version, which does nothing. We could delete it and be safe to know that we're not missing out on anything, but I'm not going to delete it. I'm just going to leave it there. And what we're going to do is what we were doing before in update fuel bar. We're going to take these nodes from update fuel bar. We're going to paste them in here and use this fuel% to update the fuel bar. And now we don't need this update fuel bar function. We've now implemented the inherited fuel update. So update fuel bar can be deleted. We're going to take it over here and delete it. Now it says it's in use, but we're going to delete it anyway because we now have fuel update, which is inherited from the base class. And in BP Kicks, this function doesn't exist anymore. In fact, we don't even need Kicks player controller anymore. We're going to use Kicks player controller base. We're going to convert it to a validated get, and we're going to call the function that only exists on the base class called fuel update and pass in the fuel percent here. And now BP Kicks does not even need Kicks player controller. It has a reference to the base class, which is much smaller than the child class Kicks player controller. We can see that by checking the size map for Kicks now. We see that it's only 15.8 megabytes, and the reference to Kicks player controller is somewhere down here. It's really small. It's not the biggest contributor to the size of BP Kicks. So instead of casting to a big class in store essential variables, we cast to a very small class, the base class for Kicks player controller. And then we moved any functions we needed to access from Kicks player controller into Kicks player controller base, namely fuel update. And we don't even do anything here. It's just here so that we can call it from BP Kicks. And because the player controller base variable stores an object of type Kicks player controller, we'll get the correct implementation, the version of fuel update on the child class Kicks player controller. This is a concept called polymorphism. It's more advanced. Don't be concerned if you're scratching your head on this one. You may need to watch this video again sometime in the future, but really just think about it this way. We're using Kicks player controller base just like an interface. Kicks player controller inherits from Kicks player controller base. Therefore, it inherits the fuel update function and provides its own implementation of it, just like you would for an interface. And then in BP Kicks, we have a reference to the base class. And because we have a reference to the base class, we can then call functions on the base class like fuel update, and we will get the functionality for fuel update that we've implemented in Kicks player controller. If you don't believe me, let's go back and spin some fuel and then pick up a fuel pickup, and we'll see that we get our fuel refilled. So the result of this is that BP Kicks now doesn't have to be larger just because it has a reference to the player controller, a hard reference created by casting. It has a hard reference to the player controller's base class, which is much smaller. It's void of big assets. So that's one thing we can do to use casting effectively. So you don't have to just avoid it, but you have to cast smartly and be aware of the file sizes. Now, Kicks player controller does not need this new variable we called newvar, the static mesh, which is a reference to the static mesh jet fuel. So I'm going to go ahead and remove that. And now we don't have such a large asset. In the next video, we'll talk a little bit more about these hard references and these size maps and how, looking at the size map, we can see that there are assets here making this particular blueprint larger in memory once it's loaded, and things we can do to mitigate that. So excellent job. I'll see you in the next video. Welcome back. While we're still on the topic of performance, I'd like to bring your attention back to the size map that we looked at in the previous video. For instance, if we take BP Kicks and right-click on it and choose Size Map, then we get to see the assets that are blueprint references and how big our overall blueprint will be in memory according to the memory size. We see 15.8 megabytes. And most of these are due to SKM Kicks, the skeletal mesh, and the majority of that is from the material. And as we can see, based on the size of the squares here, that the majority of the memory taken up by the material is due to these textures being used. Now, these textures exist in the assets folder next to the material. We created this material asset. We can go into Assets, Kicks, Materials, and we can see these textures here. Now, let's double-click one of them. the T-Kix-D. This is diffusion, that base color. And as we can see in the details, that its size is 2048 by 2048. In other words, this is a 4K texture. So that's why it takes up so much memory. And we have several textures here used by this material. We have the emissive color, which is mostly black. We have some color on there, but this is also a 4K texture. We have the normal map, which is also a 4K texture. And we have the ambient occlusion roughness metallic map. Remember, this has information in 3 separate channels, and we're using the grayscale values of each of those channels for different things in the material. Now, 4K textures look really solid. They look pretty great. If I start playing, we can see that Kix looks vibrant, looks detailed. Kix looks badass. And for the player-controlled character, that's okay if you want that much memory to be taken up, because, well, this is the object we look at the most. It's right there in front of the camera, so we're always looking at it, and we always want it to look great. But what if our camera was farther away? What if this was more of a top-down, or we just happen to have a longer spring arm target arm length? If I select my spring arm and change it from 250 to, let's say, 600, well, now Kix is going to be farther away. It's a little bit smaller on the screen, and we can still play the game, but, well, this is just a different style of camera. The camera's farther away, right? And in this case, we can't really see those up-close details. In other words, we don't really need 4K textures in this situation. Now, if we don't really need 4K textures, but our textures are 4K, something we can do to save on memory is we can compress the textures. You see, if we open our T-Kix-D, which is 2048 by 2048, we can search in our search bar for compression. And we have a maximum texture size. And if we wanted to cut that size down, we can enter a value here. If it's 0, there is no maximum, and we'll just use that 4K texture. But if we use a smaller value, then we'll compress the textures and use a lower fidelity version of the textures. And we can see the impact of that on our material from a memory standpoint by taking a look at BP Kix in the outliner and looking at its size map. So let's first take a look at our largest texture here, T-Kix-N, that's the normal map. Normal maps have more information packed within them. So the normal map is 5.6 megabytes. That's a third of Kix, almost. So what if we compress the normal map? What if we make it half as large? So instead of having 2048 by 2048, what if we cut this in half? So we can search for compression and set the maximum texture size. Instead of 2048, we can go 1024. We always want to use a multiple of 2 here. So we just cut 2048 in half here. And now if we take our size map, we have to actually close it and open it back up. Well, now we can see that the normal map is much smaller. It's 1.4 megabytes. It was almost a third of Kix. Now it's more like a tenth of Kix. Now, how does this affect how Kix looks in the game? Well, we can press play and see. In this case, we can't really tell the difference. In fact, we probably couldn't even tell the difference if we set that spring arm length back to 250. Let's see. Yeah, I don't know about you, but I really can't tell the difference with a compressed normal map. Now, how far can we go with this? How much can we compress these textures? Because right now, our size map has gone down to 11.6 megabytes. It was over 15 before, right? Well, what if we compress these down really small? Instead of 4K, what if we use half K, 512, as our maximum texture size? Well, let's try that with all 4 of them. We'll use 512 for T-Kix-D. Here for the emissive, we'll search for compression and enter 512 here for maximum texture size. We'll use 512 for the normal map. That's going to compress it down even more. And for T-Kix-ORM, we'll search for compression and set maximum texture size to 512 here. So I'm going to save all and play test and see what this looks like. Now in this case, I'm starting to see a difference. look at Kix's hair. The hair is a little bit pixelated, and you can really see the difference if you eject and you zoom up close. You can really see that things are looking blurry and pixelated. They're not all that great looking anymore. But in a game where our target arm length is longer, like 600, well, that might not matter. Let's see how it looks like this. Well, with the camera farther away, Kix actually still looks pretty good. And if I hit F11 to full screen, we can really see what's going on. And Kix does actually look pretty good. We don't really need 4K textures in this case, do we? So this is one way to get that file size down quite a bit, especially if you really want your overall game size to go down. Compressing the textures is one of the ways to do that. And once your levels have a lot of things going on, you might start seeing warnings in the viewport that say that your texture streaming pool is over budget, and cutting down on the texture size is one way to improve upon that. Now, in my case, because I want this to look really good, and I want Kix to have a short target arm length, like 250, I really don't want my textures on Kix to be compressed. I'm okay with them taking up more memory because this is the player-controlled character. Like I said, it's the character that we see most often. So I'm not going to compress the textures on Kix. I'm going to set that maximum texture size to 0 for all of them, and that way we have the maximum quality possible on Kix. But it's good to know about texture compression because there are cases where you'll still want to do it. For instance, take a look at our jet fuel pickup over here. The jet fuel pickup is not in front of the camera all the time. In fact, most of the time it's way out there in the distance. We don't really need it to be all that detailed. But if you'll recall, we took a look at our jet fuel size map before in the previous video. If we browse to it and look at its size map, we'll see that it's 81.5 megabytes, which is a lot larger than even Kix. Kix isn't even that big. Remember, we looked at Kix's size map and it was 15.8 megabytes before we even did any compression of the textures. So this jet fuel is ginormous compared to Kix. 81.5 megabytes is kind of extreme. And we can see that these are mostly textured 2Ds. These are from the materials being used on that jet fuel static mesh. We're using actually multiple materials, and these are referencing these very large textures. And the truth is, we don't need that much detail for this pickup because it's not going to be seen up close in all that much detail. I mean, we don't have a reason for it to be so detailed. So how do we optimize the materials on this so our jet fuel is not such a big blueprint? Well, first of all, I'm going to close my textures for Kix, and I'm going to take a look at my material being used by this static mesh. In fact, there are 3 of them. We'll start with the first one, MI Jet Fuel. This is a material instance, and if I double click on it to open it up, we'll see that its parent material is actually mTileMaster. And if I browse to that, it's here in the StackoBot folder. It's called mTileMaster. And if you open that up, you'll see that really it doesn't look like much, but it's using what's called a material function, which can contain a lot of things inside of it. If we double click it, we see a lot of things, a lot of nodes. I'm going to go ahead and close that beast right down, but we know that TileMaster is the master material for this material instance. It's actually the material parent for this material instance. And I want to see if we can find some of those textures being referenced in our jet fuel's size map, right? If we take a look at the size map and keep this open, we'll see that we're looking at a couple of textures here that we could potentially compress down, like this wind texture. I want to find this wind. And if I look at these concentric rectangles surrounding it, I see that this wind texture is in MI Plastic, and I can see in BP Jet Fuel that MI Plastic is right here. And if I browse to MI Plastic and double click it, well, there's that mTileMaster as its parent. Again, everything goes back to mTileMaster for these 3 materials. So how do I find which textures TileMaster is using? Well, if I browse to TileMaster, I can see what assets it's referencing by right-clicking on it and selecting Reference Viewer. If I choose that, then I can now see the dependencies of this material. It depends on these assets. And in fact, we can see the material instances behind it that use it, that depend on TileMaster. So TileMaster has these dependencies, and look, I can see this texture 2D called Wind. Remember, that's the biggest thing here in Jet Fuel. It's 22.4 megabytes, and here it is as a dependency for TileMaster. Now I can find this by right-clicking on it and selecting Browse to Asset. That's going to open up my content browser to this wind texture. There it is. If I hover over it, I see under dimensions, it's 4K, 2048 by 2048. And this is in the StackoBot folder. It's not in the engine content. You typically don't want to change engine content in general. But this is in StackoBot, and I can double-click it to open it and see what it looks like. If I move these out of the way, here's this 4K texture. It's being used in those materials. And I can compress this. If I go to compression and set the maximum texture size, I can set this down to about 512, and it's going to take up less space. If I save that, I can go back and look at my size map again, where before it was 22.4 megabytes. If I close that and browse to Jet Fuel and right-click and open the size map again, well, where's that wind? It's down here, 1.4 megabytes. It went down by a large amount. So we can get this material down by compressing the textures. But first, before we do that, let's take a look at our actual asset here. It doesn't really look any different to me. It still looks great. So I think compressing the textures for this should be okay. Now, next we have T-Metal painted in. This is in MI Plastic as well. So if I go back to my reference viewer, and if I look at these references, I don't see that metal texture, but I can find my MI Plastic over here, double click on it, and see the textures that it references, and there it is, T-Metal painted in. Here's my size map. I see that it's taking 22.4 megabytes. So why don't I browse to that? Here it is. Again, in the StackoBot folder, I can open this and see that this is not 4K, this is even more. This is a very large texture, 4096 by 4096. Let's see what happens if we compress this. It seems to be twice as large as the other textures, so I'm just going to compress it down to 1024 and save that. And now I can take my size map, and I see that T-Metal painted in was 22.4 megabytes. But now if I browse to Jet Fuel and look at its size map again, that T-Metal painted in is way smaller. It's 1.4 megabytes. And Jet Fuel is down to 39.6. It's quite a bit smaller now. So we can do this a couple more times. I'm going to compress T-Concrete Tileable in. That's in my MI Metal, so I'm going to find that. Now I've gone into MI Plastic, but I'm going to double click on SM Jet Fuel because it references MI Metal. And then I can double click on MI Metal, and I can find that texture. I believe it was T-Concrete Tileable in. Here it is. I can browse to it. I can open it, and I can see that it's 4096 by 4096. I can change its compression, maximum texture size to 1024, and save that. And now I can reopen my size map again. So browsing back to Jet Fuel, opening the size map. Now we're down to 18.6 megabytes, and the biggest texture now is T-Sand Tileable BC, and I can see that that's here in TileMaster. So I just want to find TileMaster, and I can go back to SM Jet Fuel, find MI Jet Fuel, which references TileMaster, and TileMaster has a reference to T-Sand Tileable BC, and here it is down at the bottom. I'm going to browse to this asset. Open it up, move these out of the way, search for compression, and set its maximum texture size. I see it's 4096, but I'm going to cut it down to 1024, so it's much smaller. Now I can close my size map, browse to my jet fuel blueprint, open its size map again, and now we're down to 8.1 megabytes. We've cut this down by a factor of 10. Now, we're going to want to see what it looks like. Here's what it looks like. It still looks good. And if we go and play test our game, I think it still looks fantastic here in the level. In fact, we can't even really tell the difference. At least I can't. And I'm fine with it having lower quality textures because, like I said, I can't really see a big difference. And if you wanted to, you could even go in and cut these down even further if you wanted to do that. So I leave that as an exercise for you, but 8.1 megabytes is a great deal smaller for this blueprint. So what I think I'm going to do, and I'm going to time lapse this so this video doesn't get too boring, is I'm going to go through all of these large squares here and just cut them in half. I'm going to cut their max texture size down in half of what they currently are, and then go back and take a look at the asset and see if I can't get this BP jet fuel down to close to 4 megabytes rather than 8. So let's time lapse this. Okay, so I found this default diffuse, which happens to be an engine content, and that's not one I want to mess with. So I'm going to go ahead and leave this default diffuse alone. I'm going to skip that one and go to the next T-Sand tileable. Okay, so I've cut in half the Wind, the T-Sand tileable, T-Metal painted, T-Grunge, T-Concrete tileable, _N and M. Actually, I didn't get the M yet, so I'm just going to really quickly do that. This is 1024. I'm going to cut it down to 256. And now I've cut that one down quite a bit as well. So we're going to see what happens when we save all and take a look at the size. It was 8.1 megabytes. We're going to browse to jet fuel, check out the size map, and now it's 3.1 megabytes. It's a great deal smaller. And that fuel pickup is starting to look more significant, right? Let's see how it looks in here. And honestly, I think it still looks really good. You can definitely tell the difference. It's definitely a little bit more blurry, but if I look at it here in the level, I think it still looks fine from the distance that we're looking at these from. So I think it looks really, really good, and we can live with those texture sizes. And BP jet fuel is a lot smaller. It used to be over 80 megabytes. Now it's down to 3.1, which is way, way smaller. It's 1/5 the size of Kix now. Now, if we migrate assets over from StackoBot, and those are using these textures, we have to keep in mind now that if those don't look detailed enough, we might have to go and remove those restrictions on the compression or alter the materials to use duplicates of these that have different levels of compression. But for now, this is looking great. In the next video, we are going to talk about what we can do about this size of the NS fuel pickup and see if we can't get that 3.1 megabytes down to closer to 2. So great job, and I'll see you soon. Welcome back. Now, in the last video, we took our BP jet fuel blueprint, and we saw that it had over 80 megabytes in size because of its hard references to the textures being used by the material on its static mesh. We saw that jet fuel, this tiny little pickup in our world, had larger memory than our full-on 4K textured skeletal mesh Kix. So that was quite a bit imbalanced, right? But we fixed that. We went through and found the largest textures by checking the size map for jet fuel. And we took those textures and we compressed them. We went and found, by searching for compression, the maximum texture size, and we kept cutting that down more and more until those textures took up less and less memory, and we kept checking on our jet fuel blueprint to look at our static mesh to make sure that it still looks decent, and it still looks pretty good. If you're not happy with that, just go back and compress these textures less. Now, one thing to take note of was whenever I found a texture being referenced from engine content, I did not touch that because I don't like to alter engine content. And as soon as I opened one of these assets, as soon as I browsed to one that was in engine content, all of a sudden now my folder structure is showing engine right here, this engine folder, and there's a lot of engine content, and we typically don't want to mess with engine content. So now I'm showing engine content, but I can go up to settings and uncheck show engine content here to get rid of that folder. And now it's not there anymore, and I don't really want to mess with engine content. But we got this file size down quite a bit by compressing these textures, which is great. And the smaller these materials got, the larger everything else started to look in comparison. So once you've compressed down textures and optimized on that front, how do we optimize even further by minimizing the memory footprint of this blueprint even more? And let's just say that we've reached the smallest texture sizes we're comfortable with here, and the static mesh is going to take 2.7 megabytes. Let's say we've accepted that, okay? But let's just say that we need to squeeze this size down even farther. We need our overall game project size to be smaller, so we need to cut as much as we possibly can. Well, if we can't touch the static mesh, this red square anymore, then we have to go to the next biggest square, which is the purple one, NS Fuel Pickup. This is the Niagara system. Now, the Niagara system, we can show that by scrolling up one tick on our mouse wheel, and we can see all the things that are taking up memory on this Niagara system. Most of it just has to do with the Niagara system itself. We're using textures here and there, but let's just say we don't want to mess with any of these textures. So how do we make this memory smaller on BP jet fuel? Well, the truth is that we don't actually need this Niagara system to be loaded in at the beginning of the game. We only really need it loaded in memory when we overlap with one of these. And we can delay loading this in memory so that we're not loading it right away. We can lazily load it. That's actually a technical term. Lazy loading is waiting until you actually need a resource to load it. So fuel pickup, which is, by the way, the Niagara system of the splashing fuel particles when we pick one of these up, those splashes there, those are not needed when we start the game. Let's say we're playing our game and we're running around, and maybe we don't use our jetpack for the first half hour of the game, and we don't even see those fuel pickups for a while. So there's really no need to load up that Niagara system if we're not even going to see it. That would be consuming resources that we're not using. And it's only later in the game when we finally come across some of these pickups and we actually pick one up that we need to load that Niagara system in memory. So how do we lazily load this NS fuel pickup on our jet fuel? We're going to learn how to do that in this video. And we're going to start by closing all the tabs. I'm going to close other tabs and keep my jetpack level open, and then just simply right-click on one of these jet fuels and browse to the asset here. So first of all, we're going to check out our size map. I'm going to keep this open on another monitor just so we can remember that this takes 3.1 megabytes of memory. And our fuel pickup here, if we maximize it, we see that it's 388.8 kilobytes. Not quite half of a megabyte, but it's significant. So we're going to move this off screen and see about how we can lazily load that fuel pickup. In other words, avoid loading it until we need it. So let's open BP jet fuel, and let's find where we're actually referencing that Niagara system. On overlap, we handle pickup effects, then wink out, then handle collision. Well, the pickup effects is where we're spawning those systems, right? So let's open that. And here we're referencing two assets. We're referencing the sound that we're playing, and we're referencing the NS fuel pickup Niagara system. So hard coding an asset into the input of a node is the same as hard referencing. We can tell by looking at the size map. There it is, NS fuel pickup. It's there because of this drop down right here. Now, we want to avoid loading this until we reach this node. As it stands, just hard referencing it here, hard coding it, creates a hard reference. That means this fuel pickup Niagara system is loaded in memory right away as soon as this blueprint actor is loaded into memory. As soon as an instance of this is in the world loaded up, which we have two of, then we're loading this up, whether we're playing the Niagara system or not. So here's what we can do. We can create what's called a soft object reference. Let me explain. I'm going to promote this to a variable. So dragging off, promote to variable, I'm going to call this pickup effect. And by default, it's a Niagara system object reference. And if we go down to the variable here and open the dropdown, notice at the bottom, it says change to, and we have 4 options. Now, it's already an object reference. We've seen that, but we can change it to a class reference, which we don't want. Remember, that's purple. That's for nodes that need the class and not an object reference, right? But then we have these soft versions of each. Soft object reference, soft class reference. And these are for lazy loading. This is a very important optimization technique, lazily loading assets. If I change this to a soft object reference, of course we get the warning that says, hey, this could break connections. Well, we know it's going to break connections because we're changing the data type. And this spawn system at location does not take a soft object reference. It takes a object reference, right? But we're going to change it anyway. We're going to let it break those connections. So once we're done, we'll close this window. And now look, our pickup effect is now not blue, but light blue. And we can see under variables that its data type, if we show more room, it has a light blue color. So this is now a soft object reference. Under the hood, a soft object reference is simply a file path. It's just the path to that asset in memory, and we're not going to load that asset until we specify that we need to do so. Now, if I click compile, we get an error message. That's those broken connections we were talking about, which means we have to break that connection to system template and compile again, because this is a soft object reference, which is not the same thing as an object reference. They're different. Now, if I drag this over and connect it, we get a conversion node from soft object reference to object reference. And what this does is it checks to see if this pickup effect asset has been loaded yet. And if it has, then it retrieves that loaded object. But we have not loaded this yet. So if we have not loaded it yet, this will return none. It will not be a valid value. So now that this is a soft object reference, we can go ahead and play test and see what happens when we pick up one of these. And of course, we'll see it because it's already been loaded in memory and the editor remembers that. But if we close down the editor and open it back up, let's see what happens then. I'm going to close it down first, and I'm going to open my project back up. And I'm going to let it open up my asset editors that I had open, and I'm going to play test and pick up one of these pickups. And notice we did not get our Niagara system because it's not loaded in memory. I'll try this one. Yep, still not loaded in memory. Because we have a soft object reference. It's lazily loaded, and because we haven't manually loaded it yet, then this conversion node just returns an empty value. It's not valid at all. what we have to do is check to see if it's been loaded yet. And if it hasn't been, we need to load it. And there are two ways to load a soft object reference. So let's find out how to do that. Well, first I'm going to break these wires and move the spawn system node ahead a little bit. And we'll take this node, which will not be valid until we've loaded it. We're going to give it an isValid node. And that way we can check to see if it's been loaded yet or not. Now, the first time it will not be valid. And that's when we need to load it. So one way to do so is to take our soft object reference, drag off and type load, and we get this function called load asset blocking. What does that do? It loads the asset. But it's called load asset blocking because this is what we call a blocking call. This will stop execution of everything else in the game temporarily until we finish what we're doing here, which is loading the asset. So the first time we load up the asset, this could cause a glitch in the game. And if something important is happening, we'll see a brief pause, a little bit of lag. It might not be dramatic enough for us to notice in this project, but what we can do is we can simply load the asset. Now, it returns an object reference to the object, which is not the data type that we can use with spawn system at location, but we can take pickup effect and drag it straight in and get that conversion node. So this is going to give us the Niagara system object reference. So what we'll do is we'll check pickup effect. If it's not valid, we'll hit this load asset blocking, which will stop the whole game for a brief moment while we load the asset, and then we'll spawn the system. And then the next time this gets called, pickup effect should be valid, at which point we can print a string and say already loaded, and we can do the same thing. We can spawn the system. So we can go back down to spawn system and we can get the pickup effect without having to use load asset blocking. So now if we press play and we pick one of these up, we won't see that print string yet, but we will load it. Now, this was not expensive enough to cause a noticeable glitch in this game, but it did perform a blocking call. So there was a slight hitch, we just didn't notice it. But now that it's loaded in memory, if we go and pick up this pickup, well, we see already loaded. So we didn't have to call load asset blocking the second time because pickup effect was already loaded into memory. So that's one way to load assets, and it's typically only used when you know a hitch in the game is not going to affect anything. Maybe there's a loading widget on the screen that says loading assets with a little loading bar. You know, you could use load asset blocking in that case. But if this is during the game and it's crucial that you don't have any glitches or hitches in the game, you can use a different way to load assets. And that way is to load them asynchronously. Now, we can't do that from within a function. We have to do it from within the event graph, which means we need to make an event for doing this. So we're going to make a custom event, and we're going to call this load pickup effect. And we're going to load the pickup asynchronously. We do that by taking our pickup effect soft object reference, dragging off, and if we search for load here, we'll see this time, because we're in the event graph and not in a function, that we have another option, async load asset. It has a little clock on it. This is an asynchronous call. We can't call this in functions, just like the delay node or other nodes that we call latent nodes. These are things that start performing something and then have an execution pin that will execute once it's done doing that. This actually does the async loading of the asset on a separate thread. Interesting, right? Look up multi-threading if you're interested in parallel lines of execution, basically multiple bits of code running at the same time. We're going to load our asset in on a different thread, and once that loading is done, we have this completed wire that will be executed. Now, it's important to understand the difference between these two output execution pins. The top one is executed right away. As soon as we've reached this node, we'll continue with any logic we want to keep doing. That is going to execute right away, And our completed is going to execute sometime later, as soon as the loading of the asset has been done. And at that point, that's when it's safe to use the pickup effect. So once we've loaded the pickup effect, we can then use it. We can drag off of pickup effect. And if we want to get the actual object reference from the soft object reference, we can use resolve soft object reference. And this gives us that same conversion node that we've been using. After that, we can spawn that Niagara system. Just like we're doing here in handle pickup. We can use spawn system at location. So I could copy these two nodes, go back out to my event graph, and paste them in. And in the completed case, I can call spawn system at location. It has to be completed. If we've connected this to the top pin, well, then this pickup effect will not necessarily have been loaded in memory yet by that point. But in completed, it has been loaded, and we can plug in that object reference here and spawn the system. So if we call load pickup effect, we might see a little bit of a delay from the time we hit this node to the time we hit this node, but it's not going to block the execution of the game thread, which means the game itself will keep going. There won't be any hitches or glitches. It's just this spawning the system that will be slightly delayed the very first time we load this asset in memory. Only the first time. So back in handle pickup, what we're going to do is if pickup effect is not valid, rather than load asset blocking, which could cause a glitch in our game, we're going to instead call our custom event, which we called load pickup effect. And what that's going to do is execute async load asset. And once that's done, we'll spawn the system here. And this will only be done the first time. After that, the pickup effect will be loaded in memory, and then we'll get to simply resolve the soft object reference here because it's already loaded, and we can spawn the system. So let's see how this works. We're going to press play, and if I get one, I'll get already loaded because remember, the editor remembers having already loaded this in memory. So to see the full benefit, we have to close the editor and reopen our project once again. And now we should be loading this in for the first time. So if we go in and press play, the first time we pick one of these up, we'll actually be loading that asset asynchronously. So thus far, that Niagara system has not been loaded in memory. These two actors only have a file path. That's the soft object pointer, that file path pointing to where that Niagara system rests in memory. But once we load it, we'll see that effect. Now, let's see if there's a noticeable delay from the time we overlap to the time we see the effect. Well, not really. We couldn't really see a noticeable delay. But now that it's already loaded, if we pick up this one, we see already loaded in the top corner of the screen. So we only had to call async load asset the first time. Now this is a great optimization because if we go to jet fuel and we look at its size map, it used to be 3.1 megabytes. Now it's only 2.7. And notice that Niagara system is gone from the size map because it doesn't have that object in memory. It's only dynamically during the game when we overlap with one of these for the first time that we actually load the Niagara system in memory and increase the size of a BP jet fuel instance. Until then, we haven't loaded it yet, and this decreases the size of BP jet fuel. We've gone from over 80-something megabytes to now down to less than 3, and you can go so far as to lazily load basically any asset that you want if it makes sense to do so. We can do this with our jet fuel meta sound, which is 37 kilobytes, and if you wish to do so, I leave that as an optional exercise for you. But for now, I'd say that this has been a great lesson in performance and optimization. Our jet fuel blueprint is much smaller, and it's lazily loading its pickup effect using async load asset. This is an advanced topic, so congratulations for learning about it. I'm very proud of you for that. Excellent job. We can continue now in the next video. I'll see you soon.